Good morning, everyone. If you could please find a seat, we're going to get started in a minute or two. Welcome, and please find your seats. All right, good morning, everyone. Thank you for joining us. It's time for us to get started today. We have an exciting program ahead of us. My name is Rachel Bruton. I am one of the co-chairs for the 2026 Indian River Lagoon Symposium, along with Kristen Davis and Matthew Ajamian. This symposium is dedicated to advancing science, dialogue, and stewardship for one of Florida's most important ecosystems. Since the inception of the symposium in 2012, it has served as a vital forum for sharing cutting-edge research, fostering interdisciplinary collaboration, and translating scientific discovery into meaningful strategies for the management of the lagoon. Every year, scientists, resource managers, educators, and students come together with a shared purpose to deepen our understanding of the lagoon, to strengthen collaborations across different sectors, and to inspire solutions that support the future health and sustainability of the Indian River Lagoon. First off, I want to say that we are deeply grateful to our supporters who helped make this possible: Florida Atlantic University, the Harbor Branch Oceanographic Institute Foundation, and the IRL National Estuary Program. By investing in scientific exchange, student participation, and community involvement, our sponsors are helping to advance the knowledge and partnerships that safeguard the Indian River Lagoon and help keep it safe for future generations. So thank you to you all for your continued commitment to this ecosystem and to the people working to protect and understand it. So let's give them all a round of applause, please. All right, so just a few quick logistical notes before we begin. Everyone, please take a moment to ensure that your cell phone is on silent. Restrooms are located down the hall this way and also upstairs. We have a water bottle filling station and a water fountain on the first floor. So if you want to step out for a little bit and work on your computer, there is a live stream that's happening in the computer room just across the hall here. On our second floor this year is where the poster session will be held in rooms 209 and 210. There is an elevator that's located on this side of the building for anyone who needs it, as well as 2 flights of stairs to get up there. So thank you to everyone who's offered to judge student presentations. The judging room is also located on the second floor. I do have the assignments for 3 judges, so if you could come get them, please. Ashley Ryume, is she in here? All right, we'll get that to her later. Someone with the last name Antonio? Nope, okay. And then if anyone is not judging and is really excited to judge, please come and get this assignment right now. Free to the first, there we go. Thank you, Sam. All right, so we're really excited this year to introduce a new format of presentations, which are digital posters. We've never done this here before, so we'll be excited to get some feedback on it. We hope that it works well. We hope you all like it. And please help the new digital poster presenters kind of get through this first round. Digital poster presenters, please do arrive 15 minutes early to your session and help keep your session on track by moderating the timing of the previous presenter. All right. So I'm going to quickly walk you through our day ahead. We're going to begin with a keynote from Dr. Christine Angelini from AECOM, who's going to help frame our theme of innovation in lagoon science. This morning features sessions on novel applications, sensor and remote technologies, along with our first 3 minutes, 3 slides rapid presentations. After lunch, we shift to molecular innovation, monitoring, restoration, and living resources, with 2 more fast-paced 3 minutes, 3 slides sessions. Please be sure to explore the posters during the breaks and join us for the evening reception, and we hope that you'll all stay for the Student Awards to help celebrate the awesome work being done by these guys. So this year, our theme is emerging technology and novel methods. So we're shining a spotlight on technological innovation and how this can help us in lagoon science. Across disciplines, new tools and approaches are transforming how we conduct research, how we monitor change and inform management decisions. At the same time, long-established scientific methods are being applied in increasingly creative ways, improving how we can analyze data, visualize complex patterns, and support evidence-based decision-making. Today's presentations will highlight the growing role of artificial intelligence, machine learning, and molecular techniques such as environmental DNA, how we can use advanced advanced sensor systems, sorry, that's kind of a tongue twister there, remote sensing technologies and autonomous platforms to understand what's happening in the Indian River Lagoon. So together, all of these innovations are expanding what we can measure, accelerating how we interpret change, and strengthening our ability to respond effectively. So our goal today is not simply to showcase new technology, but to explore how these tools can meaningfully enhance our stewardship of the Indian River Lagoon. And now for a look back at past symposiums, please welcome Kristen Davis.
Thank you, Rachel. Before we dive into the next portion of the program, I just wanted to take a few minutes to share a bit of background on the symposium. So in 2012, with encouragement and funding from the Harbor Branch Oceanographic Institute Foundation, our main supporter ever since, Dr. Dennis Hanasak, founded the Indian River Lagoon Symposium and assembled the first steering committee, bringing together organizations from across the lagoon. From the beginning, Dennis's vision was to create a space where scientists, resource managers, educators, students, and community members could come together and share knowledge and build partnerships focusing on the lagoon. The inaugural symposium took place right here at FAU Harbor Branch in this auditorium. The theme was the Indian River Lagoon looking forward, focusing on the future of the lagoon's ecosystems and management strategies. And some of you might see yourselves in this photo. So each year, the steering committee selects a theme, identifies a keynote speaker, and builds the program around those ideas. Over the past 15 years, we've covered a wide range of topics, though some themes do tend to resurface, including restoration, water quality challenges, and harmful algal blooms. Because as we all know, those issues remain central to the lagoon to this day. When the symposium began in 2012, student awards weren't part of the program. In 2014, we introduced a single award for the best student poster. But that year, the judges came to Dennis and said, "We have too many good posters." And so in true Dennis fashion, he didn't scale back, he scaled up. And in about an hour, and just from the people in the room, $200 were raised, were donated to fund 3 awards in total. And so this is just one perfect example of how this community rallies to support the students. And since then, the awards program has continued to grow. In 2015, we added an Outstanding Student Presentation Award for oral presentations. In 2019, we introduced the People's Choice Award, which I'll be giving a couple more details on later. And that gives basically all of the attendees and those participating on the live stream the opportunity to vote for their favorite presentations, whether it's a 10-minute talk, 3-minute talk, poster, or for this year, digital poster. In 2021, we renamed the Outstanding Student Poster Award to the Leroy Cresswell Best Student Poster Award, honoring Leroy's invaluable contributions to the Lagoon and his mentorship of students. In 2022, the IRL National Estuary Program established the Promising Scientist Award, and this was done to recognize a student whose research shows exceptional promise for advancing our understanding of the lagoon. And then last year, in honor of Dennis's contributions to this symposium and to the lagoon, the steering committee established the Dennis Hanasak Storyteller Award. Dennis cared deeply about good science, but also communicating science in ways that are meaningful and accessible. And so the Dennis Hanasak Storyteller Award focuses on the overall narrative of the research and how it resonates with the audience, extending beyond the judging criteria of the student presentations and the People's Choice Award. Just a reminder that all scores are due by 7 o'clock so that we can have our award ceremony promptly at 7:30. And this is how you can vote for the People's Choice Award. So you will also see this in the QR code, the General Resources QR code that has a link to the program, the abstracts, People's Choice live stream. It's a one-stop shop. So please take your time. This does open at 9 o'clock. I'm going to remember to do that. And it closes also at 7 o'clock. So that's a quick look at how the symposium has evolved over the years and a reminder on how to vote for the People's Choice. So now we're going to talk about this year, 2026, year 15. So let's see. This year we have 367 total attendees that registered. Not all of them have come, but we have at least 350, and this does not include our live stream. And so about 69% are professionals, and the rest represent graduate, undergraduate, and high school students, which is a really strong student presence, and it's always really great to see. And supporting students has always been a really important part of the symposium from the beginning. So it's something that keeps the science in the lagoon moving forward. Let's see. Okay, so show of hands. Who's here for the first time for the symposium? Wow, okay. Yep. And how many returning veterans do we have? Okay. Yep, that you guys did a great job filling out your registration. That reflects exactly what we saw when you filled that out. Even though the ones who said yes didn't tell me how many years, they were coming. That's fine. And somebody said that they were here more times than symposia that we had. So maybe we had maybe we counted twice. I don't know. And lastly, just for fun, who's been here? Who's been to more than 10 symposia over the years? Nice, great. Well, that's incredible. I think it's amazing. Sticking with the community and really moving science forward is so important. So as you can see from this graph, most returning participants have attended within the past 1 to 5 years, but we also have a solid group in the 6 to 10 year range, and then those few who have been to more than 10 over the past years. We have over 72 unique organizations represented this year, spanning universities, government agencies, nonprofits, research institutions, and the private sector. And this range of perspectives is essential to solve some of the challenges that we're facing in the lagoon. And then finally, the heart of the symposium is the presentations. So there are more than 100 presentations this year, and about 43 of them are from professionals and early career researchers, and about 57 are student presentations. So overall, this year's symposium really brings together a large, diverse, and deeply committed community, and it's exactly what we need as we look forward to the future of the lagoon. So before we move on to the next part of the program, I just want to take a moment to recognize the many, many people who have made the symposium move forward. From FAU Harbor Branch, our director, Dr. Jim Sullivan, Patrick Bowles, Audrey Slade, who you'll see running around all day today, as well as Gabby McHenry, Tina Angelo, and a lot of the other admin team for all of their help. Our IT support, Dylan's in the back, and you'll see a couple others here today, making sure everything runs smoothly. And we also appreciate the support of Stuart Moreau and the facilities team for getting everything going. Elizabeth Saluski, and then the Seas Lab and Team Erlo. And then I'd also like to recognize our steering committee, whose guidance and leadership over the years have helped shape the symposium. They also organize the student judging process, which is a major undertaking and is an important part of the supporting emerging scientists. So please join me in thanking both the steering committee and all of the staff that has helped today. I'd also like to thank my fellow co-chairs, Rachel and Matt, who have been coordinating the details, solving problems, and discovering just how many emails you can get leading up to an event. And with that, I'd like to introduce Matt Adamian, who is going to introduce our keynote speaker.
Okay. So, my pleasure to introduce our symposium plenary speaker, Dr. Christine Angelini. Christine serves as a vice president within AECOM Advisory, where she leads strategy and growth within the nature services market. In this role, Christine assembles and leads interdisciplinary teams to innovate solutions that sustain critical ecological functions while addressing infrastructure and operational imperatives for government, NGO, and private clients. A marine community ecologist by training, Christine specializes in coastal habitat restoration design and mitigating watershed impacts on estuarine water quality. Prior to joining AECOM, Christine was the founder and executive director for the Center for Coastal Solutions and the Scott and Barbie Presley Rising Star Professor in Environmental Engineering Sciences at the University of Florida, where she was faculty for over a decade. Christine has authored over 100 peer-reviewed articles, including publications in Science, Nature, and PNAS, and maintains a vibrant network of global collaborations focused on advancing science-based, stakeholder-driven environmental management. Please join me in welcoming Dr. Angelini.
Good morning, everyone. All right, I'm going to go back to my professor days to start with a couple of questions for all of you in the audience. The first is, let's see if I can get this going, is a little reflection on, let's see, maybe the mouse will be the way to do this. Why are you here this morning? I'm going to take a second. What sort of like put you in the mind space that you wanted to get in your car and drive here to get to the IRL symposium this morning? So I'm going to take two answers from the audience. What got you out of bed to get here today? All right. Anyone here? Dwayne, why did you come to the IRL symposium today? All right, you're here to share your stuff. All right, do we have Ron Brockmeyer in the audience today? Ron, okay. What brought you here today? All right, some obligations. All right, well, I'm going to say that maybe for some of you, let's see, let me see if I can get this animated. There we go. Is that you came to learn some new things, you came to connect with some friends, gain some professional experience for you junior folks in the audience, and many of you brought some new emerging technology and tools that you want other people to know about and are socializing it here. So it's these personal outcomes, the value to you that, you know, the planning committee really sort of put all this effort into making this event about. But the bigger question that I really think we need to start this day with is, why are we here? What is this group here to achieve? So I'm going to take, again, two answers from the audience. But if you look around the folks that are here, what are we looking to achieve? Yeah.
The lagoon, we all
Amazing. All right. A shared place, a shared sense of pride about the place that we're working in. Any other answers of why you want to connect with the people around you for the sake of the event today?
Christine, I'll jump in.
Thanks, Dwayne.
Not only sharing knowledge and experience, but these new technologies need to be somewhat integrated through this community of practice to make them most valuable.
That's right. So there is a sharing. We need to harness each other's capabilities. And so I would say we are here for the bigger vision of a lagoon that tomorrow supports stronger communities, cleaner water, a thriving economy, abundant wildlife. I would say we have a North Star as a community and a shared purpose as a group of why we are all here in this room today, committing our time and our energy and effort to being here. And so, if we share this common North Star, a lagoon that's brighter tomorrow than it is today, then what is it going to take from where we are in this moment to say 2040 to get there? Well, it's going to take a whole bunch of different things and a whole bunch of different skills from the people in this room. And so maybe it's community buy-in and support that Jesse Wales is leading in the Northern IRL. It's new scientific insights from the bright brains from our academic programs. It's innovation and policy and funding. It's going to take all of this, right? And so we're all heading to a shared direction, but perhaps on different paths. All right, so my talk today is a little bit of a look back in my own history of some of the insights that I've collected over my career that has been really dedicated on focusing on revitalizing nature with a focus on the coast. And I'm going to sort of pull some lessons from this career that I think could be helpful as we go towards that North Star. So I'll start with a brief overview of some of the work that I've led as an undergrad in salt marshes and food webs. We'll talk a little bit about some of the work that I led when I was a professor at the University of Florida, in which my sort of scientific basis started to get connected with folks that were working more on innovations in policy, community outreach, essentially expanding my connections from being just a scientist to a scientist embedded in a broader network. And now I'll be talking a little bit about the work that I'm leading as a consultant that's now at this kind of hyperscale of connectivity across, where my science and science foundation is connected across a sort of a hyper network of different entities. For the sake of time today, I'm not going to tell you much about the work that I'm sort of currently focused on financing nature revitalization, but if that's something that you're passionate about, please feel free to reach out to me. I'm really interested in how we unlock private finance to drive our restoration goals forward, and so this has been something that's been front of mind for me over the last year, but it'll be off the schedule today. All right, so let's talk a little bit about time when I was a 20-year-old undergraduate. In my first research experience when I was at Brown, we're going to take you up the coast to New England. And this is what the marshes looked like at this time, which is this lower sort of margin of the marsh is bare of vegetation. It's riddled with these burrows. And this is supposed to be lush meadows of Spartina, cordgrass that builds the marshes in this region. And so the questions that my lab at the time was setting out to sort of answer is what is causing the widespread die-off of vegetation across New England and the sort of commensurate bank erosion that was happening there. So this is 20 years ago, my first academic adventure. And so we did tons of experiments in this system, manipulating, the presence of, crabs. We were tethering crabs on the banks. We were like in the field, day in and day out, studying the dynamics and trying to untangle, what was causing die-off in the system. And this was the culprit. It's the purple marsh crab. It's a really beautiful animal. It's a grazer, and so it eats cordgrass, both above and below ground. And it also excavates these extensive burrows on the banks of vegetation. And so we made some really powerful insights through experiments and large-scale surveys that it was grazing and burrowing that was causing die-off. We then did some additional work in areas where there was intensive recreational fishing and not to untangle whether perhaps all the fish, all the hooks in the water and all the crab traps in the creeks were potentially causing a tip in the balance in this system where when you remove those predators, maybe it's releasing these crabs from predation pressure, and it's in these circumstances where you get overgrazing of plants. And so through a lot of intensive work across many different systems across the Cape with high intensive local pressure, from fishing and areas that were really kind of prevented from having intensive fishing, we found that localized overfishing is in fact triggering these crab outbreaks. And finally, we started to notice these kind of larger patterns in these New England marshes where there's a lot of historic ditching for draining these marshes for mosquito control. And one of the things that we found is that in cases where we have intensive ditching, but also lots of fishing, these were areas where the whole marsh platform was exposed to die-off. And so what you're seeing in the middle is an example of a marsh where there's intensive fishing, lots of hooks in the water from local recreational fishermen, but there's also intensive ditching in this system, and this allowed essentially the crabs to sort of take off in these marshes and denude large areas of the landscape. So really sort of a pile of science coming together to really understand, what was driving change in this system. And so we had some really sort of high impact of potential impact of these discovery. This was like a team of scientists like in relentless pursuit of like understanding the system. This is some of the folks that I worked with during this time. We were prolific writers. We produced a pile of publications all over the map in terms of where they ended up. Huge amount of experiments, data analysis that went into all of this work. And we were really focused on making sure people knew about it. And so we got out to the journals and the local news outlets, and our work was featured all over the place. The New York Times, the Boston Globe, Providence Journal. And so there was, we felt like we were doing the job of not only sort of telling the science story, but also getting it out to the world. But what we found is that work, all of that work, had very little management and policy implications, right? We did all this effort, multiple rounds of grants from NSF. And I'll tell you a bit about why that is. But the first thing I want to mention is for all the students in this room, the research that I contributed to as an undergraduate, and this could be you, has really substantial management and policy implications. Quite simply, conserving predators in the systems is really important for revitalizing foundational plants and the habitats they form. We have to manage the top of the food web in order to get the bottom of the food web to flourish. In addition, from the bottom up, there's a significant benefit of thinking about restoration of ditches as a means to enhance the resilience of the system to these unbalanced food webs, but also over the longer term to sea level rise. And Ron, I hope you're listening. You're my favorite ditch person in the state of Florida. But we had really ineffective application of all of this work because managers and policymakers were not meaningfully included in our pursuit of this science journey. We did not bring them in the field with us. We did not include them in the experimental design. We didn't include them in the communication journey. We really just engaged with journalists at these prominent publications. And so I learned a lot from that period where I felt like we had done a huge amount of work, but the translation was not nearly what it could have been. And so this is, wisened me up a bit as a faculty member. And so here I am now, about 10 to 15 years later, had the pleasure of working with an amazing group of scientists. This was a project that was led by Ashley Smith with strong collaborations from Nikki Dix and Caitlin Dietz from the GTM NER, Hallie Fishman and AJ Reisinger. And we wrote a science collaborative grant. And the purpose of this project, and this may resonate with you guys working in the IRL, was to understand what the key drivers of eutrophication were in a rapidly urbanizing estuary. And so where we were working was in the Guana River system. It's like your sister estuary to the north, for those of you who haven't spent time in this system. But what you can see is sort of a land use development index map of the watershed here. And so it's hot red and orange in the upper watershed. This is an area with lots of golf courses, lots of development, and intensively more and more people getting packed into the landscape here. And so not surprisingly, this is a story you guys maybe know well, we're seeing increases in chlorophyll levels indicating sort of eutrophication in this system. So these are two graphs showing chlorophyll A levels that are in the lake, the Guana Lake, which is in the upper part of the estuary, and then the Guana River is this kind of lower estuarine sort of region. And so what we've got is kind of over time is this kind of increasing levels of chlorophyll in the system, and there's nutrient data associated with this if you're interested, that Nikki just published this last year. And then we also see, some seasonal dynamics where the blooms are particularly sort of intensive in the mid to late sort of summer. And we're getting these kind of surges of elevated chlorophyll even in the downstream estuarine areas. So this is a system that needs some solutions to address. And what we were particularly curious about was understanding whether the naturally occurring distribution of bivalves in this system, both the eastern oyster that grows in reefs in the lower intertidal margins of the estuary, as well as these rib mussels that are packed up in the marshes. So they have complementary distributions from the lower elevation to the higher elevations. But what is the role of these two filter feeders in sort of mitigating eutrophication as it is today in their current distribution? And can we think about restoration and restoration aquaculture of particularly oysters as a potential solution for managing nutrient loads and their eutrophication impacts in this system? And so we took a really different approach from where I was as an undergrad. In this case, we built this kind of team of academic scientists with managers that work on the ground, translating science into application. We then had a team of kind of collaborators and invested actors, as we call them, from multiple different departments, the local city, the county, the federal, the Army Corps of Engineers. Some of you guys were some of our folks that participated in this. We've got some of them in this room. And we worked through a really deliberate process in this project where we worked to understand, what are the critical needs of these actors to manage eutrophication in the system. We then took those kind of needs and drove our scientific process forward to say, how do we understand and take the best available data and research to understand those management needs? And then we essentially evaluated these results. And what is most important, I think, about this project is number one, is that we continued to engage these entities over the course of the project, but we summarized our results in actionable outcomes that those managers and folks that are engaged in policy at multiple levels could actually use. So just a couple things around what did we learn over the course of this project that you might be interested in. So what I'm going to be sharing with you is just a figure here where we're seeing the nitrogen storage that's on the left and the carbon storage on the right that's packed in the shells and the tissue of oysters in purple and then those rib mussels in green. Right now you're seeing this on a per meter square basis, so any given plot of the system. How much nitrogen and carbon is being stored by these different components of these bivalves. And the big thing is you see the giant purple bars, right? Oysters are doing most of the work in terms of nitrogen and carbon storage in this system. And they're doing far, outperforming mussels on a per unit basis, but also if we scale this up to the estuary scale, they're doing it on a whole estuary scale basis as well. Oysters are doing 60 to 90% of essentially the carbon and nitrogen storage process or function in the system. And the other thing to note is that these storage services are far greater up by the dam in the upper river than they are downstream. So we have variation in the functionality of these bivalves and essentially their nutrient mediation functions. We put the numbers in context of how much nitrogen is coming into this estuary. If we take these estimates of what the bivalves are doing, how does this measure up to the amount of nitrogen that's coming into the system? And what we found is that oysters and mussels together are assimilating about 630 kilograms of nitrogen per year in this system. And what that equates to is about 6% of the total nitrogen load and 12% of the particulate nitrogen load coming into the system. So they're not doing all the work to mop up all those nutrients, but they're doing significant work. All right, the next thing that we did was simulate oyster aquaculture in this system. Can we deploy oyster aquaculture cages in a way that might boost the eutrophication mitigation function, if you will, of these bivalves. And so we did is we simulated experiments where we had either oyster aquaculture cages distributed throughout the system or just up by the upper dam where we know that they're doing the most work in terms of mopping up nitrogen and carbon. And what we find is that we can really maximize the nitrogen storage function if we pack all the cages in the upper part of the estuary. But from a feasibility perspective, if we wanted to remove, say, 25% of the annual nitrogen load using oyster aquaculture, we would need 19,000 aquaculture cages to accommodate and accomplish that much nitrogen removal in the system. All right, so what we did is we ended up putting our results from this project into essentially the top 10 management and science recommendations. There's an executive summary that's really easy to read. It has essentially the high points of all this work. And this is us taking a body of work, including what I just showed, and distilling it into something that is now a set of sort of actionable solutions. We also put this work into a peer-reviewed publication where we've got essentially these different recommendations for the system and who is responsible for taking those management or science actions to activate solutions in this system. And I wanted to show this graphic because the point is that, as you guys probably well know about eutrophication, is we don't fully understand it, but there are solutions on hand today, and that there are many different agencies and entities and organizations that need to be activated to take management and science recommendations to the next level. So you do not see the same organization in all of these buckets across this system taking action to essentially address eutrophication in this system. It's an all-hands-on-deck approach to addressing these challenges. And one of the things we sort of highlight is that there's a bunch of things that we don't have enough science right now today to answer. And so one of these recommendations is to do more science on the things we don't know yet. So just to close this out, our research reveals that these bivalves in the system are providing nitrogen cycling services that are meaningful at a system-wide scale. The bivalves do matter. And 6% of the total sort of nitrogen load is getting sort of cycled through their system. That spatial planning of aquaculture can significantly increase the nutrient removal benefits. So if there is hot spots of nitrogen input into your system, there may be opportunities across the IRL to systematically be deploying these restoration aquaculture approaches in those hot spots to maximize their removal benefits, right? If we want to be using that as a part of our mitigation solution. And so we've got good data from an adjacent system to show that that's the case. And that I think that, at a system-wide scale, while the mussels seem to be not doing as much as the oysters, they provide spatial complementarity, they support essentially this function, and so I think we should be thinking about a kind of multiple species approach to management and not a single species approach exclusively. And through our co-production process, what we realized is that this structured engagement, continuing to come back to stakeholders, is really hard. People have fatigue. They're tired of getting asked, like, what do you need? The researchers are like, I can't deliver work that the managers need, and so I don't know how to do that in my dissertation timeline. Like, it is hard to do this collaborative science work, and you feel like you're crossing each other at different planes all the times. But going through this really boosted the quality of applied research that we produced through this work. I think that decision makers have really appreciated that we took complicated science that's in publications and distilled it into those clear recommendations. And that where we were willing to endorse certain management actions was appreciated. Hey, we have enough science to say that this is a worthwhile management action for you to pursue. But we also flagged where the science wasn't strong enough. And I think this kind of understanding of this is what we're willing to say and this is what we're not willing to say yet because we don't know enough is really critical for building trust. All right, so the last thing I'm gonna just briefly talk on is work that I'm a part of now because I find it really inspirational. But I've had an opportunity over the last 18 months to be a part of an effort called the Nature Record. This is the first holistic assessment of the U.S.'s lands, waters, wildlife, and the benefits that these systems provide. So if you think about, all of the nature that exists across the U.S. and its territories, how is it doing? How are we doing at managing these systems? It's an effort that involves 100 authors, and I've had the pleasure of working on a chapter that I find, again, inspiring, which is working on the bright spots in nature. This is a chapter that's led by Timon McPherson and Emmett Duffy, who have taught me so much about how to do collaborative science. But I just wanted to leave with a couple of notes about bright spots because it may be inspiring for you as well. So bright spots in nature, what are they? These are species, communities, and ecosystems at all scales of organization that are performing substantially better than expected given the general environmental conditions and sort of human pressures that are on our systems. There's these areas where I can't believe it's working. So some kind of examples, we are seeing recovery of bald eagles across the US. I mean, many of you have seen them now on a somewhat regular basis. We have examples from sea otters recovering in California, and they're, stabilizing food webs, and we're seeing coastal kelp forests and marshes flourishing as a result of the recovery of, decades of conservation of this iconic talc predator. And then we've got some examples of bright spots here in the lagoon. So this is a picture of one of Linda Walters' experiments or projects where they're restoring oysters, and that used to be a degraded bed of oysters, and you've got a lush mat of essentially oysters thriving. You have bright spots in your backyard that are working. And so the point of this chapter is to, number one, document where these bright spots exist and to leverage knowledge of how they're formed so that we can replicate and scale them across those species, communities, and ecosystems that are now dim. They're not doing so well. So just a couple things that we learned from this process. Number one, there are many examples of success. We did a comprehensive literature search. It was pretty exhausting and not something I necessarily want to do again. But we have examples of bright spots across many different ecosystem types. There's examples where they're occurring and where we're doing sort of nature conservation and large-scale restoration. There's examples of bright spots in production systems where fisheries are doing better today than they were decades ago, or the same thing on farms and other areas where we're producing food. And amazing bright spots in urban systems as well. And so these are sort of speckling the US landscape. Number two is that enabling conditions are really critical for getting bright spots to not only emerge, but to sustain themselves overall. And so what we mean by enabling conditions are essentially things that fall in the kind of social enablers, ecological enablers, and technological enablers. And you see some examples of these things. Partnerships among disparate institutions, new ways of thinking about funding and resourcing projects and programs, how you set up proper governance and oversight of projects, those are underpinning the formation of bright spots. Similarly, there's things around the natural ecology of systems that give rise to bright spots. And some technological solutions as well. The way that you guys are designing innovative monitoring systems that allow for proactive management. And so these things all can underpin the reason why these bright spots kind of form in the first place. And we have this hypothesis that really isn't shown well yet in the literature, but that when you activate multiple enablers over time, this can be a mechanism to not only just sort of sustain bright spots, but also help them grow, from their current footprint. And so I want you all thinking about how you connect to these different pieces. And finally, this may be taboo to talk about, but equity can enable and sustain bright spots. Not only when you provide equity in what's going in as inputs into the decision making, where you're acknowledging that people from different sectors bring unique knowledge, and that should be driven into the decision making process, but that we're providing equity in how decisions are made, that there's different voices being brought to the table. And finally, who benefits from bright spots also matters, is that we're not just having the wealthy communities that can do local restoration benefiting from bright spots, but that there's bright spots with their under-resourced neighbors as well. And so these are just a couple of examples where there's been tremendous progress in co-management of tribal lands in the West and Bears Ears, and it's just really remarkable example of equity and governance of remarkable natural resources. And then an example that our team at AECOM has been involved in East Newark, New Jersey, where we've taken a brownfield site that was a liability for one of our industrial clients and turned it into a park that's supporting an under-resourced area in that city, and improving property values, improving health outcomes, and so there's many different examples of these. All right, so to close this out, with the kind of bright spots in mind, I want to return to, what can each of us do to brighten the Indian River Lagoon? And so I want you thinking about how you are building your network of innovation by connecting your ingenuity with that of others. And so many of you are very good at this already. I see examples in the room of people who know how to cross-connect. But we can all do it better in a more effective way. And I think that what it means is sharing your own knowledge and insight and energy with others, but also being willing to learn and know from them to build these networks that are more robust and also more interesting than what we each accomplish in our own sort of lane. And so I encourage you to think about your own journey today of how you're building your network. In addition, as we think about what we can do to brighten the Indian River Lagoon, what I would say is we have responsibilities to align our institutions in a way that are accelerating progress towards that North Star. So rather than a system where we all are on different paths, I'd like us to think about whether there's a way to start weaving together in a more intentional, synergistic, effective way to get to essentially a brighter system for the lagoon. And that also can come from interactions that occur over the course of today. So with that, I'd like to say thank you. Enjoy this amazing opportunity you have to be here with all of these people, and I look forward to talking to you over the course of the day. Thanks.
That working? Okay, here we go. The first session. So first up, we have Dwayne DeFries coming from somewhere, talking about emerging technologies and novel solutions for the lagoon. They'll have warning signs. We do have the net, so.
I advance here, Chuck? Or the... Or do I just use this?
You can use the slide. You can use the keyboard. You can use that.
I use the keyboard.
And then this is on if you need.
Good morning, everybody. That was an amazing speech and keynote. And you'd think that Christine and I probably had a conversation ahead of time. And at 10 o'clock last night, I wasn't exactly sure where I was going to go today. So I'm going to feed you from the fire hose of a different perspective on innovation, technology. About 48% of you in the room are students. There's a handful of what I would call innovators who are actually building the tools that you are all using. And I want to integrate that story with the National Estuary Program, where we are after 10 years, what we've done in this innovation and technology space, and also talk a little bit about some unique examples that I've stumbled across over the last few years, and we'll see where it goes. And so I always like to say, where are you getting your information from? And I am not an expert on innovation and technology, but over 20 years ago, I recognized how our industry, and I call us an industry, you are a collaborative governance community doing science, resource management. You just heard taking that science to decision makers. We have never been recognized in the marketplace of economic enterprise in any way close to tourism, aviation and aerospace, maritime industries, And that is beginning to change largely because of the work all of you are doing collectively and around the state. And the last 3 days I've been in Tallahassee, and somebody said, why are you so interested in this? So go down to the very last example. So I've been 20 years recognizing that we are a workforce. That's important. I didn't realize how tough it was to take innovation through a concept to an early stage company, cross the commercialization gap, and actually have a product for all of you and us to use. And I was in that company, and that company failed, even though all of the technology worked. This is a tough thing to bring technology to the forefront and commercialize it. And so I'm very sensitive to that, and I've embedded kind of that interest into the NEP over the last 10 years. I did a quick look because I was wanting to see how many students, but how many tech innovators are in the room. Raise your hand if you're a tech innovator. You're actually creating a product, whether it's an IT product or a hard sensor. So we've got a few people who are using technology, but very few in the room that are creating, but many of you are testing it day to day. Something like eDNA, the applications are very unique and very different. We're going to see that today. But you can also see kind of this workforce structure, and I'm going to talk about that a little bit. So when we restructured the NEP under the IRL Council now 11 years ago, we understood that there was a link between the science we do, how that science translates into resource management, stewardship, but that you can't neglect or ignore the human condition, the political condition, and most importantly, the economic condition. None of us can do our work unless we have funding. And that funding is very difficult to obtain, although the last 10 years has been a bright spot. But even in the last 2 days, as I walked through some House and Senate offices and had conversations, I heard this. Well, you're just a bunch of environmentalists. You know, why should we put so much money into the Indian River Lagoon? So I'm going to give you some ammunition to answer that question this morning. Where does innovation start? Starts with each one of you individually thinking about a problem that doesn't have a good solution, and then moving through those solutions to answer those questions. And when you think about innovation and technology, and I heard this a couple times up in Tallahassee, we want to see you as scientists do it quicker, cheaper, better. I hear that for 20 years. It should be just the opposite. We want to do it better and quicker. Cheaper shouldn't be part of the equation, because cheaper means we're only thinking about cost and not benefit. Our management conference is now a collaborative governance structure, and I just passed that slide, of over 100 scientists, resource managers, citizens from all 5 counties with a diverse set of background. And what makes me most proud and also very happy is after 10 years, almost all those volunteers are participating at these quarterly meetings. They are functioning as a collaborative governance structure, and I thought it was going to be harder to keep everybody together, but we as a community are committed to a healthier Indian River Lagoon. And we as a National Estuary Program have put money into that innovation and technology and science side. And you can see over the last 10 years, 56 projects have been funded, over $3.9 million in investment. But when you look at our 10-year delivery system, water quality, habitat restoration, 267 projects, almost $30 million. And a lot of that money is being cobbled together from multiple sources. But we are making a difference, even though each one of those projects in itself may not be transformational. We did the first, I'm going to say, because there's no evidence against my statement, the first hack the Indian River Lagoon in the nation where we actually team with the Economic Development Commission of the Space Coast, Groundswell Startups, which is an incubator in Melbourne, funded literally by high-tech folks who felt we needed an incubator. That was in 2018. You know, it was a while ago. We had 52 students. There were technology experts, a few entrepreneurs, 16 teams, 36 hours of coding and building. And I want to tell you a really quick story because I'm going to try to squeeze this into my 10 minutes and not go over. The winning team actually had a water quality system at the end of the dock that was Bluetoothed, under $1,000, had basically a businessman said, I want to buy 6 of those. And the students went, we're not doing this to do business. They could have commercialized that, and they had an investor at the table willing to put 8 or 9 of those units on a property. And so to get from the good idea to where you're using eDNA or machine learning, somebody has got to move that idea to product for us to be able to use it. And that sequence, 1 minute? All right, I'm going really fast now. We have tested technology for communicating harmful algal blooms. We've invested in infrastructure that's supporting 5 different seagrass nurseries. And the outplanting is the most important part. It's the science and research that's being done. That was a grant through the Infrastructure Investment and Jobs Act. We have a $9.4 million NOAA habitat restoration project, and you talk about bright systems. This is the workforce that this is funding. We've got 5 federal agencies, 2 state agencies, rolled down to 16 industry consultants. And we have quantified economically the value of the system. This is newly released in November, but the economic output of the Indian River Lagoon is $28.3 billion. Roll over to the number of jobs. All right, Chuck's giving me the red line. And we've taken that down to site-by-site analysis, and I just want to mention 2. You're going to hear later from Ron about marsh restoration. Look at the benefit-cost ratio of that work. We have, how many people are doing clams from drones? We've got a few. Well, you know, if it's cheaper to deliver the restoration, the benefit-cost ratio goes up. So Chuck, I'm going to do the flyby and I'll be around. Mobile Bay's using sentinel dogs to detect nutrient pollution in systems. We've got a tiny little entrepreneurial shop in Melbourne that's doing drones, doing sensors, all fabricated basically in a garage, an industrial strip garage. And I promised I would tell Jim and Colin, we have a new Office of the Ocean Economy. And those of you who never imagined that you're part of that ocean and coastal economy, and you can find this online, this is how they're defining it. And what I would argue is that we need to expand this living resource part so it's not so generalized. And I'll end with this. There are places for you to go to get help if you're going to commercialize a technology. There are major centers being developed where you can get to instrumentation, like the Vertex Lab in Palm Bay. There is new development coming that is going to be a new center for all of us to work, play, and do work. And the big challenge, besides Lake Okeechobee and Everglades, is going to be the massive expansion of space and aerospace at Kennedy Space Center. It's also an opportunity to take ocean technology and what we do in the marine world and find a nexus between those 2 industries.
Thank you, Dwayne.
And don't forget, field work matters, you know.
Sorry, Chuck.
All right. Okay, next up, we have Madison, and she's a student presentation, and it's going to be about atmospheric deposition of microplastics.
Good morning, everyone. My name is Madison Strati. I'm a first-year master's student at the University of Central Florida, and I'm going to be telling you a little bit about a microplastic project that I've been working on. So I'm sure you've all been hearing a lot about microplastics in the news recently, with a lot of focus being about where we're finding microplastics. We have headlines about microplastics being found in our food and in our drinking water, even microplastics being found at the top of Mount Everest. But what normally is lacking from a lot of these headlines is how these microplastics are spreading so vastly. So first, to take a step back and define what a microplastic is, microplastics are plastic particles that are less than 5 millimeters in size, and they were either created to be this small or have been broken down from larger plastics. And a lot of previous research on their dispersal has been focused on things like wastewater runoff and stormwater as a method for their transportation, but recently there has been a look at atmospheric deposition. And atmospheric deposition is the transportation of pollutants like microplastics through the atmosphere via things like wind and rain. And a lot of previous microplastic atmospheric deposition research has already established that it is in fact transporting microplastics, but also rain tends to contain more microplastics than wind samples, and furthermore, population of a study area tends to be a big factor in determining how many microplastics are actually being transported in that area. And not only does atmospheric deposition allow for a new vector for transportation, but it also gives us another avenue for bioaccumulation through inhalation, which has already been linked to adverse health effects. And with the environmental and health risks associated with microplastic pollution, it's imperative that we continue to have these, continue to research how these microplastics are being dispersed and transported so widely. So for our study, we focused on the northernmost basin of the Indian River Lagoon, Mosquito Lagoon. And in 2021, the Indian River Lagoon was identified as a microplastic hotspot with a mean of 1.5 microplastics per liter of lagoon water. And this study also estimates that there's about 1.4 trillion microplastics lagoon-wide within the water, but they were unable to identify a source that could be contributing the amount of microplastics necessary to get to this number of microplastics in the water, which led us to our research question as to how much microplastic pollution does atmospheric deposition account for in the Indian River Lagoon. To do this, to study this, we had 3 different site types that we sampled from across 14 months. We had our CANA sites, which were Canaveral National Seashore parking lots and shorelines adjacent to the lagoon. We had our oyster reef sites, which were intertidal oyster reefs accessed at low tide via a boat, and our residential sites, which were actually collected by partnering with citizen scientists who collected these samples in areas like their homes, schools, places of work, and local parks. At these sites, we used passive atmospheric deposition collection devices, which is a fancy way of saying we used glass mason jars to collect microplastics. We left these glass mason jars open at our sites for around 3 hours before we sealed them, marked them as rained or wind accordingly, and brought them back to the lab. In order to trap the microplastics, there's about 10 millimeters of filtered deionized water at the bottom of the jar, which just ensured that anything that settled in the jar would stay trapped in the jar for those 3 hours before being sealed. In the lab, to process them, we would filter them using a vacuum pump filtration system where we added more of that filtered deionized water to the jars, shook them, and then filtered that water through the system. We did that 3 different times, or 3 times total for each jar. And once the microplastics had been filtered, we examined anything under a microscope. During this time, we had blanks set around the lab to account for any aerial contamination that could potentially be contributing to our samples. While under the microscope, we looked at potential microplastics. We looked at their morphology, things like fiber, film, fragment. You can see some examples here of some microplastics we found, as well as their color and length. And a subset of our samples were also set aside for FTIR, which is a form of infrared spectroscopy that determines the material composition of the microplastic. So here you can see what an FTIR spectra output would look like. This one, for example, is nylon. And overall, over the course of our project, we collected 1,401 jars, 74% of which actually did contain microplastics, which came out to a total of 6,853 microplastics total that we found. The top morphology for our microplastics was fiber, and the top color was clear. You can see an example of a bundle of fibers that we found in one of our residential jar sets here, and fiber being the top morphology and color being the top clear being the top color was something we were expecting based on previous literature. As far as what we were finding in our jars material-wise, our FTIR results showed that about 60% of our tested particles were a match for materials that are commonly used in the textile industry, things like polyester and nylon. Not only can these things make their way into the atmosphere during production of textiles and clothes, But they can also make their way into waterways when we're washing our clothes. So every time you wash your clothes, microparticles are shed into the water, makes its way into the waterway, and once it's participating in the water cycle, it has the opportunity to be transported in the atmosphere. To look at our overall deposition, here we have the density of our microplastics per meter squared per minute, split up between our rain and wind samples, as well as across our site types. And while we initially hypothesized that we would have significantly more microplastics in our residential sites, especially once we started processing these jars, and we had some residential samples that would have over 100 microplastics in one jar, these samples actually ended up being outliers, and we had no statistical significant differences between our sample types, our site types. This could be due for a number of reasons, and it really just shows that despite the characteristic differences between these site types, you have someone's backyard compared to an oyster reef, you would think there would be more microplastics in someone's backyard. That there is just, because of how these sites are clustered around the Mosquito Lagoon, they are all around the same area, there's an even distribution happening here. We did, however, like we expected in many other studies, find more microplastics in our rain samples. We also had more microplastics overall in the wet season. And so this is just the overall breakdown between our sample and site type, but what does this look like overall? So our overall daily deposition rate for Mosquito Lagoon was 1,224 microplastics per meter squared per day. And to provide some context for how high this number is, we have one of the highest reported atmospheric deposition rates. And to provide even more context, here are some other studies. This one out of Germany, which had 212 microplastics per meter squared per day, one out of London with 771. Shanghai actually did report a higher number than us at just over 3,000 microplastics per meter squared per day. But something you're probably thinking is, these are major cities. And if you remember what I said earlier, population can be a big contributing factor into how many microplastics are in atmospheric deposition samples. So if you're looking at these major cities and you're thinking, okay, Mosquito Lagoon, that's not really in a major metropolitan area. And if we looked at the study area population, for us, it's only 60,000 residents. So we're not really following that trend we would expect to see. Based on our population, if we're just looking at that, you would expect we would have way less microplastics, even less than in Germany and Hamburg. But based on our microplastic deposition rate, we should be falling in between London and Shanghai with our residents, which of course we do not. But something that's important to take into consideration for this area is tourism. So in this area, we had 10.6 million visitors in 2022. And now our numbers start to make a little bit more sense. You see, we do have a lot of people coming into this area, and it's not just those 60,000 residents. And our numbers start to make a little bit more sense, and we fall in between that London and Shanghai number, both with our deposition rates as well as our population. And I think this just really drives home the fact that we need to continue having these atmospheric deposition studies, not only worldwide, but in diverse areas, so we can really tease apart the trends that are happening and show that it's not just these major cities that are being impacted by microplastic pollution. And now I want to bring you back to a point I made earlier about the Indian River Lagoon being a microplastic hotspot. So in 2021, the lagoon, they estimated that there's 1.1 trillion microplastics lagoon-wide within the water, and we wanted to know if atmospheric deposition was important to coming up with this large amount of microplastics. And the answer that we found was yes. So we estimate, if you take our Northern IRL Mosquito Lagoon number, that 1,200 number, and extrapolate that out for the entire Indian River Lagoon, that's 1.1 trillion microplastics settling over the lagoon a day, which is a very scary number. And to make the number even scarier, if you take that number and you multiply it by our average microplastic length that we have and convert that into miles, it's enough miles of microplastics to go to the moon and back 1.5 times, which is even scarier. And with that, I would like to apologize for scaring you, and I would like to thank you all for listening to me, all of our collaborators and funders who made this research possible. And if there's time for questions, I'll take any questions. And this is a paper that we recently published that's associated with the study. Thank you.
Okay, we're going to keep going. Thank you. And next up, Gianna Price, coming from somewhere, we hope. Ah, here we go. All right. Another student presentation. So deep learning models for predicting chlorophyll A and dissolved oxygen variability.
All right. Good morning, everyone. My name is Gianna Price, and I recently completed my master's at Bethune-Cookman University. And today I will be talking about my thesis titled Evaluating Deep Learning for Predicting Chlorophyll A and Dissolved Oxygen Variability in the IRL. So most of us already know about harmful algal blooms, or HABs, and how the IRL has experienced many HAB events over the years, of course, including the 2011 super bloom, which had detrimental impacts on the lagoon. Despite technological advances, current monitoring approaches are primarily reactive rather than predictive. So this study evaluated the feasibility using deep learning models to forecast short-term variability in key water quality parameters in the IRL. So our overall goal was to predict chlorophyll A and dissolved oxygen levels in the IRL using deep learning. We compared 4 different types of models of increasing complexity to see which could better handle the ecological dynamics in the IRL. And then we also tested whether one or multiple variables would help improve model performance. So our study had 2 phases. In phase 1, we compared 2 linear models and then 2 deep learning models to evaluate their ability to forecast dissolved oxygen over just a 24-hour horizon. And then in phase 2, we extended this framework by applying the top performing model to forecast both dissolved oxygen and chlorophyll A over a 48-hour horizon. So for our methods, this study, we used chlorophyll A as an indicator of algal biomass, and then we also have dissolved oxygen, because as we know, low levels can be an indicator of bloom-related hypoxic conditions. So the data were collected from the Orca Kilroy network, which provided high-resolution samples that were collected every 30 minutes. And for this study, we used 1 full year of data from January to December 2024. For the 24-hour forecast, the model only used dissolved oxygen data. And then for the 48-hour models, we incorporated multiple environmental variables to predict either DO or chlorophyll A. So for this study, we focused on the Banana River Basin due to its shallow and highly restricted conditions. And the data was from the Cars Park Station, which is located in the center of the basin. So first, I'm going to briefly talk about phase 1. Again, we evaluated 4 models. We began with the linear recursive models, and recursive meaning that the output was fed back into the model as the input for the next forecast. And then we tested deep learning architectures, including a recursive DNN and a multi-output framework. And this just means that all the outputs were generated at the same time. And this is important because those recursive models can accumulate errors over time because those errors are fed back into one another. So we were hoping that the multi-output framework would prevent that. So for all of them, the models were optimized and trained to reduce errors, and then they were evaluated using mean absolute error, root mean square error, and mean absolute percentage error. And due to time constraints, I can't go into full detail about phase 1, but the complete study is available in my very first publication, thanks to my advisors. So you guys can scan or take a picture if you want. But to summarize phase 1, the DNN multi-output did perform the best. So yeah, its predicted values followed the true values the closest compared to the other models, and it also had the lowest, most stable errors. So now for phase 2. Again, we continued our analysis. We implemented predictive uncertainty estimation and also assessed model performance across seasonal periods because, as we know, dissolved oxygen and chlorophyll A are heavily influenced by seasonality, and we wanted to see if our models were capable of picking those up. So overall, the models captured the temporal trends and short-term variability. In both models, the single and multivariable models performed well regardless of the input quantity. As you can see, they both followed the true values pretty well. And then same thing goes for the chlorophyll A models. Both of them captured the overall trends and the variability, and the predicted values followed the true values pretty well. But looking closer at the errors, this table just tells us that the errors increased with longer forecast horizon, and this is expected. Except for the 30-minute horizon, the errors increased when predicting further into the future. This table also tells us that the multivariable model had lower errors than the single variable model, but the differences weren't that large. With chlorophyll A, however, it was a little bit different. The trends weren't as obvious, and more variables did not improve model performance. But again, the differences were still relatively small. We also evaluated predictive uncertainty by calculating the 95% confidence intervals for each forecast. These bars represent the confidence interval widths, with the multivariable model being green and the single variable model being yellow. So as you can see, the multivariable model was consistently more confident, but if you look closer at the scale, you can see that the differences weren't that large. For the chlorophyll A models, the confidence was pretty similar across all the forecast horizons. So next, we have our mixed effects analysis, which allowed us to assess seasonal performance while accounting for the temporal dependence within the data. Our results showed that the models did effectively capture seasonal dissolved oxygen variability, and also that the single and multivariable models performed similarly, indicating limited benefit from additional predictors. And then the same thing for the chlorophyll A analysis. And then we also used an autocorrelation function to determine whether any temporal structure remained in the residuals. So if the residuals resembled white noise, then that means our model did pick up those seasonal patterns, whereas if they showed like a consistent pattern, then it didn't. But these were our results, meaning that they did resemble white noise, suggesting both the single and multivariable models successfully captured those temporal and seasonal trends. And then again, same for chlorophyll A. Yeah, that was a lot of information, and I tried to condense my hour-long thesis defense into like 8 minutes, so that was a struggle for me. But the key takeaway, our deep learning models were able to accurately reproduce short-term dissolved oxygen and chlorophyll A dynamics using ORCA data, and those models were capable of capturing those seasonal trends. Including additional predictors marginally improved the dissolved oxygen predictions, but they didn't really help for the chlorophyll A model. But yeah, overall, these results show that using deep learning has potential within the Indian River Lagoon in predicting bloom conditions and hypoxic conditions. And again, I wish I could go more in depth, but obviously I don't have the time. But yeah, before I stop, I want to thank my advisors, Dr. Krejci and Dr. Calderon, Bethune-Cookman and Title III for funding, ORCA for providing the data, and of course my lab mates and my team at Cookman for all their support and encouragement. And thank you guys for listening. If I have time for questions, then I'd be happy to answer.
We'll have sure Ms. Press will be around today, so we'll save the questions. Try to get back on track here. Next up, another student presentation. Ahmed. Hey. We'll be talking about using autoholo to characterize cyanobacterial blooms.
Good morning. Thank you, everyone. My name is Ahmed Abdullah, PhD students from Dr. Nayak Labs. Today, I'm going to talk about in situ digital holographic imaging system to characterize cyanobacterial bloom in freshwater and estuarine environment. So harmful algal blooms or HABs are rapid algal growth events that actually can produce the toxin and negatively impact on aquatic ecosystems. The major category of HABs in freshwater systems is cyanobacterial bloom, often actually referred to as cyanohab. The collage you are seeing the right side, those are the common bloom-forming cyanobacteria from freshwater systems, including the Aphanizomenon, Dolichospermum, Plankton, and Microplastics. So monitoring of these bloom-forming communities is essential for effective management and early warning efforts. So here you see the major approaches currently which are using to study the harmful algal blooms. So firstly, the remote sensing provides large spatial coverage, but it has limitation by cloud cover and mainly detects the surface condition. The conventional microscopy is widely usable, but it's labor intensive, the time consuming, and limited in processing efficiency, which makes it difficult for large scale monitoring. So, and the other system, the image-based systems such as IFCB, which can capture detailed plankton images, but the sample actually relatively small volume and may break the colonies while drawing the sample from the natural environment because it's a flow-through system. So, in this slide actually introduces the fundamental principle of behind our imaging approach, which is called holography. So the digital holography basically captured the 3D volumetric information in situ across the wide range without altering the sample. That's why it's called the free stream approach. And overall, every method actually has strength and limitations, and digital holography offers a complementary approach that actually addresses the several challenges associated with the traditional techniques. So in the diagram at the top right position you see, which actually illustrates the holography method, where a coherent laser beam actually passes through the sample and the scattered light actually interferes with the reference wave, and this reference pattern is recorded by the digital sensor, or the camera, and later it reconstructed computationally to retrieve the particle information. And here you see the bottom images, which is the top view of our underwater imaging system, which is called AutoHolo. The system basically consists two sides, like the laser side and the camera side. And the system basically combines adjustable sample length with flexible optical configuration to resolve the particle from microns to centimeter scale. Here I'm going to talk about the geographic context of our study locations. If you look at the upper panel, it shows the Lake Okeechobee, the largest freshwater lake in Florida, and it connects the Indian River Lagoon through the St. Lucie Canal, where the freshwater discharges can transport a nutrient downstream and impact the lagoon water quality. It's shallow depth, and one condition makes it susceptible to recurrent the cyanobacterial bloom. The lower panel actually shows the Lake Erie, particularly the western basin, which is also relatively shallow and highly productive. This region also frequently experiences with cyanobacterial bloom, especially dominated by microcystis. The image collage, which is highlighted differences in plankton diversity, colony morphology, aggregation pattern between the two lakes. I would like to mention that I'm showing some results from Lake Erie to demonstrate the interlake comparison, and also this is my main PhD study area. In the previous slide, actually I presented the plankton community collage of both lakes. Here we are shifting our focus to the overall particle size distribution observed in each lake. we sampled actually across different location and different season in both lakes, but here I'm just showing one example of the particle size distribution to show the variation between the lake. Here we observed the clear contrast, how particles are distributed across the size range. You see, if you look at the Lake Okeechobee, which shows the stronger contribution from the larger aggregates. On the other hand, the Lake Erie actually exhibits the sharper decline in abundance and particle size. And in the plot, I have shown the slope value and the mean size. The holographic images also reinforce this pattern, like in Lake Erie, in Lake Okeechobee, we observed the denser and the more cohesive cluster, whereas the Lake Erie particle appears more dispersed and the less aggregate. So in this slide actually focuses on the cyanobacterial genus Microcystis, highlighting its vertical abundance pattern and the colony size distribution in the water column based on actually Lake Erie observation. I used machine learning approach to train the CNN architecture to classify individual species from Lake Erie to get the particle abundance and the size distribution. Actually, if you look at the plot, like overall Microcystis shows the strong surface accumulation near shore with decreasing abundance and smaller colonies towards the offshore and the deeper stations. And this result basically highlighting that our imaging system's capability to assess the colony abundance and the size distribution without breaking the colonies in the natural environment, because at the beginning I said it's a free stream approach. So here you see our future plan, like we will analyze all our current data sets from both lakes to strengthen our inter-lake comparison of individual plankton abundance and size distribution. And we have more plan for the field deployments in diverse environment to evaluate and enhance the auto-holo performance. And another, the last one, we will expand our label data sets across freshwater and estuarine system, including the Indian River Lagoon, and deploy lightweight CNN architectures for real-time monitoring. And my colleagues, Madison Bennett, will present a short overview of this instrument during her 3 minutes segment. Thank you for listening.
Okay, we can take one question, if there is one. Okay, you're free to go, man.
Thank you.
All right, next up is another student presentation, Shoreline. There we go. It's going to talk about dealing with contaminants in water.
Hi, everybody. My name is Sharanya Natarajan. I'm really excited to be here. I'm a senior at Edgewood Junior Senior High School in Merritt Island, Florida. Thank you. Thank you. My research that I'm going to be talking to you about today is where I developed an integrated detection and delivery system to abate contaminants in water bodies. But before I get started, I wanted to thank Miss Melissa and Miss Hall from St. John's for putting up with me for the last 6 years, because this is a 6-year evolution. I started in 6th grade, and I'm a senior now. Thank you. Okay, so starting with the problem, eutrophication, as we all know, is the main issue. It's costed about 7,000 acres of seagrass to have lost in the Indian River Lagoon. And thankfully, the good news is that it's slowly recovering, but this has also costed billions of dollars for the nation to address. The current work right now, our current data collection is great, but of course there's always room for improvement by integrating intelligent monitoring coupled with a sustainable remediation. Which brings to the goal of my research, to sequester nutrients using an engineered detection and delivery system, all integrated onto a surface water vehicle for real-time management of aquatic environments. So let me unpack my research for you, starting off with sequestration, where I was looking for agents that are sustainable to absorb nutrients from water bodies. I started by selecting 4 different agents: zeolite, biosorption, activated media, activated carbon, and coir. And I looked at the agent properties and down-selected zeolites for its natural and sustainable properties. Then I did benchtop wet chemistry analysis, where I tested the 4 agents using a Hanna colorimeter, and thank you to Orca for lending me that. And I was able to down-select zeolites because it had the highest nitrate absorption efficiency. But I wanted to increase the efficiency of the absorption, so I surface modified the zeolite. Essentially, I took the zeolite and I treated it with a 0.1 molar sodium chloride solution for 8 hours. And what happens is, if you look at the middle picture, the sodium ions absorb onto the zeolite pores. And then when this is exposed to the nitrate solution, the nitrate ions displace the sodium ions at the surface of the water, thereby sequestering or getting absorbed by the zeolites. Now, I wanted a visual confirmation of this process, so I used a scanning electron microscope at Embry-Riddle, and I was able to look at the 3 different stages of the process. So on the left, you see the plain zeolite with the active pores. Then when this is surface modified, the sodium crystals, which are like the little white crystals in the middle, those get absorbed and they bind to the zeolite pores. And then finally, on the right side, that's when the sequestration occurs, where the nitrates, the little flowery things, when they displace the sodium crystals. And that's the sequestration process. I tested this in the lab. I did static tests. And overall, I noticed that the surface modified zeolites exhibited the highest nitrate removal efficiency at 23% on the left. Then I wanted to go from static to continuous monitoring, so I used an ORP sensor, which is oxidation reduction potential, and I used this as a proxy to measure the nitrates. A high ORP is an oxidizing environment, which means that there's higher electron activity and high nitrate concentrations in the water column. And low ORP is the converse of. Now, testing this, getting some results on this. So overall, the ORP declined in the presence of the surface-modified zeolites, which indicated that there was a 23% more nitrate sequestration in the water column, as you can see on the graph. Now for phase 2, detection. I wanted to look for sensors that could detect the water quality in real time. So to do this, I started with a 5-sensor selection. My 5 sensors was ORP, photointensity, salinity, TDS, and DO2. I connected all of these sensors together onto a wireless microcontroller. I hand soldered everything onto a printed circuit board and programmed it to transmit real-time data to a dashboard, which I'll get into later. I tested this in a nutrient-enriched environment, and I got continuous data monitoring on the right side. And after my lab testing, I noticed that there was a 63% more clear waters after the SMZ treatment, as you can see in the graph. And essentially, this just shows that the surface-modified zeolites were able to inhibit or prevent the growth of algae in the water column. Now, to make this more field-worthy, I created a CAD design on the left to house all the circuits into one full detection system. So on the left is a 3D model of the detection system, which I 3D printed on the left at my school, and I housed all the circuitry into that one detection box. And on the bottom, you can see the PCB prototyping board, which also was housed into the full detection system on the right. Now, phase 3 is delivery, where I am essentially taking that sequestration agent, the zeolites, and I'm making it automated. So if you, on the dashboard, if you can operate it remotely, and you can press a button, and it'll automatically disperse the zeolites into the water to absorb the nutrients and prevent algal blooms. I started with another 3D model. I 3D printed that, and the final design has a funnel-like cross-section, and that's for a gravity-assisted discharge of the zeolites into the water to absorb the algae, the nitrates. And then all of this is controlled by a servo pulley gate mechanism on the top right. My final phase is integration, where I combined all of these components into one modular system, and that is this. So this is my swath. I combined the detection and delivery modules onto the the device on the left. This is, I 3D printed the swath on the bottom, and that's like a twin hull design. I have 4 thrusters which can be remotely operated from the cloud. And the final design on the right is a 100% fabricated, modular, extensible. The hardware is scalable, and the software connects to the cloud. I tested this at FIT at their ocean engineering lab, and so that's on the left. And then I did testing at my neighbor's pool, and then finally did I run out of time? Oh, okay, we're good. Thank you. And then I did final testing at Lake Washington with Miss Melissa, actually. And here I was able to get real-time data transmission to the cloud. And all the data is stored here. So this is my bidirectional communication dashboard. I programmed this to take all the data and store it onto this dashboard. On the right over here, you can see all like the little widgets, which are the real-time data transmission. And then on the left right here, these are the controls, so you can operate my system from anywhere and anytime. I took all this data and I did a machine learning predictive analysis where I predicted the DO2, which is an indicator for algal growth, using the ORP, and I got a 92% accuracy on this model. Okay, now for implementation. So my research is a prototype level, of course, but I wanted to create a theoretical case study on how this could possibly be implemented. So if you look at the top 4 images, those are the 4 seasons of the year, starting off with low algal intensity at the beginning. Summertime, you have high algal intensity, and at the end, it kind of dies off. So how can my system be implemented in this model? Well, the first thing is denitrification walls, where you can implement this into the stormwater runoffs, where the zeolites will absorb the nitrates in the water before it enters large water bodies. The second way is denitrification pads, which can be installed at the source, which is the stormwater overflows. So as the water goes through the overflow, the nitrates will be collected, and then it enters the water body. But of course, if you need more, you have my solution, which can monitor water bodies remotely, sequester nitrates sustainably, and predict algal blooms. So ultimately, it's scalable and cost-effective, and recently, I just filed a provisional patent. So.
Nice job. Okay, between you and break is Jonathan. Hey. Let's talk about electrochemical profiling. Go, man.
All right. All right, good morning, everyone. Thank you all for coming out and supporting Lagoon Science here at the Symposium today. My name is Jonathan Terzato. I'm a master's student here in the Geochemistry and Geochemical Sensing Lab here at Harbor Branch. Today, I'd like to share some data from the Southern Indian River Lagoon, more specifically, the St. Lucie Estuary. So, first things first, I want to dive into the link between sediments and water quality. In the St. Lucie Estuary, many of the water quality issues we care about, like hypoxia, sulfite toxicity, nutrient regeneration, and even ocean acidification, are strongly influenced by what happens in sediments. Sediment redox structure controls benthic oxygen demand, sulfide production, and how nutrients and alkalinity move between sediments and the water column. So just to give you guys a little taste, microbes respire organic matter deposited in sediment. As oxygen is depleted, microbes switch to other terminal electron acceptors in a predictable redox sequence, as you can see on the diagenetic ladder on the slide. And sediments are structured this way as a result of microbes trying to get the most energy out of their respiratory processes. So, it's a little complicated, but I'll walk you through it. We've just seen the general redox ladder, but for estuarine sediments, the key coupling I want to focus on is iron and sulfide. Reactive iron oxides, essentially rust phases, are microbially reducible and also react rapidly with sulfide, producing reduced iron in sediments. When sulfide encounters reduced iron, it is captured as iron sulfide, seen right here. This is an aqueous intermediate, but together these reactions trap reduced sulfur and prevent it from accumulating near the sediment-water interface. Sorry about that. So this work primarily focuses on the St. Lucie estuary and the adjacent southern Indian River Lagoon. This is a freshwater to marine transition system characterized by strong salinity gradients and variable sediment input. These gradients influence sediment redox structure and buffering capacity. Specifically, freshwater delivery introduces particulate material, including reactive iron oxides. Geologically, these iron-rich sediments are common in most of the southeast US, and as freshwater inputs vary spatially, reactive iron availability may also vary. Sulfate is one of the major constituents of seawater. As salinity increases, sulfate availability increases. Across the St. Lucie estuary, these gradients intersect, potentially altering the redox structure of sediments in the estuary. So, we sampled across this gradient. We started at SF2, which is the Erlon station closest to the lock on the C-44 coming out of the St. Lucie Canal. We also sampled at SF, which represents mid-estuary conditions and is located near the Erlon Tower in the South Fork. And we sampled at Walton Scrub Preserve, which represents our marine lagoon sediments. Sampling occurred during 4 campaigns between November 2024 and October 2025. Intact sediment cores were collected and immediately profiled upon return to the lab to preserve in situ redox structure. After profiling, cores were sectioned for reactive iron extraction using the citrate bicarbonate dithionite method, which is a colorimetric assay, while solid phase elemental concentrations were determined by flash combustion on an elemental analyzer. Using this combination allows us to connect high-resolution redox profiles and emerging technology with traditional bulk geochemical measurements. We used mercury gold solid-state microelectrodes to voltammetrically detect the following redox active species. That's oxygen, iron 2, organically chelated iron 3, hydrogen sulfides, and aqueous iron sulfide. This gives us sub-millimeter spatial resolution. As you can see here, we're getting about the first 20 millimeters of the overlying water and about 100 to 200 millimeters down in the core. These electrodes are fabricated in-house, and generating even a few of these high-quality profiles takes significant priming, conditioning, and preparation before we can sample. So, electrochemical data can be a lot to process at once. Let me walk you through it. So we'll start with oxygen. So as you guys can see, oxygen, we lose oxygen within the first couple millimeters of the core. This is due to intense respiration in surface sediments, which is why microbes in deeper layers will turn to alternative terminal electron acceptors. So, adding on, you guys now see iron 2 and organically chelated iron 3. So, with metal reduction, metals are coming from terrestrial material deposited in the upper estuary. Organically chelated iron 3 is an important indicator for microbial iron reduction, showing the presence of iron cycling at site SF2. So let's bring in the real star, sulfide. Sulfide does not accumulate until deeper in the core. This means iron is effectively intercepting reduced sulfur, buffering sulfide buildup. The limited presence of aqueous iron sulfide shows the greater influence of iron reduction than sulfate reduction at this site. Now we move on to the South Fork Erlon Tower, which is a little bit more marine in the middle estuary. Here we can see the classic iron-sulfur transition structure. So where I've circled on the plot, you guys can see that sulfide is increasing as iron 2 is decreasing, and we start to see the formation of iron-sulfur just below 80 millimeters into the core. This is an active precipitation process. Once iron is exhausted, sulfate reduction takes over, as you see. This is important because this is a system where buffering is existing, but it's limited. If iron supply were to decrease here, sulfide would creep upward. And then we look at Scrub, which is our marine site, and you can see the weaker iron 2 signal, limited reactive iron buffering, and iron here is quickly, if there is any iron present, it's quickly converted to iron sulfide. But be wary of our units here. These units are semi-quantitative. We report these units in nanoamps because we are measuring iron sulfide nanoparticles or colloids. It's a little hard to quantitatively calibrate for that. So it looks like it is in greater abundance than sulfide, but in reality, it's more just evidence of decycling and buffering occurring. So sulfide onset depth declines with increasing marine influence. When we compare the three sites, sulfide onset depth decreased with increasing salinity. So sulfide onset depth is a proxy for buffering strength. The deeper the sulfide appears, the stronger the iron buffer. The marine influence at scrub is visible in its shallow sulfidic layer. It's only 3.5 millimeters deep, while the interplay of marine and terrestrial forces is seen in the South Fork core's intermediate sulfidization depth. All right. So these are traditional geochemical measurements. So here we used our reactive iron extractions to show profiles of sediments throughout our study area. And you guys can see that concentrations of reactive iron differ substantially between estuarine and lagoon sediments. It's highest in the upper estuary, lower towards the IRL. And just bringing this together, we see clear spatial variability in sediment redox structure across relatively short distances. In the freshwater South Fork site, iron buffering capacity is higher and sulfide onset occurs deeper. At the mid-estuary site, we observe a transitional iron-sulfur boundary. And in the marine lagoon site, reactive iron availability is lower and sulfide is present throughout much of the core. These spatial differences suggest that sediment buffering capacity varies across the system. In a system with fluctuating freshwater delivery, this structure is likely shifting over time as well. And so key takeaways, first things first, as you can see by the picture of the boat, it's a very dirty job, but someone has got to do it. In the South Fork, where reactive iron is more abundant, sulfide accumulation is delayed and structured, indicating greater buffering capacity. In the adjacent lagoon sediments, buffering capacity is lower and sulfide is present throughout much of the sediment layers. And bulk extractions alone cannot resolve these active redox boundaries. This is why we use techniques like high-resolution voltammetry to reveal the structure of these transitions directly. Because sediment redox structure influences oxygen demand, sulfide exposure and nutrient cycling, spatial variability in this buffering capacity may contribute to broader water quality differences across the system. Finally, these high-resolution electrochemical tools can be deployed in situ. This offers a way to monitor these dynamics at greater temporal resolution, especially with things like harmful freshwater releases or harmful algae blooms. Ultimately, if we want to understand and manage water quality in this system, we have to understand the sediments, and iron is central to that story. And with that, I'd like to thank the Indian River Lagoon Graduate Research Fellowship for funding this work, also the School of Environmental, Coastal, and Ocean Sustainability, my advisor, Dr. Jordan Beckler, Analytical Instrument Systems for providing the instrumentation, the Geochemistry Lab, shout out you guys, and obviously HBOI Marina. Without them, I wouldn't be able to collect any of my samples. So with that, thank you.
All right. It looks like 10 minutes eliminates all the questions. But okay, you're on break till 10:30 and be back on time because you don't want to mess with Lorraine.
In the crowd then that would like to take on some student judging for us? Takers? I do. Oh, thank you. I see one hand. Hi, good morning. Will you pass that down here? Do I have one more taker to help us do student judging? Thank you. Taryn for the win. All right, everybody. Let's go ahead and kick off oral session number 2, and this is Sensors and Remote Technology. I would like to invite Megan Conklin up, and she's going to be talking about acidification in the Indian River Lagoon, the drivers of such.
All right, I hope everyone had a nice break and got to talk to their friends and colleagues. Like I was introduced, I'm going to talk about coastal acidification drivers in the Indian River Lagoon. All right, and as we all know, the Indian River Lagoon and estuaries across Florida are ecologically, economically and intrinsically important systems for the state of Florida. And unfortunately, the Indian River Lagoon has experienced severe degradation due to increasing urbanization in the areas. And unfortunately, because of this, we're seeing more wastewater entering the water systems, more stormwater runoff and nutrient pollution entering these waters, which we know can influence coastal acidification in waterways. But this has not been actually looked at in the Indian River Lagoon. So just to recap, coastal acidification is when we see a drop in pH in the coastal waters, and this can be from atmospheric CO2 in the area, but also through precipitation and freshwater influence, as well as nutrients coming in from watersheds nearby. And unfortunately, because of this, a lot of animals such as shellfish and crustaceans can be negatively impacted because their skeletons and shells can then break down, and that can reduce their growth, survival in these areas. But scientists have found that coastal acidification is correlated with aragonite saturation state and calcification of these marine organisms. So we're able to look at aragonite saturation state in these waterways in order to better understand the decline of these crustaceans and shellfish in these water systems. So in 2016, 2017, some scientists visited all 20 of these red dots on this map and collected samples, water samples, to look at coastal acidification and DIC, dissolved inorganic carbon, total alkalinity, as well as environmental parameters and nutrient parameters. And what we found was that aragonite saturation state significantly was lower in the dry season of 2016. As you can see, it's significantly lower than the dashed line, which indicates kind of the health threshold for a lot of these crustaceans and shellfish in the waterways. So above 3, we have happy waters, we have growth and reproduction for these organisms. Below 3, these organisms become compromised. Their growth just starts to deteriorate, but below 1 is when they actually start to dissolve. So as we can see in 2016, we saw a significant drop in the aragonite saturation state to the point that a lot of these organisms were being broken down potentially. And the threshold was rarely met in the other 2 seasons that were monitored, in the wet season of 2016 and the dry season of 2017. So to look at this and explain kind of what's going on, especially in the dry season of 2016, early on in the year of 2016, there was a brown tide event up in the northern IRL, meaning the Mosquito Lagoon, Banana River, and northern region. And with this, we see an increase in the photosynthesis occurring. And because of this, we're going to see a drop in the dissolved inorganic carbon. But afterwards, after we started doing the sampling, we saw a cellular respiration increase, which is because of the breakdown of these HAB events and the increasing decomposition by the microorganisms in the water. And with that, we also are going to see an increase in the dissolved inorganic carbon, which we see in the graph below, with the light blue bars here showing a significant increase for the Mosquito Lagoon, Banana River, and the Northern Iowa region. So this then causes that drop in aragonite saturation state. But we also saw that in the central and southern, we saw very low levels as well. And we're not seeing that dissolved inorganic carbon increase like we do in the northern regions. And this is likely due to an increase in rainfall in the season because of an El Nino event that occurred in 2016 across Florida. And the graph on the left is showing precipitation and discharge in the northern, southern, and central IRL, and the lines indicate the different discharge locations, and the dots indicate the month sum of the rainfall occurred. And we see that at the beginning, before monitoring, we see a huge influx of discharge in the southern IRL, and with this, we're not seeing it in the data because our data was collected later on in the season, but we still see a significant increase of that discharge. And with that, obviously, freshwater influence into the system, we're seeing a drop in salinity as well as a drop in the total alkalinity. And with the drop in total alkalinity, we then get the drop in aragonite saturation state. So unfortunately, as we all know, with the influence of freshwater influence, we also get increases in nutrients because of the runoff situation in the area. And from the graph on the right, we see that in the Banana River, after the brown tide event, we got an influx of rain, and then we also got a lot of nitrogen influence, which then spurred on a summer bloom event, which you can see in the orange shaded area in the map. And unfortunately, in the southern region and central region, specifically the St. Lucie estuary, we're seeing an increase in phosphorus levels, probably through discharges of the Lake O, and as well as a microcystis bloom that was introduced at the same time. So there's a lot going on, but ultimately it's the driving force of freshwater influence, nutrients, which is then also causing HAB events, but it's secretly also creating a coastal acidification issue in the region. So that's all the spatial data that we looked at, but we also did temporal analyses where we went to 3 different sites, these yellow dots here, in the central IRL, and looked at time period between June of 2016 to June 2017, and weekly monitoring was done in this area. The MRC site is the main relief canal for Vero Beach. SSR is the St. Sebastian River, mouth of the river right there, which gets some exchange with the Atlantic Ocean. And then we have a reference site at Sebastian Inlet, which gets a lot of exchange, not a lot of runoff influence. And the main relief canal in Vero obviously gets a lot of runoff from that city area, but not a lot of exchange with the Atlantic Ocean. And what we found was that locations significantly impacted the aragonite saturation levels. So the red lines are the main relief canal, and that did not meet the threshold at all during the monitoring period of 3. So this was a significantly low area for these shellfish and crustaceans. They're in a state of constant stress in this region, and we're seeing a slightly improved levels at the St. Sebastian River, and at the reference site, we're seeing it almost consistently above the threshold of 3. So this is informing us that the water exchange is really important in the influence and impact of coastal acidification in this area. And like I said previously, precipitation, rainfall, discharges into the area are a huge influence, and we did see a significantly higher levels of rainfall in the area, and this was also seen in our data with salinity at the main relief canal as well as the St. Sebastian River. We saw a huge drop in salinity in this region, and this is, we saw a positive correlation with aragonite saturation state. So with decreasing salinity, we're seeing a decrease in that aragonite saturation state. And for the reference site, because it had high water exchange, it stayed relatively consistent. And at these sites, we also looked at nutrient levels, and as you can see with the red lines for each of the nitrogen levels, they were significantly higher at the main relief canals in Vero Beach, and this is due to the runoff because of the city of Vero Beach in this area, unfortunately. And we also see the spike in phosphorus for St. Sebastian River, which is likely due to some of the agricultural runoff that's occurring in that area. But for each of these, we saw a significant negative correlation with aragonite saturation state. So with increasing nutrients, we're seeing that drop in aragonite saturation state, which is then negatively impacting these animals in the area. So to summarize all of this information, this was, to our knowledge, the first documentation of aragonite saturation state being monitored throughout the entirety of the IRL. We discovered significant and important correlations between aragonite saturation state and eutrophication and freshwater influence. And ultimately, we hope that this research is driving the importance of coastal acidification in the area, but also driving the importance of monitoring and understanding these systems, as well as working together and collaborating with the community, with policy, in order to develop effective mitigation methods and adaptation strategies in order to improve the IRL. So check out our recent publication this year, which kind of summarizes all of this work. And thank you to all the funding sources and for you guys for listening.
Thank you, Megan. No time for questions. Next up, we have Austin Fox, who is going to talk about hypoxia and nutrient cycling in the IRL.
First of all, I have 10 minutes. I'm going to breathe. So our story begins, the motivation behind this is a change in phosphorus concentrations over time. And so many of you are familiar with this, but pre-2010, our average phosphate concentration in IRL was about 50 micrograms per liter. Since then, it's increased by about 70% to somewhere around 85 micrograms per liter. And so can we start to explain this? I'd like to point out that this occurred with a simultaneous decrease in N-to-P ratio. Basically, that increased phosphorus is not necessarily accompanied by an increase in nitrogen. And so we did see some changes in nitrogen speciation, but it is really a phosphorus event. And so where did this extra phosphorus come from, right? So from a geochemical perspective, we can start to explain through some sedimentary process what might be occurring. And so I want to point out first, fluxes from muck are high, right? A lot of you know me for muck. Fluxes from muck are high. I'm talking today about sand that covers 90% of that lagoon bottom. And so these fluxes vary, right? What you'll notice here is there's a line at 0. Most sand is taking in phosphorus. It's helping to assimilate and remove that external loading. But what you'll notice is some of these sites actually are adding phosphorus. Can we explain where we're adding versus removing, right? And so this is a great graphic that Rebecca put together. It's basically showing that from a geochemical perspective, that iron that you've heard about, right, can actually bind to phosphorus and pull it from the water column into the sediments where it's sequestered. It's not bioavailable. When we have anoxic events or hypoxic events, the iron can become reduced by interactions with sulfur through iron-reducing bacteria, and this can actually release that phosphorus back into the water column. And so the analogy I like to use is it's like a sponge. The sediment's like a sponge soaking up phosphorus under aerobic conditions, or at least that's the hope. And then under anaerobic conditions, we're wringing out that sponge, putting back these giant pulses of phosphorus that can drive or even exacerbate some of these harmful algal blooms. And so we set out to monitor hypoxia, right? If we can measure the extent of hypoxia, we can actually start to calculate how much phosphorus is being put back in. And so first thing, we're measuring at the bottom. That's where this geochemistry is happening. And so if we look at mid-depth versus bottom water hypoxia, you're noticing that that 2 milligrams per liter threshold, which I'll reference, is being crossed a lot more times in that bottom water than it is at those mid-depths. And so we can look at vertical profiles to confirm this. There are a lot of places where that vertical water column for DO is pretty well mixed, but we also see a lot of places, especially in close proximity to muck, where we have those DO concentrations decreasing with depth. And so do we see this kind of geochemical process occurring within our lagoon sediments? And so this is just one site that we've tracked over time. And I'm zooming in on a little short period here where you see kind of that zero line, that zero phosphorus flux. Sometimes it's going in, sometimes it's going out. How can we explain that? So we throw up the dissolved oxygen, this green line here. And those really high positive phosphorus fluxes are occurring when we have hypoxic events occurring, right? And so we are validating that these geochemical processes are in fact occurring in our lagoon. If we look across sites, right, we can take our kind of average from across the entire lagoon, all of the study sites we've looked at, and you're seeing that there's normoxic conditions, the median phosphorus flux is approximately 0. Most of the time it's going in, sometimes it's coming out, and we believe that that's related to those transitional periods between those hypoxic and normoxic timeframes, where hypoxic it's virtually always, or virtually almost always, a positive phosphorus flux from sediments into overlying water. All of a sudden, hypoxia is really important. And so how do we quantify this? How do we look at this spatially and temporally? And so we build a hypoxia monitoring network. So we've been working with these Hobo U26 and MX800 data loggers. They're really great for this purpose. They're low cost. They're very accurate. They have some issues that we deal with, so fouling. Anybody working in the lagoon has fouling issues. But we actually are working with the manufacturer. We have at Florida Tech some proprietary anti-fouling techniques that are working incredibly well. And when you put things at the bottom in anoxic water, things don't like anoxic water. So that actually helped us out a little bit. But we have over 80 of these locations throughout Indian River and Banana River Lagoon trying to map the hypoxia. And so I want to throw in here, we're talking about technology. Quality control is of utmost importance, right? So we do chronological and quantitative calibration brackets every month during these maintenance visits. We also have secondary calibration verification at most of these sites, since we're lowering something like a YSI to check those values. I had 50 slides as of 9 p.m. last night. I had to cut some of those out to make it fit in 10 minutes. But anyways, that's our thing. So we start to put this together, and I could show you graphs of every hour from every day, but just to show you a couple, these are the averages for a couple of quarters, midsummer and October to December. And what you're noticing is that fairly significant portions of the lagoon are experiencing hypoxia 50% of the time or greater, right? And this is fascinating. When we look at those mid-depth water quality monitoring stations, we're not seeing this. It's when we start to look at the bottom, we see these massive areas of hypoxia. And we're calculating somewhere around 5 to 8% of the lagoon bottom is hypoxic at any given time. Times 400 square kilometers in the system, that's a huge area. So relatively small fluxes times massive areas are massively impactful. And so we're working on frequency analyses to look for where we're seeing diurnal versus episodic hypoxic events. This can allude to kind of those internal controls versus external controls. So things like the distribution of muck versus rainfall. And this is helping us to look at mechanisms that are driving this. And so from here, we can start to model things. And so in development, we're developing this assimilative internal flux model. And so if we look at TMDLs and BMAPs, they're based on how much phosphorus or how many nutrients can these systems assimilate, right? And so that's something we're trying to understand. So we're developing this assimilative internal flux model, which we're abbreviating as if. If you're old enough, you'll get that joke and the associated picture. So we're developing this as an ArcGIS tool that's going to basically be a hypoxia risk map. We can use this to calculate the areal and spatial extent of those phosphorus fluxes and get to a number for internal flux. I haven't included it here because it's too scary, but it is significant, right? We absolutely need to be considering this. It is on the scale of that should be considered when you compare internal to external loading, right? They may be somewhere close to equal. And so phosphorus fluxes may help to explain that change, right? If we're seeing a larger areal extent of hypoxia following those cold snaps in 2010, following the algae blooms after that, we can start to maybe explain some of those increased phosphorus concentrations. And so we're refining these estimates, right? The calculations that we're using in this model right now are based on those aerobic versus anaerobic fluxes. Something that we're wondering is what about those transitional periods? You saw kind of the large noise in those aerobic values in that first graph. And so something we're doing is we're using technology, right, to be able to better quantify benthic fluxes throughout the course of those hypoxic, normoxic transitions. And so we basically built some animated gas manifolds to control the redox environment, so we can have 1 hour of hypoxia, 2 hours of hypoxia, 2 days of hypoxia, name the hypoxic duration you want, and we can test how that impacts benthic fluxes, both during those events and in those transitional phases. We've also built an automated segmented continuous flow nutrient autoanalyzer that's going to have multiple sampling ports, so we can sample continuously benthic fluxes throughout this process. We'll have every 15-minute fluxes across these these transitional phases between hypoxia and normoxia, and this is going to significantly improve those estimates of phosphorus fluxes. And so the goal is this will provide rapid assessment of sediments from sites throughout the IRL, looking at fluxes under hypoxic, normoxic, and in between. And so what have we learned, right? We're building a system to look at those short-term changes in fluxes, but are there long-term consequences? Has this hypoxia, this chronic hypoxia, led to changes in the sediment composition? And yes, we're seeing a change in the phosphorus sorption capacity of sediments. Sediments hold, in theory, less phosphorus than they used to, right? So that equilibrium point concentration is helping to buffer concentrations. Before 2001, the equilibrium point concentration, 50 micrograms per liter. Now, that equilibrium point concentration, somewhere around 100 micrograms per liter. Basically, the sediments are helping to sustain the concentrations that we see in the lagoon now and what we saw in the lagoon in the past. And so sediments are so important toward controlling that phosphorus. The expanding extent of hypoxia is going to be important, and we're seeing data that shows that there's a chronic impact, and we're starting to now look at kind of how those short-term changes impact things. And so, to summarize this, spatial extent of hypoxia combined with fluxes under different hypoxic conditions helps us to explain things like these changes in phosphorus throughout the lagoon. And I want to end on time by thanking our funding agencies. There's been so many different people that have contributed to this over the years, but this work was primarily funded by Florida Department of Environmental Protection, the National Estuary Program, Brevard County, but we've had so many other people that have helped and contributed to this over the years. I want to also say that we're talking about technology today, but that technology, right, the people make this possible. And so I'd really like to thank the people, and AI can come for me if it thinks people aren't necessary. But I will end with save the sand and save the worms. They're so important towards controlling phosphorus, and those worms help to bioturbate, push that oxygen down to help control those phosphorus concentrations. So perfect timing. Thank you.
Woo! 10 seconds to spare. Thank you, Austin. Okay, next up we have Tara Blanchard, and she is gonna, this is a student presentation, Don't Go Breaking Apart, How Habitat Fragmentation Affects Oyster Reef Biodiversity.
Hi everyone, my name is Tara Blanchard. I am a PhD student at the University of Central Florida, and today I'm going to be sharing results from the first year of my research looking at the effects of oyster reef fragmentation on reef biodiversity. So habitat fragmentation occurs when large continuous areas are broken into multiple smaller isolated patches. Now this is a major ecological concern as it can lead to reduced habitat size, limited gene flow, loss of biodiversity, and increased vulnerability to disturbances. And while these impacts are well documented in many terrestrial systems, they are much less well understood in marine habitats, especially when it comes to our intertidal oyster reefs. Oyster reefs are critical for coastal habitats, providing habitat for fish, invertebrates, and birds. However, the effects of fragmentation on these species remain unknown. So in Mosquito Lagoon, where these aerial images are all from, a recent study documented that 9% of our intertidal oyster reefs fragmented between 2009 and 2021. Now, the mechanisms of this fragmentation are currently unknown, but we hypothesize that this may be related to sea level rise, changes in hydrology, and boat wakes or strikes. And even though we don't know the exact mechanism of this, it is still essential to understand what effects it has on biodiversity, because what we do know is that these smaller fragmented reefs are more vulnerable and less likely to persist over time, likely due to an increased vulnerability to those disturbances, such as boat wakes or storms. So my research aims to address two main questions. First, do bird density and behavior differ between fragmented and intact oyster reefs? And second, do the diversity in macroinvertebrates and reef-dwelling fishes differ between fragmented and intact reefs? And looking at biodiversity on these two different scales can allow us to have a broad view of the trophic web on these reefs. So for this study, I defined fragmented sites as those that were one continuous reef patch in 2009, but have since split into two distinct patches. And intact sites were those that have remained as a single continuous reef over that same time period. So to monitor birds on these reefs, I used remote motion-activated trail cameras that recorded 10-second video clips when triggered. And watching these videos, I recorded all birds that were on or within 1 meter of the reef. At fragmented sites, I deployed 2 cameras, one on each reef patch, while intact sites had 1 camera each. And I recorded the total amount of time birds were spending on each behavior, such as walking, loafing, or resting, and foraging. To sample macroinvertebrates, I used bioboxes, which are these mesh-lined cartons that are buried into the reef surface and filled with oyster clusters and loose shell to mimic the surrounding reef structure. These were deployed in summer 2025, and the first collection period began this winter, where upon retrieval, we identify, count, and measure all organisms. 4 of these bioboxes are deployed on the reef edges and 4 on the reef interior to assess differences in microhabitat structure. And at the fragmented sites, these were split evenly between the 2 reef patches. So preliminary results for these camera traps. To date, I've recorded 289 birds, made up of 18 species from over 18,000 video clips. And here are some examples of what species were commonly recorded on the cameras, with great blue herons being the most frequently recorded. Additionally, I've recorded 3 species of birds that are listed as threatened in the state of Florida, which are the American oyster catcher, little blue heron, and tricolored heron. So preliminary analyses of this data suggest that bird density, which is the number of birds per day per meter squared, did not differ between site types. And I also found that the total amount of time birds are spending on these sites does not differ. However, when looking at behavior and examining the top 5 most observed behaviors, I found that birds spent more time loafing or resting at fragmented sites and more time walking at intact sites. Now, this pattern is likely due to the fact that many of these bird species are highly territorial, especially over their preferred foraging areas. And at fragmented sites, these smaller, isolated reef patches may allow for birds to remain more stationary while still monitoring for predators and competitors and accessing reef edges for foraging. In contrast, those larger reefs at intact sites may require birds to patrol more actively to defend their territory and locate prey, resulting in increased walking behavior. And now these results are just from that summer data, which is what's completely processed so far. But here is a little sneak peek of the winter data that I've been collecting. And as you can see, we've been recording many migratory bird species, and this includes red-breasted mergansers and hooded mergansers, American white pelicans, and many gull and tern species. And this will allow us to examine differences between migratory and resident bird populations in the future. So moving on to the results from those bioboxes. To date, I've recorded over 14,000 organisms from the bioboxes made up of 62 unique taxa. And here are a few examples of those, and this includes bivalves, crustaceans, sponges, and bryozoans, and polychaetes. So when analyzing this data, I found that diversity did not significantly differ by site type. However, richness was slightly lower on fragmented sites, but this effect was small and non-significant. And this suggests that fragmentation status alone does not capture the main driver of diversity patterns on these reefs. However, within the reefs, diversity strongly differed by biobox location. So those bioboxes that were deployed on the reef edges had significantly higher richness and Shannon diversity than those interior bioboxes. And when we add in reef size into this model, we see that the edge effect of higher diversity on the edges decreases as reef size increases. So edge bioboxes have the highest Shannon diversity on small reefs, which have a higher edge to interior ratio, and then there is almost no change in those intact or interior biodiversity bioboxes. But together, these results suggest that microhabitat structure and reef size are important drivers of diversity patterns. So to summarize my findings to date, fragmentation by itself did not produce strong differences in bird diversity or bird density or biobox diversity. However, bird behavior did differ between site types, suggesting subtle differences in habitat quality. Biobox diversity was driven more by microhabitat structure, so edge versus interior, and reef size than by fragmentation status. And to better capture the nuanced effects of fragmentation, in the future I will be analyzing continuous landscape metrics such as edge density, proximity to neighboring reef patches, and patch shape complexity to see how these interact with edge habitat and reef size. And using these quantitative measures rather than a simple categorical fragmented versus intact classification may allow us to have a better understanding of how these are shaping differences in biodiversity based on whether how reef configuration changes over time. And overall, it's still important to understand how this occurs because it is critical to maintain long-term reef integrity, connectivity, and ecosystem function. So the next steps of this project include continued camera trap and biodiversity sampling and continued analyses of this data, and to evaluate reef reconnection as a potential strategy to enhance habitat quality and resilience. And we'll be doing this using POSH units or pervious oyster shell habitats to reconnect these fragmented reef patches to see if this can enhance biodiversity on these habitats. And with that, I'd like to thank the many students who have assisted with processing this trail camera videos. And thank you all so much for listening. I'd be happy to take any questions if there's time.
Thank you. You're going to have to catch Tara at the break. Thank you. Next up, we have another student presentation. We have Whitney Knope, and she is going to be talking about machine learning and fluorescent sensors.
All right. I already clicked. How do I go back? Oh my goodness. Wait, I figured it out. Awesome. Hello, everyone. My name is Whitney Knope, and I am a PhD student at the University of Colorado Boulder and an environmental engineer with Verity. And I'm really happy to be here today, all the way from Colorado, presenting on machine learning and fluorescent sensors, modeling E. coli dynamics in coastal waters. Oh no. So first, starting off, why monitor microbial contamination? As I'm sure many of us are aware, microbial contamination drives public health risk and environmental concerns, specifically through dynamics like runoff, leaky sewer systems, and failing septic systems. Typical conventional methods for monitoring microbial contamination require field sampling, lab analysis, and long time periods of incubation, which are often limiting time response for identifying contamination events. Additionally, these events or these sampling methods are spatially and temporally limited, given that you take a sample, have to wait 24 hours, and you're only seeing data from a single point, which doesn't often capture episodic contamination events. This makes for significant challenges in regulatory compliance, as well as operational functionality in order to identify sources of contamination, as well as public health risk in the environment. Additionally, microbial monitoring at current locations is very financially restrictive as well. So, born out of this, our research group has developed the first real-time IoT device for monitoring E. coli. It's this whole thing right here, which utilizes fluorescence-based monitoring for the amino acid tryptophan. And tryptophan is known to be highly correlated to E. coli, as it is present in the cell walls of E. coli from the gut microbiome and fecal contamination. So this sensor is fully integrated IoT, and it takes measurements through a passive monitoring optical chamber, which senses the intensity of fluorescence of this bacteria, and then is able to be correlated to the presence and counts of E. coli. The sensor itself is highly stable and allows for really low detection, as well as is equipped with 2 high-powered LEDs to monitor both at high and low levels of contamination. We then take these data points and build a regression model built on ground truth enumeration methods. Additionally, this sensor includes a time of flight sensor, which is essentially the same as a turbidimeter, so allows for measurement of turbidity and allows for this to be integrated into our model. It also measures temperature, which are known to impact fluorescence and E. coli contamination events. So, over the course of the last year, our team has been able to deploy over 20 sensors across the US and France to monitor this contamination. We deployed sensors in Paris, in Chicago, Cleveland, Boston, as well as 4 sensors along Boulder Creek right outside my research lab. And through that, we've collected over 600 data points to train our machine learning models, which is how we take the data from raw sensor signal to meaningful outputs. These contexts are diverse in both their environmental as well as regulatory contexts, so these sensors inform both on compliance as well as recreational advisories for safe water swimming. We've been able to collaborate with universities, cities, water advocacy groups, and private companies throughout the duration of these deployments. As well, all of the data are either collected with membrane filtration or call alert data, and those are both EPA-approved methods for the ground truth data. It's worth mentioning that these methods for enumeration are, in and of itself, wrought with some level of error, which is specifically known to be more impactful at low ends of concentration. So while we train our model on these data, there is existing error that is occurring within these EPA-approved methods. So moving on to some of the results, the machine learning model that predicts E. coli concentrations comes in 2 different forms. The first of these is a categorical model, and the second is a continuous model. So first I'll talk about the categorical model, which is seen on the left here. So the categorical model breaks down estimations of contamination into 3 categories, which are operationally relevant for notifying when there's contamination. Less than 10 follows WHO standards for low risk or safe drinking water. 10 to 100 typically falls within safe recreating limits, although this is dependent on specific location. And greater than 100 typically is not safe for drinking or swimming. So our model predicts or is able to achieve around 90% accuracy within these 3 categories. However, it is worth noting the data on which it's trained at the moment is significantly biased towards that middle category. So one of the things that we continue to do, and is not included in this data set, but I'm working on in my research currently, is including really lower concentrations and at the line between that 10 and 100 to make sure that we're able to significantly differentiate between those concentrations. However, you can see all of the misclassifications are really limited to that low area of accuracy, which we're improving at the moment, and are only constrained to neighboring categories, so there's no significant misclassifications. On the right here, you see the continuous model, and this is for predicting any sort of E. coli contamination. We trained our model on exclusively call alert data, and so the horizontal error bars reflect the 95% confidence interval cited by IDEX on their estimation. So you can see at the lower range, we get pretty wide potential error. Our model was able to predict all of over 75% of these contamination events within the error bounds of the ground truth. So we're approaching really high accuracy there with a mean average percent error of about 7%. So now I would like to welcome up our colleague, Dr. Laura Wilson from the Marine Resources Council to talk how this can specifically impact the the Indian River Lagoon.
So MRC, we are the end user partner as part of this project. As part of our historic data, we have 35 years of citizen science water quality data from the entire length of the lagoon, and this includes several years of bacteria data. So for the last 3.5 years, we've collaborated with Space Coast Surfrider and their Blue Water Task Force to look at enterobacteria at specific sites of concerns. So with that, we've come up with a plan of key places for deployment for the sensors across the lagoon, where we can then provide the ground truthing for calibrations using the traditional wet chemistry models. This will be, if I remember correctly, the first estuarian deployment of the sensors. So really working to get that kind of boots on the ground in what's going on with the historical data and manual sampling. Once we get the computer learning models and calibrations up to date, MRC is also going to be the ones hosting the data for public use and awareness. And so the idea is that this can become a lot more predictive versus our very either passive or reactive grab sampling after wastewater spills or something like that. So the goals are to reduce those gaps and then increase public awareness and municipal response to when we have the bacteria surges. The sensors that'll be deployed in the lagoon are also going to have chlorophyll A as well as turbidity sensors on them as well. So we'll be able to pair chlorophyll A data with the bacteria data and turbidity to get a little bit more holistic picture of what's going on with the water quality that could be driving any of the harmful algal blooms that we may see going forward.
Thank you, Laura. And I just want to close the loop on this, mentioning that we have a preprint of all of these data that have gone in so far, and to thank all of my collaborators on how we've been able to pursue this, as well as all of our community partners. And we're really looking forward to further collaborating on this. So thank you very much, and I'll take any questions later, I'm sure.
Hello. Thank you, Whitney. Next up, we have another student presentation. We have Adam Steinfeld, and he is going to be talking about remote visual monitoring of predator interactions in hard clam aquaculture.
All right, hello everybody. I want to talk about today some of my master's thesis work, which is looking at predators on hard clam aquaculture sites. So the commercial clam aquaculture industry here in Florida is a growing and valuable industry. Began in the 1980s, and in 1987, around 2.5 million clams were being produced. In 2019, almost 100 million clams were produced. The vast majority of Florida's shellfish aquaculture sales, in general, are the hard clam. The other purpose for clam aquaculture here is for ecosystem restoration. By leveraging clams' efficient filter feeding capabilities, we can help sequester excess nutrients from our water column. Together, these efforts require space in our coastal waterways. Today, around 2,600 acres of our coastal waters are comprised of designated aquaculture zones. And here's a map of all the counties, just for reference around Florida, that do use this aquaculture leasing system. To start, clam aquaculture begins in the hatchery phase in a controlled facility. This lasts to around 1 millimeter shell length. Then the clams are placed in a nursery setting in a flow-through system, or actually placed in the field, consolidated in fine mesh bags and staked to the bottom of clam leases. The next stage is the commercial grow-out stage, where again, clams are placed into a bag, a wider mesh bag, and staked to the bottom of clam leases. This stage lasts to at least the first commercial size, which is like something you'd find in like a pasta dish. The bags both serve to consolidate the clams, but also as a predator exclusion device. However, these two field-based stages, they are still vulnerable to predation, as these bags can be left out for up to 18 months at a time. These bags fail and leave the clams open to predation. So as you'd imagine, this is a financial loss for aquaculture growers. In 2022, we distributed a questionnaire to growers around the state, asking them to estimate some annual costs of both clam mortality and gear damages. This ranged anywhere from $1,000 to $100,000. We also asked them to report on some predators that they believe are causing these damages. Some top predators were things like black drum, stingray, sheep's head, cow-nose ray, and through literature, some reports have predatory invertebrates and even sea turtles. However, the evidence for these larger vertebrate predators actually remains very limited, and a lot of the reports are very anecdotal. Predation on farm bivalves is actually a global challenge and can lead to negative perceptions of species implicated and even less likely to support conservation efforts overall. So to address our kind of gap in knowledge about predator dynamics at these sites, we're first going to kind of see what predators are actually present at an active aquaculture site, as well as if any environmental conditions will influence their visitation patterns. To address this, we deployed 4 cameras on our leases. These are time-lapse cameras that take one photo every 20 seconds for the entire day. This gave us around 2,000 to 2,500 frames per day, depending on seasonal variable day length. And deployments lasted from 7 to 12 and a half days. Just to orient everyone to our study site, this is the central Indian River Lagoon. The northern sections, the Sebastian Inlet. Down here are highlighted are the aquaculture zones. In between is Erlon Station SB, which we pulled our environmental parameters from. This enhanced image, you can actually make out the rows of the clam bags, as well as our camera deployments overlaid with our field of views highlighted. So upon retrieval of the cameras, we look at each and every single frame and identify all the fauna that's passing by. We also classified some behavior, like as if they're actively foraging, just swimming by, or I don't really know what this loggerhead was doing, but. This yielded almost 90,000 frames to review, 12,000 of which actually had some fauna in them. This was across 44 days, 4 seasons, and we saw 42 unique taxa. Among teleosts, we saw a majority, it was largely dominated by catfish, grunts, and burrfish. For sharks and rays, we saw mostly stingrays, while we did see some visitation of sharks and white-spotted eagle rays. Among sea turtles, the majority we saw were green sea turtles and almost 30% loggerhead. We then fit binomial GAMs to model hourly clam lease presence as a function of temperature, turbidity, season, and as a random intercept our camera location. We use this functional group of molluscivores comprised of fish that we saw on our cameras that were known molluscivores such as sheep's head, burrfish, puffers, permit, pompano. This model here has turbidity held at a median to isolate the response of temperature. As you can see, around 18 to 23 degrees Celsius, there is an elevated probability of being present at the clam lease. We also fit this model for stingrays, where we did see a slight increase in those more extreme higher ranges of temperature, around 29 to 30 degrees Celsius, although this model had a much lower effect size. I think overall, predator activity is, we got some evidence that predator activity is structured by some of the environmental conditions out on the clam lease. For teleosts, we found a kind of ideal range for their temperature, and that's for the molluscivores, which are of interest to us. And for stingrays, we did see that slight increase in that higher temperature range, but did seem to be less temperature driven. And I think an important takeaway from this, which is what I'll kind of delve into further, is that the responses seem to differ among predator groups. And so as I expand this research, we'll incorporate other covariates as well as species groups, as well as incorporating those behavioral dynamics. And I think overall, down the line, the results from this study will help predict some high-risk periods for predation and even some unwanted stingray farmer encounters. I think this can help inform some netting and exclusion strategies as you want to cater your predator exclusion materials to what predators are actually present. And I think commercial aquaculture planning for other on-bottom bivalves and for restoration purposes, I think this will help planning for those. I like to acknowledge the striped burrfish. It kept me endlessly entertained during my hours and hours of video analysis. I'd like to thank my funding sources of the Aquaculture Review Council, Specialty License Plate Fund for Aquaculture, the Harbor Branch Foundation, Ed Mangano and the Orchid Island Shellfish Company for all the collaboration over the years, Team Erlon for keeping all their stations up and running and all the really hard work you guys do, as well as my advisor, Dr. Ajamian.
Thank you. We have time for one quick question. Okay. Catch you up, Rick. Thank you. All right. Last up, we have another student presentation. This is Cecilia Hampton, and I can't read it in the dark, so she will let us know.
Hi, everybody. It'll load up in just a second here, but I'm going to talk to you guys more from the perspective of the creatures that find the things in the sediment delicious. So this is the white-spotted eagle ray, and we're going to talk about using novel biologging technologies to reveal some of their foraging behavior that we have not before been able to confirm. All right, so if you spent any time in the Indian River Lagoon, hopefully you've seen one of these guys, the white-spotted eel ray, Aetobatus nari, and you may have seen them swimming, jumping in the air, doing whatever. They are a voracious coastal durophagous predator with a benthopelagic lifestyle. So they live in the water column and move out to offshore pelagic areas, but they feed in the benthos on macroinvertebrates, either infaunal or epifaunal. And that includes mollusks and crustaceans, which we have recorded using stomach content analysis. And we do know that their mesoscale movement patterns tend to be localized around channels, bridges, current, inlets, things like this. They really like that kind of area. And we know that they go in shallower areas at night, but we haven't been able to confirm where or when they're doing this feeding. And this is a huge gap that we need to fill in order to better understand how predators affect benthic macroinvertebrate populations, which, as we've discussed, are vital to the health of lagoons. So that's what we're really missing here. So let's, instead of watching a mobile predator from a stationary point of view, which Adam just wonderfully described for us, let's put the sensor on the animal's head and follow it around and see what it does. So doing this, we get to know exactly what the predator that we're recording from is. We get to record all of its predation during a certain time period, and we get to answer questions about what the prey are, where they are, and when the foraging is occurring, which give us more information on that predator vulnerability, which is, like I said, a crucial gap in that background natural mortality to predation. So let's put it on the head. So this is our tag. Well, our tag is designed by Customized Animal Tracking Solutions and assembled and finalized here on site by our wonderful Ben Metzger. It includes an internal depth and temperature sensor as well as a triaxial inertial measurement unit, which is the same thing you might have in a smartwatch, as well as a camera and a underwater microphone or hydrophone up on the front. We also have equipment to help us retrieve it when it falls off. It is attached, much like you may have heard of D-tags on dolphins with passive suction cups, but we also developed an attachment method which increased the duration of our deployments using a galvanic timed release strapped to two rounded, soft, biodegradable 3D printed hooks which settle on the dorsal spherical cartilage on either side of the head. This is what that attachment looks like. It's quick, so pay attention. First cup, second cup, GTR goes on top, and the hooks are stretched to these spiracles. So that ray is now ready to go and hopefully resume normal foraging behavior as soon as possible. So a few miles south of here, this is the Fort Pierce Inlet, and these are the locations where we tagged rays in 2025, and these are the rays that we tagged. You'll see there are 3 smaller males and 2 larger females, one of whom we actually captured twice, sorry, and did tag a second time. So these are the durations of those deployments over the time of day. You'll see that most of them start in the middle day or the early afternoon, and that's just because it's really easy to see them when the sun is out at high tide. Happens to be the only time it is possible to do this. So the tag stays on, and then either the battery dies or the tag falls off either that evening, the next morning, or in some cases, it can last a bit longer. These are the depth profiles of all of those deployments. They're stacked on top of each other in cases that we had multiple days. But you can see some sort of dial patterns maybe that the animals are using areas between 0 and more than 10 meters, almost 15 in some points of depth, and that very likely indicates use of dredged areas in the inlet based on what it looked like on the camera and where they were before and after those depths were measured. And then all of them seem to, at night, go to really, really shallow depths. So are they just at the surface, or are they in the shallows? And again, we're seeing that kind of conserved over everything, but do keep in mind that the morning we're a bit data deficient comparatively. But all of them seem to go very shallow at night. So we look at the videos and we look at the audio and we label what we see. For example, here are some videos that we would have labeled with the help of Ethan Canto. And we would label things like whether the bottom is visible and what it is if we can see it, whether the ray is swimming or what else it might be doing, and whether a conspecific is visible or other interesting behaviors. For example, you can see the tail of another ray. Now this is a foraging event. So on the top you're going to see depth. And this is a digging behavior that the rays exhibit when they're trying to maybe excavate an infaunal prey item in sediment. So we can both see that and actually hear it. It's a bit quiet, but we can hear it. And then this ray is now going to move on and find a very, very nervous hermit crab for good reason. There's a hermit crab, and that has been abducted. So it's now manipulating the hermit crab in its mouth, kind of adjusting the orientation. We've had to speed this up. I'm not sure if we're going to be able to hear anything. We were supposed to, but now it's, there we go. Now we're processing the hermit crab shell, and you can hear the shell failure. It's quite loud. So as it processes that shell, it'll move back down to the benthos, and as you could hear, we could be labeling that without the video. So this is an example at about midnight of the same ray. And you can see on the bottom, this is a spectrogram. On the top are high frequencies, the bottom are low frequencies. Brighter colors are more powerful or louder signals. And you can see that we can sort of see this digging behavior in the spectrogram there. And you can actually hear it. Again, it's a little quiet, I apologize. But then you will also hear the processing of the prey. So we can both hear a part of their foraging behavior and the success of that foraging event or not, at least whether there was a shell involved. So we can just hear nice crunches. So by confirming those in the audio, these are the 206 feeding events that we recorded, colored by individual, so you can see how it sort of spreads out across different deployments. And we got a pretty high density of feeding, especially in the late evening, and just generally a bit more at night or around dusk times than midday. But we did see feeding up to about 5 meters and one event deeper than that, so we are seeing feeding at various depths as well as pretty much throughout the day. I clicked the wrong button. There we go. So what we're learning is that they're eating a variety of prey items, including epifauna and infauna, and mollusks and crustaceans. We're seeing them eat blue crabs, hermit crabs, things like that. And they're feeding between 0 and 7 meters. They tend to feed where they're going and go where they're feeding. Excuse me. And they're feeding in various bottom types like sand, seagrass, and rubble. So again, this gives us more insights into where the prey items are vulnerable to predation and will give us a lot of context when we work in the future to conserve and maintain populations of macroinvertebrates that we care a lot about. Now, geospatially, it's pretty hard to estimate from an animal that does not breathe at the surface, unfortunately. So we have pretty rough pseudo-tracks, and we will be deploying a lot more tags this summer and hopefully getting a much better idea of where they're actually spending their time physically, longitude, latitude-wise. Finally, if you're out on the Indian River Lagoon and you happen to see a little pink thingy floating around, I do really need it back. Please, please give us a call. The phone number's on there, or just stop by. We would love to see that again. And thank you so very much for listening to me.
Thank you. We have time for one question before we start our 3-minute slides. Questions? Okay, I guess they'll get you at the break. Now I'm going to pass it off to Kristen. Good luck, everyone.
All right, everybody. Okay, so we're going to move on to our first session of our lightning talks, which is 3 minutes, sometimes 3 slides, but most importantly, 3 minutes. So just going to give a little bit of ground rules as we go into this first session. If you are later in the afternoon and have a chance, please make sure to sit in the first 2 rows if you are a presenter. And then also,
for each presenter. If you want to be at the base of the stairs when the person previously to you is presenting, that'll give you a quick transition up to the slide. You will have 3 minutes as soon as I'm done saying that what your title is. And we'll be timing it with a beeper. You'll be hearing the beeper go off. It will stay going off if you go over 3 minutes, okay? And in keeping with tradition, if you go really long, we still have the net. And I'm not afraid to use it. Okay, hopefully that doesn't fall. All right, so getting ready with our first speaker. Going to welcome to the stage, as I put this down. Yep, I'm going to welcome to the stage Richard Axe, and it's a student presentation, and he's going to be discussing unsupervised clustering of passive acoustic monitoring sound signatures in the Indian River Lagoon.
Hi everyone, my name is Richard. I'm working with Dr. Sharubin, and we've been working with acoustic data from the Indian River Lagoon. So this is slide 1 of 4. So the main problem that we've been facing is that acoustic data is cheap and easier to collect considering video or image data. And essentially we can deploy these different hydrophones in both the Indian River Lagoon, and then Dr. Laurent and I have been working with the Gulf of Mexico and the Caribbean. And by using these continuous deployments, we can record data for up to months. So this specific project focused on 2 months of continuous recording, 1 minute on for every 5 minutes. And this produces up to terabytes of data. So I think I've had to deal with more than 2 terabytes by now. And our goal was, this is extremely tedious to analyze and label. No one's gonna sit there through 2 terabytes. We've tried, it doesn't work. So how can we uncover acoustic structure using unsupervised machine learning? And until the last 5 years or so, this wasn't exactly possible until self-supervised learning, due to all this generative AI, really advanced this. And we've deployed one of these models that were recently developed and optimized it for passive acoustic monitoring. So here's just a preliminary quantitative findings that we had. And our method, called SimClear, or contrastive learning, has the highest silhouette scores as well as temporal results when comparing it to previous state-of-the-art methods, including wavelet transform and Mills frequency coefficients. And this results in a clustering space that gives us area densities that actually represent meaningful clusters in the acoustic space, with our method having the highest 24-hour temporal patterns, which is a unique finding that we didn't expect to actually see. So what this practically means is that once we cluster the data, we can actually find clusters that display this heat map pattern without any actual intervention by experts. So just purely by clustering, they gave us heat maps. This is the 0 to first 15 days of the deployment. And different patterns show up at different time periods. So this hour of day profile actually shows that different clusters peak in occurrence at different points. So this cluster, cluster 21, generally shows up during daylight hours, so from midday toward 6 o'clock or so. But other patterns show up during dawn hours, for example, or generally during the nighttime hours. This cluster itself is a repeated pulse train that is most likely biological and shows up during the nighttime in the Indian River Lagoon, corresponding to, I think, this cluster here, which does show this temporal pattern. And the key implication of this study is that we can actually use this, deploy it in acoustic deployments as well as video data, and without any intervention, give a basic map of what the data entails. So off the bat, understand behavioral, understand what the data is actually giving us before going in and focusing on specific parts of the data. And hopefully this will speed up analysis of these large data sets, and then also move on to video and image data to greatly speed up the process. Thank you.
All right, great job. Thank you for being such a good model for our first 3-minute talk. Up next is Alex Johnson, and the presentation is real-time fecal risk sensing in the Indian River Lagoon, from satellites to sensors.
Howdy, folks. I think I'm the first non-academic up here today, so be gentle with me. My name is Alex Johnson. I'm the Chief Strategy Officer for Verity. So this is kind of a part 2 to what you just heard from Whitney and Laura about the Loom, real-time fecal risk sensing device. And I think important and interesting, at least Dwayne led me to believe, some commercialization and innovation talk would be interesting today beyond the science. I think This is important to note that these sensors right now are in a community water filter device that we deploy in Rwanda. Viridi, the bulk of our business, is actually clean water delivery in 6 African countries. And in order to finance, right now, 500,000 people getting clean water every single day, we needed a low-cost, rugged IoT sensor that demonstrated that the water was clean enough, it was meeting World Health Organization standards. So that's what led us at the University of Colorado Boulder and at Viridi, which is a spin-out of that research, to a very low cost. This is about $1,000 to make. There's no moving parts. You can open it up. The water moves through this part, and an LED flashes and is bounced back the fluorescence onto the photomultiplier. And that gives us a very low-cost way to know if that water is clean. We're using this for clean water, as I said, but then we're starting to look at, are there large commercial applications in the United States, in Europe, in more developed water sectors, and we think that there are. So testing that out with MRC in the Indian River Lagoon is a very exciting next step for us. You already saw the device. You heard a good bit about the accuracy. I think the take-home that we're finding is that, look, there's 2 EPA-certified ways to measure fecal coliform in America. Both of those are lab tests. You need to get a grab sample. You take them to a lab. You hear back a day later, and they have uncertainty bars that are decently large. We can hit those same uncertainty bars, at least 94% accuracy of those uncertainty bars, on a device that can give you data every minute, every 15 minutes, every hour, and go up to a cellular network or even a satellite network. And so that, I think, with a low-cost sensor and then taking advantage of massive improvements in AI and machine learning, we think could be a pretty big change in what is currently a $300 million a year business for fecal coliform testing in America alone. So, in terms of the deployment, our company has been very fortunate to get a lot of funding from the National Science Foundation, as well as NASA appropriations last year, as well as plenty of private contracts with interested parties. And through those funding sources, we're excited to bring this type of dashboard. Actually, the dashboards have accelerated quite a lot just recently. If I'd known that the AV was this good, I would have brought you something that moved. But we want to bring that here, NASA KSC and with the MRC. Thank you.
All right, up next, we have Leslie Bertolotti, and whose presentation is Smart Watershed Network Management in the IRL. And I won't start till your presentation's up.
Hi, everyone. I'm excited to be here today to talk to you about Smart Watershed Network innovation. For over a decade, smart stormwater pond technology, known as continuous monitoring and adaptive control, has shown us that these actively controlled stormwater ponds outperform static ponds in retention, in treatment, and in flood protection. But there's a limitation with these. Every pond operates in isolation. Runoff and first flush pollutants hit downstream water bodies simultaneously, compounding their adverse effects to these systems. When we should be looking at our stormwater systems holistically, like a watershed. So what would happen if these smart stormwater ponds shared data and coordinated and acted more like a natural system would? And that's the question that we're asking ourselves. So our core innovation pairs 2 things. First, it's machine learning, known as a neural network, that learns a relationship between ponds from measured and modeled data, how to optimize flow through the network. And second, we have developed fast simulation models that run about 1,000 times faster than traditional physics-based approaches, allowing us to run thousands of simulations within minutes and feed that learning into the neural network. And we're testing this technology at a pilot in Indian River County, an about 4 square kilometer site with interconnected ponds that serve about 2,500 residents. And each pond will receive water quality sensors, automated sampling and valves, and control software for operations. And the system will predict when the ponds will receive inflow and will provide storage capacity ahead of large storm events. Then it sequences releases amongst the ponds to avoid peak flows and to optimize water quality. So the questions we're asking ourselves in this pilot are, what is the benefit of systems that share data and coordinate versus isolated control strategies? Can these systems learn hydraulic connections from real-time data, or do we need to train it from existing models? And how do we balance competing goals, emptying ponds before storms and holding water back after storms for treatment while still meeting regulatory requirements? We anticipate this pilot will be operational in the first quarter of 2027. We're partnering with the University of Florida, who's looking at nitrogen cycling, with AWS and NVIDIA on the AI and machine learning models, and with the IRL NEP, St. Johns River Water Management District, and the county on the pilot project. And we're always looking for partners, advisors, other folks that are interested in these technological advances to join in the development. So if you're interested, please see me afterwards. Thank you.
You beat the buzzer. All right, up next we have Brandon Rao, whose presentation will be Autonomous Aerial and Surface Systems Transforming Coastal Habitat Restoration.
So hi everybody, good morning. I'm Brandon Rao. I'm a restoration specialist at Aquatech Eco Consultants. I just wanted to show off a little bit of our technology we've been using and are starting to plan to use in this season and moving forward. So we have a fleet of heavy lift drones we've been using for shellfish restoration, along with putting out harmful algal bloom dispersants with moat. It's very similar to some of the work that Dr. Todd Osborne's been doing over here in the IRL. We put out 36 million clams, or 36 million oysters in about 3.5 days up in Apalachicola last summer, so that was pretty cool. Our biggest drone can lift up to 150 pounds, so it's a really effective tool at, putting out large volume of oysters at a time and also scaring my niece into behaving. And then it's really user-friendly. All the variables can be adjusted and used based on your winds, your weather conditions. You could import a shapefile, and it automatically fills the flight path for you. It knows when the battery dies, so if it ends halfway through like an acre or a polygon, it changes the battery, and it picks right where it left off. So this summer, we have implemented some USVs. So these are basically open source autonomous boats that we have been starting to outfit with some survey technology. So we're able to do like bottom composition, vegetation, and determine the appropriate areas for shellfish and oyster restoration. So this is super helpful with the new general permit that DEP put out for seagrass restoration. So it's a really effective tool for helping us choose effective locations for seagrass restoration, so we know it's going to be successful. And then we have implemented or starting to implement our own proprietary software that basically sums all of this up. Similar to the drone profile, we can import a shape file, or we could actually drive the boat around, let's say, a map grounding that might not be on Google Earth or Google Images. So we can go out into the field, go around a boat grounding, go over prop scars, and it'll actually create on site a very rough, not so pretty 3D point cloud of the bottom, so we can calculate fill, water depth, temperature, and all that good stuff as well. So this is just some of the stuff that we're going to be putting out and using in some of our restoration projects this summer and moving forward. And if anybody is interested and would like to help us either further develop it, especially with our AI learning modules that we're starting to do BB scores, presence, absence, and even species detection, we'd love to partner with you guys to further refine our program. And that's it.
Great. Thank you very much. So up next is Carolyn Vanso, and the presentation is Spectral Constraints and Opportunities for Satellite-Based Seagrass Detection.
Good morning. I'm excited to be here today to discuss how emerging remote sensing tools perform in one of the most optically complex systems we work in, the Indian River Lagoon. The Indian River Lagoon is a particularly hard test case for satellite-based seagrass detection. We know that seagrass beds often occur in those narrow, fragmented patches, and water clarity can change rapidly due to storms, freshwater inputs, or blooms. Managers often need information quickly to understand where this change is occurring. Field monitoring remains essential, but capturing lagoon-wide patterns or responding rapidly using field data alone can be difficult. This is where emerging remote sensing tools have the potential to add value if they're applied under the right conditions. Across recent studies, 3 interacting factors consistently control whether satellites can reliably detect seagrass. Environmental conditions are the dominant constraint. Depth, turbidity, color-dissolved organic matter, CDOM, determine whether the benthic signal reaches the sensor at all. When that signal is lost, sensor choice matters very little. Spatial resolution becomes important when seagrass occurs in those narrow or fragmented patches, and spectral bands, such as red edge wavelengths, can improve discrimination, but only when sufficient signal is present. So, in those optically complex systems like the Indian River Lagoon, environmental conditions often determine whether any satellite-based approach will work at all. The key takeaway for the Indian River Lagoon is that there's no universally reliable satellite for seagrass detection. Sentinel-2, PlanetScope, and even higher resolution sensors all can perform well, but only when environmental thresholds allow it. Again, in optically complex systems, sensor capabilities matter far less than water quality, depth, and timing. Treating satellite-derived maps without that context risks overconfidence. This synthesis highlights the importance of treating satellite imagery as a conditional tool, one whose reliability depends on environmental context, not just sensor specifications. Thank you.
All right, thank you very much. Our next presentation is a student presentation. It is Madison Bennett, and she'll be discussing advancing plankton monitoring in the Indian River Lagoon, a comparative study of the imaging flow cytobot and AutoHolo.
Hi, I'm Madison Bennett from the NIAC lab here at Harbor Branch, and this project compares 2 in situ plankton imaging systems. Plankton monitoring has traditionally relied on net tows and manual counting, but this is labor-intensive and fragments delicate colonial organisms. In situ imaging offers the solution of real-time plankton monitoring in their natural habitat with minimal disturbance. So in this study, I compare the most popular commercially available plankton imaging instrument, the imaging flow cytobot, with the AutoHolo, a custom-built digital holographic imaging system developed here at Harbor Branch. The IFCB is an automated flow cytometer that combines fluorescence-triggered detection with high-resolution imaging. It's well-suited for nano and microplankton between roughly 10 and 150 microns, but it's limited by its flow-through design, which can break chains and colonies, and it takes a long time to sample a small volume of water. Our system, the AutoHolo, uses digital holography to reconstruct 3-dimensional images within a free stream sample volume. Its adjustable sample length and internal optics allow it to measure particles from 10 microns up to 2.7 centimeters with minimal disturbance. So the objectives of this project are to develop an initial IFCB database for the Indian River Lagoon, compare the IFCB and AutoHolo during co-deployments, and test both systems' performance in other environments. We began collecting data this August with researchers at the University of Connecticut's Avery Point Flowing Seawater Laboratory. In the lab experiments, the IFCB and AutoHolo were both connected to the flowing seawater system for a direct comparison of the plankton community being sampled. For field testing, we deployed both of the instruments simultaneously from a boat just outside the lab in Long Island Sound. And this design allows us to compare organism detection, size distribution, and imaging capabilities under both controlled and natural conditions. And here's some representative lab and field data from both instruments. The IFCB generates processed 2D images triggered by fluorescence, and the AutoHolo produces raw holograms that are out of focus before reconstruction. So the goal isn't to compare image clarity at this stage, but just to look at general organism presence, size ranges, and patterns in the data sets. By looking through the data so far, we can see that IFCB primarily captures smaller individual particles, while the AutoHolo captures a broader size range and more complex structures. Together, these initial results help us define how these two systems capture complementary views of the plankton community and guide the next phase of deployments in the Indian River Lagoon. This work will produce a publicly available baseline IFCB data set for the IRL and support future work. Thanks.
All right, thank you, Madison. Up next is another student presentation. Alexis Bates will be presenting characterizing zooplankton and nekton behavior in the Indian River Lagoon through in situ stereo imaging.
Hello, my name is Alexis Bates, and I will be presenting characterizing zooplankton and nekton behavior in the Indian River Lagoon through in situ stereo imaging. Currently, we're focusing on zooplankton and micronekton, which range in size from tens of microns to a few centimeters, and include groups such as copepods, krill, larval fish, and jellies. And these really consist of key components of our aquatic food webs in the Indian River Lagoon. They link phytoplankton to higher trophic levels. But unfortunately, there exists a research gap where it's difficult to quantify these individuals using standard and traditional sampling methodologies. And this is because of their elusive and patchy distributions. So there exists this need for a high-resolution, non-invasive imaging technique in order to study their spatial patterns and behavior in these natural environments. So this project introduces a custom-built in situ stereo imaging system where we have two cameras consisting of high-resolution, high frame rate mounted on a modular base plate. We're able to use this camera with a similar methodology of binocular vision, or how our eyes see things, to perceive things in 3 dimensions. On this next slide, you see an example from one of our cameras of a very dense mysid swarm. This is a swarm of mysids approximately 1 centimeter in size, and you can see hundreds of mysids here. It was collected in an estuary system where the stereo vision system is facing downwards. And currently we look to extract 3 main pieces of information from this. We're concerned with the density of the swarm by characterizing things such as its average nearest neighbor distance, as well as the nearest neighbor distributions to tell us how dense it is, which has implications for predation. We're looking at the alignment, which we can extract polarity and polarization order, which essentially tells us their orientation relative to the surrounding individuals and as a group. And we're looking at the cohesiveness, where we extract individual information such as its speed, acceleration, and temporal evolution. And overall, we can take these 3 metrics and combine them with additional sensors and data about our fluid environment to understand how they're performing under different flow conditions and light availability. So in summary, we have a custom-built in situ stereo imaging system that has been tested in the Indian River Lagoon and elsewhere successfully. And really, we can generate a 3D map of approximately 1,500 centimeters cubed underwater, offering a clear spatial representation of our size range that we're interested in. And we're currently focusing future efforts on refining our image processing pipeline to really hone in on sensitivity towards smaller zooplankton species like our mysid shrimp that we just saw, and improving tracking across a variety of environmental conditions like the very turbid IRL. I'd like to acknowledge my various funding sources and machine shop support, and thank you.
All right, up next is Kirk Fusco, and he's going to be discussing Can You Hear Me Now? An acoustic look into the world of Indian River Lagoon horseshoe crabs.
All right, yeah, so we are going to talk about arguably the most adorable animal for this year's symposium, the Atlantic horseshoe crab, Limulus polyphemus. So besides being extraordinarily majestic, IRL horseshoe crabs are also extraordinarily mysterious. So thanks to programs like FWC and Seagrass Florida Horseshoe Crab Watch, which is an amazing program, it's a mark recapture program, where citizen scientists, along with other scientists, actually tag horseshoe crabs when they're spawning on shore. They do nest and lay their eggs on shore during high tides. And that gives us a lot of data, or it's starting to shed light on what our horseshoe crab populations are looking like around the state. Unfortunately, that also leaves a data gap there for the rest of the horseshoe crab's life history. So I always say, sea turtle folks, you have your sea turtles' lost years. I like to think of this as the horseshoe crab's lost years. So what are they doing when they're not spawning, when we don't see them because they're not on shore? So in an attempt to fill some of these gaps, we've conducted a very pilot acoustic telemetry tagging study. So this is the first time that we've acoustically tagged horseshoe crabs in the state of Florida. Only a handful of other projects exist along the eastern seaboard that actually acoustically tag horseshoe crabs. So our study site was a cove in Titusville that hosts the largest nesting population in the state for horseshoe crabs, so that was very convenient. And what we did was we actually tagged 15 individuals, 15 adult horseshoe crabs who were spawning, with acoustic transmitters. So that little hat that larger horseshoe crab who is the female is wearing, that's our acoustic transmitter. If you have questions about how we attach it, you can see me at lunch. All right, so what did we find? Hey, look, a graph. All right, cool. So we actually gained over 24,000 detections or pings from this pilot study. We looked at these horseshoe crabs over a period of 17 months. And what we found was there's definitely seasonality when it comes to their movements and range and where they are. Prior to this, honestly, I expected to see, oh yeah, the horseshoe crabs, when they're not spawning, which for the IRL would be the spring times, our primary spawning period, when they're not spawning, they're probably just hanging out a little bit offshore, right, of their spawning beach. No, they actually move around a lot. So what you're seeing here on this graph, those are our 17 months of data, and bars are representing number of pings. The line there is representing number of different individuals. And as a scientist, I like the way this graph looks because you can see two very clear peaks identifying two very clear nesting seasons. And for our study area, you'll see that essentially horseshoe crabs are around when they're breeding, and guess what? They're not around at all when they're not. There's a lot of awesome people that did a lot of work for this. They're right there. And come see me at lunch to talk about crabs. Thanks.
All right, up next is a student presentation. It is Derek Aoki, and he's going to be discussing monitoring the sea turtle abundance using adaptive resolution imaging sonar.
All right, cool. So thank you, everybody. My name is Derek, and yeah, I'm going to talk a little bit about sea turtles and sonar. So adaptive resolution imaging sonar is basically an underwater acoustic camera that emits high-frequency sound pulses into the water column to detect objects and animals. So if these things are found, the objects will basically have a return signal back to the camera's onboard transducer, and then they'll generate these high-quality images and videos of whatever the object is. So you can see by this diver, tire, and then the ship hull. So ARIS is often used for underwater inspections, port security, and search and rescue missions, mainly because it can detect these objects in very turbid waters or under very low light, low visibility conditions. However, more recently, ARIS cameras have been used for more fishery-related research and ecological research, such as doing kind of like salmon estimation surveys in Alaska, as well as to identify and quantify sharks, eels, and even crocodiles in nearshore habitats. So for us at In-Water Research Group, which is located just south of here, we proposed the use of an ARIS Explorer 3000 camera and an AR2 tilt and roll unit to detect sea turtles in nearshore habitats, basically by either tethering the camera to a vessel or mounting it to a stationary platform such as like a dock. So our ultimate goal is to determine how effective ARIS is at identifying and estimating the abundance of sea turtles and other marine life in the IRL. So some early results. So turtle identification is possible, but it's fairly challenging. As you can hopefully make out the turtles in the top two images, the quality really depends on not just the speed, the size, and the orientation of the turtle, but also the velocity and the angle the camera is directed at. However, animals in slow-moving currents, or even better yet, swimming upstream, detections can be made with much greater accuracy, as you can see by the images of the nurse shark and the Goliath grouper. So both of these facts kind of reinforce the need for ARIS to be either stationary or mounted on a very slow-moving vessel. I have 3 to 5 knots, but it really should be under 3, maybe 2 to 3 knots at the most. And then for us at In-Water Research Group, our future applications include pairing ARIS with in-water abundance surveys to kind of assist in visual observations, as well as to develop an automated detection system to make data collection a lot more efficient and a lot more easier on us sonar techs. So thank you to all of the people that make this project possible, as well as everybody at In-Water Research Group and the sonar team. And yeah, thank you.
All right, we have our last 3 minutes to talk in our last presentation for the morning. Brooke Davis will be discussing Eye in the Sky, exploring drone technologies for assessing body condition of bottlenose dolphins in the southern Indian River Lagoon, Florida.
Hi everyone, my name is Brooke and I'm part of the marine mammal team here at Harbor Branch, and today I'm going to talk to you about how we are using drones to study our dolphins in the southern portion of the Indian River Lagoon. Bottlenose dolphins are a sentinel species, meaning their health can reflect the health of their environment and also indicate risks to human health. This specific stock of dolphins in the Indian River is important to study as they have experienced several unusual mortality events in the previous few decades. In order to study body condition, you can look at morphometric measurements such as widths, and at this moment we have only been able to do that in the southern Indian River Lagoon through stranding of dead animals or capture and release of live animals. So the objective of our program is to use drones as a non-invasive method for estimating morphometric measurements of these southern IRLES dolphins. Our study area is the Sebastian Inlet to Jupiter Inlet, and our goal is to fly our Skydio 2+ Enterprise drone over groups of surfacing animals to collect aerial imagery. The drone will also have a laser altimeter attached in order to gather precise altitude readings. This aerial imagery, in combination with the altitude readings, can be put into a program called Morphometrics in order to estimate morphometric readings such as lengths and widths. We are at the very beginning stages of this project, and so far we have collected drone imagery of 2 carcasses, which we look forward to using for calibrating our measurements since we have the known length of the dead animals to our estimated morphometric measurements. And we've also flown over 15 live animals. We did fly over one of our animals named Stitch, which is an interesting animal because back in 2014, she was entangled in fishing gear. She was caught, disentangled, and released. During this rescue effort, they did measure her, so we are looking forward to confirming or seeing how much she's grown in the past 12 years once we get our drone estimated total length. Both of these methods are challenging in their own ways. Measuring a live animal in a capture is not easy, especially in the water. And then, of course, with a drone, there can be challenges including image quality, water distortion, environmental conditions for flying the drone. We look forward to applying these drone estimated morphometric measurements to body condition analyses. We also hope to compare these estimates to historical capture and release data, and we look forward to hopefully being able to use these measurements to determine age class of our animals when flying over them. And with that, I'd like to thank all the people on this slide with a special mention to Elena Robertson and Lauren Clance. Thank you.
All right, great job, everybody. That was a great first session for 3-minute talks. That is the standard to follow. And can we just give a round of applause to all of our morning presenters? You all did a fantastic job. Okay, so we have a little bit of housekeeping before we break for lunch. First, if you can please try and give priority to the student poster presenters in terms of the lunch line, that would be really nice so they have time to eat and then can go and stand by their posters. Student poster presenters, that's when those name badge ribbons really come in handy. You can just flash those around a little bit and see if you can squeeze your way to the front of the line. The lunch today is box lunches from Publix. They contain either a sandwich or salad, your kind of snack or side, as well as a beverage. If you don't like the beverage that's in the bin, you're more than welcome to trade around, but we also have extra sodas and sparkling water in the coolers at the end. If you're not interested in that bottle that's in your box, if you can put it in the cooler, and we can kind of all trade around. There will be 2 lines, and it's going to be the same thing on each line, so feel free to do that. There is a dedicated table on the far side of the gallery for any of those who have any dietary restrictions. That's going to have the strawberry salad, I think it's the Caesar, and the wrap. And if you did register with a dietary restriction, it's going to be on a little underneath your name badge, if that helps. And then let's see. Yes, and so with the strawberry pecan salad, we have it listed as vegan, but we do have a side of cheese and pecans if you would like to, if you're a vegetarian and would like to include that in your meal. Enough about lunch. If you have not loaded your talk for the afternoon sessions, please do so at lunch. And let's see, steering committee, if you guys can stick around right after we're finished, we're going to finally try and get that picture for this year. And if not, I'll see you back at 1:30. And just remember, please try to let the student presenters get to the front of the line. All right, thank you.
Can anybody hear me? Now. Good afternoon, everyone. Welcome back from lunch. We have about a minute and 30 seconds left, so go ahead and find a seat. We'll get started. I'll bring it up, yeah. You can stand right here, though. That's fine. Okay, everyone, we're going to get started. This next session is going to be on molecular innovation. And to get us started, we're going to hear from Kathleen, who's going to talk to us about detecting saxotoxin in pyridinium.
All right. Hello. Thank you, everyone. Good to be here. So I'm going to talk to you about a molecular diagnostic assay that we've developed for detecting whether pyridinium bahamense blooms are toxic or not. I'm sure most of you are familiar with pyridinium bahamense. It's a toxic bioluminescent dinoflagellate. It forms annual recurring blooms in the northern Indian River Lagoon, produces the potent neurotoxin saxotoxin. And so my lab sampled several sites in the northern IRL over several seasons, right? Beacon 42, which is in the Mosquito Lagoon, Haulover Canal near the Indian River, and then Kelly Park and Diamond Bay down in the Banana River, and measuring toxicity via the ELISA, enzyme-linked immunosorbent assay, right, which is for, it's called the ELISA PST, detecting paralytic shellfish toxins. Really, it measures saxotoxin, which is the parent congener, and then one other congener at low percentage. But the point I want to make is that sampling at these different sites, and the x-axis is just different dates at Diamond Bay, Kelly Park, Haulover Canal, and B42, normalized as picograms per cell, that toxicity is dynamic and it varies by location. So I'm not defining these as pyridinium blooms, I'm calling them populations, okay? Because we're going out sampling on different dates. It's not like, oh, we know there's a bloom occurring. We're just sampling these populations. Toxicity is dynamic and changes based on location. And then it also varies daily. Down here, this is just showing you Diamond Bay for a bunch of different samplings. And then this is just Kelly Park for 3 dates in March. And you can see, compared to Diamond Bay, again, toxicity varies. So now I want to give you just a brief background on saxotoxin biosynthesis in dinoflagellates. The starting enzyme is SXTA. It can occur in 2 isoforms. SXTA123 are the genes, and these occur in non-toxic strains and species as well, right? So you have these SXTA123 genes out there in non-toxic species. Species that produce saxotoxin have this 4th gene. SXTA4 codes for the 4th domain of this overall unique starting enzyme. And overall, an organism's response to changes in its environment or genes that are involved in biosynthetic pathways, we can measure them by changes in transcription or their transcripts. So measuring these SXTA4 transcripts is indicative of whether the cells are producing toxin or not actively. Is that population at that time producing toxin? Are we collecting SXTA4 transcripts? And so this graph is just showing you the toxin quota per cell, again at, this is actually Diamond Bay, Kelly Park, over time, using the ELISA, and then using an SXTA4 specific quantitative PCR assay, which I'm not going to go into detail on, but you can see, okay, they line up. And there was even one date where the molecular assay detected the SXTA4 transcripts and the toxin didn't. That's because there are all these other different congeners and they need SXTA4 to be produced. So the ELISA may miss them. So nucleic acid sequence-based amplification is a type of isothermal amplification method, and it's an emerging field for environmental testing. Isothermal means it can be one at one temperature. So this one you run at 41 degrees C. Couple it with a fluorescent tag, you get this binary readout, yes, no, the target is present. So here's a schematic of this SXTA4 NASBA assay. You have pyridinium cells producing saxotoxin, so they're making RNAs. I won't go into details of the whole NASBA enzymatic reaction. I have it on the next slide in case you have questions. But basically, there are 3 enzymes involved, and there is a fluorescent tag in there that will bind to these transcripts, with the end result being, if you get fluorescence, you know that there's transcripts, you know that the cells were producing toxin. No fluorescence, no toxin. That's in case anybody has questions on the overall NASBA reaction. I mean, it's used for other things as well. So let me show you a little bit about the assay sensitivity. This is just showing you some fluorescent figures on the instrument that I used. This, if you use a fluorescent tag, in theory, you can use any instrument that's capable of detecting fluorescence. But for me, I was trying to figure out different values, so I was using a nicer instrument. But I made dilutions of the in vitro transcribed standard, which is, a mimic of that SXTA4 transcript. And then using this, I found that the assay could reliably detect down to 37.5 transcripts per microliter. Now, when you have a bloom of pyridinium cells, they are producing many more transcripts than that per microliter. So do we even really need that level of sensitivity? But for right now, it can detect down to 37.5. I show you the transcripts per microliter and their corresponding CT value. CT stands for threshold cycle. That is the measurement at which the fluorescence rises above the baseline. So the lower the CT value, the higher, the earlier the fluorescence is coming out, indicative of more of that target. And so, all right, we've done the standard. We figured out it can detect down to this many transcripts. I then applied it to a few field samples, TM, Titusville Marina, DB, Diamond Bay. This is the ELISA picograms per cell. And then what I'm showing you are the NASBA fluorescent values. And what undiluted 1 to 5 and 1 to 10 are when you take that water sample, you extract the RNA. If you don't dilute it, but you put it right in the reaction, you could see that you're not getting much fluorescence at all. You need to dilute it several times. So that is actually indicative of other contaminants there in that water sample that were inhibiting the reaction. So you're diluting them out, and then you're getting some very nice fluorescent values. But overall, this is to show that the SXTA4 NASBA can serve as a molecular diagnostic to identify active toxin production in Pyridinium bahamensi populations. So unlike the ELISA where you would be using that for shellfish and, okay, let's see if the toxin is there, but how long has it been there? Now you know what's out there that day, you collect it, extract the RNA, and if you get signal, okay, they are producing toxin. And I see that I have 30 seconds left, so I just wanted to give you also an example of what these dilutions look like in terms of the fluorescence. And you can see along the x-axis, that's the threshold cycle, the CT at which they come out. And so this was diluting the one environmental sample more and more. So as you make more dilutions, you get higher fluorescence. Okay, so that's my 8 minutes. And I will take any questions that anybody has. Oh, and also, let me just leave up my acknowledgements. Indian River Lagoon National Estuary Program. Life Sciences Advanced Technologies are the ones that supplied the kits. And the Boyer Lab did the toxin analysis. All right.
All right, thanks, Kathleen. We have time for one question, if anybody has a question. All the way in the back there.
Oh, it's a commercially available kit that's used very frequently for measuring for saxotoxin and the other paralytic shellfish toxins. It's by Abraxis. It's called the ELISA, the PST ELISA. Commercially available, Abraxis.
All right, thanks, Kathleen. And before we move on, I forgot to make an announcement. If you all were judging the 3-minute presentations and you had trouble with the form, that issue has been fixed, so go ahead and log back in and you should be able to complete that now. All right, so next up we have Jackie, and she's going to be talking to us about phytoplankton bacterial interactions and pyridinium as a case study.
All right.
We're finding that bacteria are significant influencers of phytoplankton physiology, and so they can have either beneficial interactions with their phytoplankton partners, like you see here. So for example, some bacteria can make vitamin B12, which phytoplankton can sometimes not make themselves. So you can see how these might be helpful in bloom formation or persistence. And then they can also have negative interactions, like some bacteria can produce algicides, which kill and lyse the phytoplankton, causing bloom collapse. And so we want to know who these bacteria are and how they're functioning in the environment with these phytoplankton, and this can help us with prediction and management strategies for these blooms, and specifically harmful algal blooms. So we have several different genomic techniques that we can use to look into who these bacteria are. And the first, it would be a culture-dependent method. So we can take a water sample and we can culture it on a nutrient plate and then do whole genome sequencing. And this will give us a complete or a draft genome of this bacteria, and we can look at genes, pathways, and functions of the bacteria. It enables experimental follow-up, but obviously this will have culture bias. Only or less than 2% of bacteria are actually culturable from the environment. So to look at those unculturable bacteria, we can do culture-independent methods. So we extract the DNA from these complex water samples, and we can do amplicon sequencing to look at the different taxa in these mixed samples. And so this is sequencing the universal gene in bacteria called the 16S gene, and it has variable regions that are different between different taxa, and this allows us to see what the different taxa are in a mixed sample. And so here we can get relative abundance of different taxa in a community and their structure. We can look at the difference between these different samples for diversity, and I'll show you some examples of that. This is a low-cost method, and it requires low data requirements, but we only get genus-level identification of these bacteria in these samples, and we don't get any functional information. And then the third thing we can do is shotgun metagenomics, and so this is taking the DNA from a mixed sample and sequencing everything. So we can get metagenome, assembled genomes from virus, bacteria, phytoplankton, everything in the sample. And so we can get community composition and function from this. However, for these really complex water samples where there are millions of virus, million bacteria, thousands of phytoplankton, it requires a lot of data. And my friend Renee has said sometimes it's about 15 terabytes of data necessary for these samples. So you can see how that might not be advantageous for our study. So we ended up using whole genome sequencing and amplicon sequencing to enrich for those bacteria. So here's our case study for figuring out the bacterial associates with pyridinium in the IRL. So we collected whole water samples across the IRL, and here are the sites in the circles. And so we did 16S amplicon metagenomic sequencing of those mixed samples. And so that gives us a broad community level composition, but if we want to look specifically at what's associated with pyridinium, you have to isolate pyridinium in the lab, and bacteria come with the cells into your isolates. And so that's how we can look at more closely associated bacteria with our specific phytoplankton of interest. Sorry, this keeps going up. And then finally, we took these co-cultures and then tried to isolate bacteria on nutrient agar plates from those cultures and do whole genome sequencing so we can look at the function of those bacteria as well. And so here's an example of some of our surface water samples. You'll see on the y-axis is relative abundance of the different taxa in each of the samples, and the colors represent different genera in that sample. And I separated it here for dry and wet season, and so you can see that there is a difference between seasonality. But bloom presence here really didn't cause a large shift within that seasonal framework. And this can be because particle or phycosphere associated bacteria might be present at lower levels than free living bacteria. So we need to do a little bit more work on our methodology for collecting these samples. But when we looked at the composition of our isolates, one, you can see that the diversity of these samples, the taxa is a lot lower. but we looked for core or regular associates, and what we called this was a prevalence of greater than 80% within the isolates and a relative abundance greater than 0.25%. And so we found only one bacteria was actually part of our core, and this was Neowella, which you can see in the brown. So looking back into our water data, we actually found that Neowella was being found in many of the same samples as pyridinium. So you can see here, pyridinium really wasn't detected in the wet or the dry season, more so in the wet season in the northern IRL, and also Neowella was found in those same sites. And they had a co-occurrence percentage in these samples, so both of them were found at the same time in the same sample about 69% of the time. And so this gives us an idea that they might have a potential ecological association, but it might not be an obligate relationship. So while I have you here, I wanted to tell you about some challenges and considerations with looking at this type of data. So based on your primer choice, the classifiers you use, the databases you use, this can assign the different taxa for your amplicon sequences differently. And so for our example, I kept finding a bacteria called Tropicomonas in my data. And then when I use a different classifier, it would be called Neowella. And so you kind of have to look at your methodology and make sure that you're confident in what they're being classified, your amplicon sequences. And then additionally, if you have low biomass samples, you really can have a risk of contamination or low confidence in what you're seeing. So we found that if you have below 10 to the 5th bacteria in your sample, then you're a lot less confident in those low abundance taxa. And additionally, it's important to include the correct controls. So for example, we spiked our control with Streptomyces lividans, and we're hoping to find almost 100% abundance for this one bacteria, but we did detect some additional bacteria. So it's really important for you to define a level of confident detection for these low abundance bacteria. And then, so finally, this is just a look into our whole genome sequencing work. So as I said, Neowella seems to be kind of an interesting player in this pyridinium story. And so what we found was that when we look at the whole genome of Neowella, we can look for specific interactions between pyridinium that might be helping or inhibiting its growth in the IRL. And then additionally, by having these in culture, we can do simplified community growth curve analysis. So essentially, I have bacteria-free pyridinium cultures where I can add single bacteria back in. And what I've found is Neowella actually seems to have a slight negative relationship with pyridinium, which is quite interesting. So my conclusions are Neowella seems to be a consistent non-obligate associate in culture-based and environmental data sets. So we're really interested in this bacteria and its relationship with pyridinium. We want to continue our co-culture work and look into transcriptomics to see what the interactions and metabolic exchange might be between this bacteria and pyridinium. We also want to look at community and transcriptomics shifts across a bloom as well, because all of these were really single samples of a bloom and not during the bloom progression. We also want to look into size fractionation. As I said, the particle-associated bacteria or phycosphere-associated bacteria might have been lower in abundance, and we're not seeing that in our water sample data as well. And then finally look into how nutrients might drive community changes as well in these populations. And hopefully use all of this for better prediction and management strategies for these important phytoplankton blooms. And so with that, I'll take any questions.
All right, thank you, Jackie. We do have time for one question again, if anybody has one. All right, you can catch Jackie at the break. Okay, we're gonna move on and switch gears a little bit. Matthew's gonna talk to us a little bit about marine mammals.
All right, hi everybody. My name is Matt. I'm a research scientist here at Harbor Branch. Started about 9 months ago, and I am very happy to be joining this IRL community of practice. So I'm going to talk to you about PFASs and marine mammals. So PFASs are per and polyfluoroalkyl substances. You also might see it written out as PFAS. They are synthetic chemicals that were developed in the 1940s, and they have very exceptional water and grease-resistant properties. And because of that, they're used in a ton of different industrial and consumer products. Have a picture here of some of the things that they're used in, like firefighting foams, paints, cosmetics, food packaging. Some of the brand names that you might be aware of are like Teflon, and, or not Teflon. Teflon, sorry. It's been a long day. Okay, so PFASs are in the environment because of these water and grease-resistant properties. They stick around. They're known as forever chemicals. And because of their ability to just stick around forever, they become globally distributed in the air, in soil, and in water. So they also become available to biological critters like us, and they accumulate in protein-rich tissues. And they also have known toxic effects like immunotoxicology, endocrine disruption, and liver dysfunction. So marine mammals like toothed whales, another word for toothed whales is odontocetes, which you'll see me write later. Marine mammals are long-lived, high trophic level predators and are sentinels for ecosystem health. Harbor Branch here operates a long-term, long-lasting marine mammal stranding program that has monitored the health and contaminant exposure of marine mammals, odontocetes, for many years. And they also maintain a comprehensive tissue archive from these strandings. PFASs have been documented in blood samples from live bottlenose dolphins here in the Indian River Lagoon in short-term studies. But to date, there has not been any multi-species, multi-decadal studies of PFASs in Florida odontocetes until now. So the purpose of the study that I'm talking about here today is to quantify liver PFASs in Florida stranded odontocetes. Like I said, liver is a high protein tissue, so that's where it accumulates. I want to compare PFAS profiles and total concentrations among multiple species using this archival data set. And I also want to evaluate temporal trends over multiple decades. So liver samples were collected at postmortem exam from all of these animals. And in total, I had 85 strandings, which I have on this map here. And of those 85 strandings, they are grouped into 10 different species. And I zoom in on the southern Indian River Lagoon. That's where most of the samples came from. And like I mentioned, this is from 2005 to 2025, so over 2 decades. For the analysis, we performed ultra-performance liquid chromatography tandem mass spectrometry, which is a mouthful. That was performed by the Center for Environmental Sciences and Engineering up at the University of Connecticut. And for my statistical approach, because of the small number of strandings per species, we needed to bin the animals into 5 different groups. So we have Kogia species, so those are dwarf and pygmy sperm whales. We have our offshore dolphins. We have sperm whales, the big ones. We have common bottlenose dolphins, and we have beaked whales. And I just want to note that these diagrams are not to scale. So also, I needed to log transform the PFAS data, so you'll see that when I get to the graphs. I ran ANOVA and Tukey post hoc tests for the groups to look for differences among them, and also did linear regression for those temporal trends. So I'm going to start out showing you just a percentage composition for each of the 5 groups. And I want to mention that we looked at 28 different PFAS compounds, and of those, 18 were detected above the detection limit for the instrumentation. PFOS is the dominant PFAS for most of the groups, for 4 of the 5. And that is despite a global phase out of this PFAS back in the early 2000s, so over 20 years ago, but it still remains prevalent. And also want to mention that beaked whales, for some reason, also have this other PFOS that is of high contribution to their profile, PFUNA. So looking at the concentration of total PFOSs amongst the groups, there was a strong statistical difference between the groups. And Kogia, so the dwarf and pygmy sperm whales, they had the lowest concentrations of the 5 groups that we looked at. And I also want to highlight, even though it's not statistically different from the other groups, bottlenose dolphins had the highest concentration. So now looking at the temporal trend, this is all 85 of my individuals over time. We do see a significant decline in total PFOSs over the 20-year study period with the regression slope listed there. And this decline is consistent with the decline in production of PFOSs around the world. I also broke this trend line up by the different groups. And it's showing the same trend that we saw before, that the Kogia had the lowest concentrations over time. Bottlenose dolphins also had the highest. I also do want to mention that the rate of decline was not different between the groups, just the intercept, just like the baseline for each of the 5 groups. Okay, so PFOSs are important because they accumulate in liver and impact immune and endocrine function. There's been previous studies that have shown that PFOSs are linked to immune response in bottlenose dolphins. And we do see that there is a high amount of PFOSs in these near-shore bottlenose dolphins, which may reflect high inputs of PFOSs into the IRL or into coastal Florida. Additionally, the dwarf and pygmy sperm whales having those lower burdens, that might be related to differences in diet or a different use of those offshore habitats compared to the other groups that I studied. And overall, this shows that marine mammals are good sentinel species for human health, especially those of us that live in coastal communities. So just to conclude here, that Florida odontocetes do show widespread long-term PFOS exposure, especially with PFOS being the dominant one. That is reflected in the literature for many other species as well. We did observe differences among the groups, and we did have a decline over the past 20 years, although the levels are still concerning that are in the newer animals. And odontocetes are good indicators of coastal and marine contamination, and this goes to show that straining response groups provide vital environmental monitoring data, and these are programs that should continue to be funded in the future and have these well-maintained tissue archives that we can use for studies in the future. So I want to thank the marine mammal stranding team here at Harbor Branch, as well as the technicians up at UConn who helped with this study, especially Chris, Wendy, and Savannah for their help with the samples. And I want to highlight the funding sources, the Protect Florida Whales and the Protect Wild Dolphins license plate funds. Thank you.
All right, thanks, Matt. We have time for a couple questions this time, if anybody has any. Yes.
Are the rates of decline that you're seeing in marine mammals similar to what's been shown in other large, vertebrate species, like terrestrial species? Is that rate of decline similar?
Yeah, it's pretty similar to what's been seen in other areas. There's been a study in Canada and the Mediterranean that's done similar work with marine mammals, and they've seen similar. But yeah, this is the first in the U.S. So.
All right, time for one more quick question, if anybody has one. All right, thanks, Matt.
Thank you.
And then to round out our session, we are going to hear from Jessica, and she's going to talk to us about eDNA for benthic monitoring in the IRL.
Hi, my name is Jessica Zanfenig. I'm a postdoc at the Smithsonian Marine Station, and as Hallie said, I'm going to talk about some eDNA work that I've been doing. So before we talk about eDNA, I want to start with introducing a little bit of what Holly's lab does at the Smithsonian Marine Station, the benthic ecology lab, partners with the Comprehensive Everglade Restoration Plan, or SERP, and the benthic infaunal monitoring program. So this is a long-term monitoring program that has been conducted since 2005, so over 20 years now. And what they do is they go out every quarter and they collect samples, and they use an index called the MAMBI, or Multivariate at-sea Marine Biotic Index, that was established by Borja et al. In 2004. And what that does is it integrates species richness, channel diversity, and ecological tolerance structure into this index that can be used then with these salinity-specific reference conditions. So as everybody knows, we have different salinities in the Indian River Lagoon, so each salinity has a different reference condition. And what they do is they collect benthic infaunal species, and these species are ranked on sensitivity from 1 to 5, 1 being the most sensitive, 5 being the most opportunistic. And they put it into this index, and it gives you benthic condition assessments. So these condition assessments are kind of like a report card, as you can see on that map. And those report cards can be great, an A, or you can get a F score. F is pretty bad benthic condition. And they do this by manually going out. They have to manually sort and taxonomically identify these infaunal creatures, which takes a lot of time. And this is where I'm going to bring in environmental DNA now. So environmental DNA, my specialty eDNA, is organismal DNA that's found in the environment, and it originates from material that's been shed from organisms. So to do that, we go out, we collect our sample, we extract DNA from that environmental sample, and then we use PCR to target a barcode region of different genes. So usually it's a CO1 or nuclear ribosomal ITS gene that gets put through sequencing, and then through bioinformatic analyses you can get amplicon sequence variants, which then have you can assign with taxonomy and look at diversity. So my project and what I do is I look to see if we can use eDNA sampling to enhance these monitoring efforts. So since I started in June of 2024, I've gone out and collected quarterly eDNA sampling with the Comprehensive Everglades Restoration Plan's long-term benthic infaunal monitoring programs. So we go through 15 sites from the Fort Pierce Inlet to the St. Lucie Estuary. And if we can use eDNA, then we can expand these monitoring sites and allow for more rapid eDNA monitoring. So there's a lot of potential there. So what I'm going to do now is I'm going to introduce some of these salinity regimes that I mentioned earlier, and then I'm going to talk about some of the traditional monitoring from our October legacy data. So we go out every quarter, and this is the October quarter, and the legacy data I'm talking about goes from October 2005 to October 2022. So each of our sites are classified in a salinity regime. We have euhaline salinity, which is a 30 to 40 part per thousand, polyhaline salinity regime, mesohaline, and then oligohaline, which is our freshest freshwater sites that we have, more freshwater sites. And what we've done is we've looked through, and I've calculated all of these rings are the proportion of those October sampling dates with that letter grade that they've assigned through their traditional monitoring. So as you can see, our euhaline sites are usually pretty healthy compared to our oligohaline sites, our freshwater sites, which have a less healthy grade most of the time. So what we do, I went out, this is, like I said, the October 2024 season. We went out at each site. We have 15 sites, so we did 3 reps per site. And we took petite ponograbs, sieved them, preserved them. I took them back to the lab, processed them, and extracted them with our QIAGEN D&EZ Power Max soil kit. We sequenced them on an Illumina platform, and then I put it through a pipeline. Taxonomically identified those ASVs using the BLAST in our database. And then I looked for the invertebrate matches that assigned applicable AMBI designations to anything that was an invertebrate match. And then I put that in our AMBI or MAMBI software using the relative abundance of sequencing reads per sample to see if I could get the same kind of score that they were getting. So this is going to be a very similar slide, but the change is that the middle circles are now eDNA, the eDNA score that I got in the AMBI software versus the legacy data proportions on the outside. So if we go through all of our salinity regimes, we can see that our euhaline sites, I'm actually getting kind of a lower score for most of them. Some of them are pretty like this M13 site's pretty relatively good, but most of the time I have a lower score than normal, but it's not abnormal to see some of those B ratings. The polyhaline sites, I actually had like a lower score than normal as well. The mesohaline, I had a higher than oftenly observed score. And then our oligahalines, I also had a higher than often observed score with the eDNA data. So this led up to the question that I'm asking was, why did the estuarine sites, those mesohaline and oligohaline, have the higher genetic M and B scores compared to legacy data? So I did some research. These are these sites, sorry, the ones that I already just went through. So I did some research and I found some studies that saw eDNA methods detected higher species richness and diversity in estuarine sites. Like I said, that M and B score uses species richness and diversity. So then I asked the question, what happens if we increase the expected diversity and species richness in the estuarine sites for these genetic M and B index scores? And when I did that, I saw that the scores for the estuarine sites resulted in scores that were more closely aligned with the October legacy data. So this was before on the left, and then on the right we can see our after sites, and you can see that these scores that I'm getting for the eDNA are a lot more closely aligned. So the next question was, why do the higher salinity sites, our euhaline and polyhaline sites, have a lower genetic M and B score compared to our legacy data? So those are those sites that are in the euhaline and polyhaline sites that I already mentioned. And I did more research, and I saw that sometimes eDNA methods actually detect a lower species richness and diversity in higher salinity sites. So this first study found that they actually had a higher diversity in their morphological data. And then I also found another site that says there's large gaps in the reference libraries, and these gaps could be accounting for some of that because, as you know, we have to taxonomically identify these animals, and if you don't have a good species level name or even a family level name, then you can't get a good score. So what happens when we decrease expected diversity and richness for these salinity sites in the AMB index? So actually what I found was decreasing the species richness and species diversity metrics in our software for those sites actually had those scores more closely aligned with our October legacy data. So if you can see before, once again, after, those legacy data sites in my eDNA are way more closely aligning, except for M5, which we're still investigating. I'll touch on that a little later. So that's great because this is legacy data, like I said, from 2022 or 2005 to 2022. But how do they look compared to our SERP traditional monitoring data for October of 2024? So we actually have 4 sites that have been processed, and 1 from each of our salinity regimes. So our euhaline site is M12 at that top. Our polyhaline site was M8 in the bottom, and then we have M4, which is our mesohaline site, and M1, which is our oligohaline site. And this table here, I'm going to go through each one of our salinities really quick. This table here has the original eDNA score, our adjusted eDNA score after I've adjusted the index, the legacy data averages, and then our traditional monitoring score for 2024. So what is important to note is that, yes, while our MAB scores are slightly different between our adjusted eDNA and our traditional data, they still are giving a similar score once we look at it overall on that status. It's still an A. Same with our polyhaline site, M8. Originally, that eDNA site did give me an ecological status score of B, but after I adjusted it, we got an A, which is closely aligned with our legacy data and our traditional monitoring data. Our mesohaline site, M4. So one thing to note in our M4 is with traditional monitoring, it did not validate in the AMB software because the AMB software needs a certain number of species, and if you have too low a proportion of species, you won't get an AMB score. But when we ran it with our adjusted eDNA, we still got the same, we got a D level score, which is closely aligned with our October legacy data. And then last but not least, our oligohaline site, which is our M1 site. Like I said, we still got a very similar score, even if the AMB score is not exactly the same. It's very similar, actually, very closely aligned to our legacy data and our traditional data. So once adjusted, our eDNA M AMB results show promising results compared to our traditional monitoring for our October stuff. What's next? Compare all the October 2024 sites to the rest of the sites, analyze more sampling periods, and look for better build more comprehensive reference libraries, so better resolution for our sites. This is M8, that's one of those polyhaline sites. I just want to say the total of reads that were classified as unknown or at a phylum level were about 50% for all the reads, and that'll help define AMB reference conditions for high salinity regimes. These are my announcements. I don't know if I have time. I'm probably pretty close, so.
You have time for one quick question.
All right. What do you mean by hydrodynamics? Hydrodynamics, sorry. Not yet. But we do take them from the benthics, so it's a benthic grab. So I don't know how much wind direction would affect that, but it might. It's something to definitely look into.
All right, thanks,
Cool.
Jessica.
Yep. Oh, I had a question slide, but
We're gonna roll right into our next session, our 3 minutes, 3 slides with Irene.
Okay, first up we have Charles Dante Romero presenting on development of underwater camera systems to evaluate ecological conditions and habitat restoration sites.
Hello everyone, my name is Dante. I'm a master's student at Florida Tech studying biological oceanography. I am currently working on the Living Docks Habitat Restoration Initiative, which engages the community to modify existing structures to improve coastal ecosystems in the Indian River Lagoon. Research conducted in Dr. Kelly Hunsucker's lab has already shown that oyster mats are effective at recruiting benthic filter-feeding organisms, which you can see here on the left, thereby improving water quality. That being said, the ecological impact of living docks on more active members of the food web, such as fish, crab, and shrimp, is less understood. Specifically, I am looking to determine if living docks increase biodiversity by determining how these organisms interact with the benthic communities growing on these altered piles. Most of the previous research on similar topics was collected by physically catching fish and invertebrates using gill nets and lift nets, but this disturbs the habitat and might deter animals from visiting in the future. My theory for evaluating the living docks' ecological impact involves non-invasively observing and quantifying the various mobile animals that visit the dock for habitat and feeding purposes using deployable underwater cameras. The biggest challenge with that is the limited visibility in the IRL, as you can see in these images to the right. Last fall, I tried using a GoPro with colored lenses to test the theory presented by camera and diving companies that magenta lenses improve visibility in murky water. Long story short, there were no significant benefits to using a magenta lens. From that project, I determined that water column particles and plankton, otherwise known as turbidity, has a more significant impact on visibility than watercolor. So a physical barrier might help increase the image range and quality. I also learned that action cameras did not deter fish from visiting, which suggests that the cameras were non-invasive, and that GoPros are terrible on battery life. From there, I drew out plans for a new concept. I borrowed an idea from a previous paper from our lab that allows divers to photograph vessel biofouling in murky water through a freshwater medium and redesigned it to work with an action camera. This will add a barrier from physical particles, reducing the turbidity between the camera lens and the living dock, which would increase our ability to see smaller animals with better resolution and prevent biofilm from damaging the camera. Instead of a GoPro, I selected a new camera that will allow for multiple hours of recording time and reports faster autofocus, counteracting the effects of excessive camera movement. I worked closely with the Florida Tech Student Design Center to bring my idea to life, and we plan to launch its first test runs later this month. Thank you.
Next up, we have Michelle Krumholz presenting on investigating stainless steel attachment materials for living docks.
Hello, my name is Michelle Krumholz, and I'm going to be talking about my investigation into stainless steel attached materials for the Living Docks benthic restoration mats in the IRL. First off, the Living Docks program is a citizen science oyster restoration project that started in 2013, which promotes benthic growth by utilizing artificial structures such as docks. This is executed with 60 to 80 dead dried oyster shells attached with UV-resistant plastic zip ties and 2 aquaculture-grade plastic mesh. This is then wrapped around dock pilings. As you can see in this map up here, these oyster mats are located in 3 counties and on over 50 docks. Recently, interest in the use of non-plastic alternatives has become a focus in this program. In previous research by Florida Tech investigated non-plastic alternatives such as bees, coconut coir, jute, and stainless steel. The only material that was successful was this 316L 22-gauge stainless steel wire. This has led into my thesis project looking into different stainless steel attachment materials. A few preliminary studies were conducted looking at 316 stainless steel cable ties and 316L stainless steel wires ranging from 16 gauge to 22 gauge. You can see in this photo on the right, the first part of it is the plastic zip tie, which we use as our control, and in the middle is our stainless steel 18 gauge wire, and on the right is the cable tie. This led into my This led into my 6-month study analyzing the impacts of different environmental conditions on the durability of 316L 18 gauge wire and 316 stainless steel cable ties. 4 locations were chosen, 2 locations with unprotected and high salinity dock waters, and 2 locations with protected docks with low salinity waters, ranging in the Indian River Lagoon from Melbourne to Vero Beach. You can see on this map right over here. At each location, there are 12 mats with 4 mats of each material. Continuing on to benthic growth and material assessment, after 3 months, almost all material has stayed attached. In the left picture on the bottom, you can see the damage caused by the stainless steel cable ties to the mat. This happened 2 times. Also, in the 4 pictures on the right, you can see abundant benthic growth such as oyster growth, tunicates, and mobile organisms such as snails. And then in the picture in the middle, you can see a representative mat after 3 months. In future work, we'll continue to assess until April, and then we'll also incorporate stainless steel material into installations. Thank you.
Up next, we have Chris Bogdan, Beyond Rocks and Revetments, Innovative Reef Arches for Coastal Resilience.
Probably freaking you out coming from over here. Hello, good afternoon. My name is Chris Bogdan. I work with Ferguson Waterworks, and we provide all kinds of different products to help manage stormwater and erosion control. And that's what brings me here to talk to you today about these innovative reef arch products that we're using as coastal breakwaters. And that guy's not working. So think about how we've done this forever and ever. Gray infrastructure, let's just throw a bunch of rocks up on a bank. More specifically, breakwaters. We build rocks, use rocks to build breakwaters. Typically, these things are placed parallel to the shoreline. They're done that way because we want to prevent erosion, right? These things present a lot of challenges, particularly rocks roll, so they don't last long in big storms, but they also really don't do much for the environment. So we've got some great new products that offer new opportunities here. So when we take a little bit closer look at these rock walls, we think about rocks are very difficult to transport, very expensive to pull out of the ground, bad for CO2 in the environment, a very limited surface area for things to grow on. Limited water exchange, so water doesn't move very well through them. They're difficult to install. There's minimal marine habitat with these rocks, and they roll, as we saw in the last slides. Ultimately, I like to say we're ultimately building a wall with these things. We're separating the marine environment from the coastline, and that's important that those things are there. So Mother Nature's been doing this for a very long time, right? We see these oyster sills. We've heard a lot about these things and the benefits they provide. Dissipate wave energy. All these structures, all these things are essentially put in place to prevent coastal erosion. But these don't cause habitat fragmentation. They actually provide habitat and clean and filter water. So how do we mimic what Mother Nature's been doing for living shorelines? Introducing reef arches. These are concrete structures. They're 1,200 pounds. They sit in the water. You can see they're open, so water can freely move through them. They're not disrupting the environment. They stack, makes them really easy and simple to transport. Very easy to install. You can install them by land, by air, by water, which is pretty cool. They're made from pH neutral material. That's really, really critical when you talk about things being able to grow onto these things. We want to see oysters, we want to see clams, and that can happen on these structures. And the coolest part is they give us that living infrastructure opportunity, that living plants behind them. Love mangroves, that mangroves can actually grow through these things when they do their natural things. So Mother Nature can take over the environment. And this is a project we did up in Indian River Lagoon. You can see at installation in March, no sand or sediment behind these things. In June, we accrued over 16 inches of sediment. We were able to plant mangroves behind these things, and we've got a really cool living shoreline now that's protecting a big burial ground back there, or sorry, big shell mound back there. So that's it. Thank you.
Next up, we have Lori Morris. What happens when Caulerpa prolifera becomes less prolific?
Ooh, so I can start talking now because my slides aren't up. Okay, so I'm going to... I threw up our graph for seagrass up there just to kind of give you, I've got to show you that, yes, we are seeing some recovery. This last bit, this is last summer's transect, so the black line is transect length, woohoo. Even the gray line, percent cover, so the beds are starting to fill in. But right now, today, we're going to be talking more about that percent cover line. I did kind of say if we're going to project the 25 maps, they will be more than 23, but I can't tell you that till spring. Okay, moving on to Caulerpa. Just a quick thing, look up in the top left corner, reminding you of a system. If you have a seagrass-dominated system, it can stay that way. But under increasing nutrients and decreasing light, your system can flip to a phytoplankton system, and that's exactly what we saw happen into our system. So after the 2011 blooms, we saw the system flip and become less seagrass dominated and into a phytoplankton. So this is taking our seagrass and macroalgae data from our transects, converting it to grams carbon per meter square. Dr. Ed Flipp's lab at UF provided the phytoplankton data, also in grams carbon per meter square. So this is kind of where I left you off last year. We said if I stacked all those three primary producers, we would kind of look like the system holds a certain amount. But there was a disconnect these last couple of years. So what was filling that void? And we hypothesized that it was probably Caulerpa prolifera. Yes, technically a macroalgae, but we monitor it differently because it's an attached benthic algae and not drifting around. So now I have some data to show you. So in 23, we were able to map the presence of prolifera. So in this footprint alone, you can see that we actually had twice as much Caulerpa prolifera mapped than the seagrass. Also note, that bar that I pop up there doesn't mean that there's seagrass everywhere in the lagoon. A mapped seagrass is mostly up in Mosquito Lagoon right now. Keep that in the back of your head. Okay, so with the help of my other co-author, Luciana, I was able to get the biomass data. I can convert my Caulerpa data to biomass and also add that to the chart in grams carbon per meter square. And so, yes, we are filling those last couple of years with all that Caulerpa. But if you look here, Caulerpa prolifera all of a sudden became very less prolific in 2025, and we saw a big crash. So what happens then? So here I've put 23 seagrass and Caulerpa together on one map. Just for fun, look at 2009 to see what used to all be seagrass. Caulerpa loves that spot right now. But along came this summer, after 3 years of Caulerpa really being pretty prolific out there, finally we saw Alicia, our little slug that loves to suck the life out of Caulerpa. And it just decimated central area of Lagoon. And for the first time in 3 years, we started seeing some phytoplankton blooms, coincidentally, in the area where we saw the biggest losses of the Caulerpa beds. So now we have a new player in town, Caulerpa ashmeadii, have not been seen in 40 years up in the north, and to be continued. And thank you, everybody.
Up next, Ron Brockmeyer, accelerating coastal wetland restoration with improved construction technology.
So my name is Ron Brockmeyer. I work with the Water Management District. I do coastal wetland restoration. In the Indian River Lagoon, there were about 65,000 acres of wetlands historically. We've lost a bunch permanently to development, navigational dredging. Most of the rest have been impacted by mosquito control, source reduction methodologies, ditching. In the Indian River Lagoon, impounding takes up about 40,000 acres of those wetlands. They only need to be closed for mosquito control during the summer. And if there are culverts connecting them to the estuary, transient fish can get in and they do utilize them. We have reconnected by all entities about 26,000 acres. But where those impoundments are not needed for management or management is handled in a different way, we can either breach or restore them. Oops. So from 1999 to 2010, we did about 43 miles of impoundment dike. Cost about $10.50 a linear foot to do the restoration. You get about 6¼ acres per mile of wetland back. but you also enhance the hydrology of the impoundment, about 2,300 acres. Recently, we planned some similar projects and estimated the cost to be about $20 a linear foot. Equipment's more expensive, labor, fuel are all more expensive. So when we implemented those two projects, we ended up with 9 miles more dike restored, 50 acres of more wetland, another 2,300 acres enhanced hydrology. But because we required the contractors to use GPS-based leveling equipment on their grading, the bulldozers basically, that instrumentation allowed the contractors to set the blade at the target elevation and achieve that surface much more quickly. It was much more effective. We basically did all that was planned in those projects at about a third of the estimated cost. So one of the projects was like $6.35 a linear foot. The other one was about $5.40 a linear foot. And with the surplus funding, we will be able to do a minimum of 14 additional miles of dike, and that brings our total to about 65 miles of dike and 420 acres returned to wetland elevation, and somewhere between 5,000 and 6,000 acres enhanced.
Next up, we have Deanna Weber, an assessment of Rupia maritima in the Indian River Lagoon mosquito impoundment. It's a potential for seagrass restoration.
Okay, hi everybody, thank you for coming to my talk. As it suggested, I'm looking at Rupia maritima here in the IRL, and this project kind of has what it says on the tin. There's two major objectives: looking at seagrass monitoring in one of our IRL points on Beacon Point Preserve, and looking at, the second objective was looking at it in a mesocosm. So this is Beacon Point Preserve here. It is on the IRL, and we had two major sites, Northeast Pond and Clevelandton Creek, and there were permanent transects, which are these red horizontal lines running across both ponds, or both subsites. And at each site, we looked at percent cover of, again, Rupia maritima, water quality parameters, and the water depth at each site. And then our secondary objective, as I mentioned before, was looking at the mesocosm experiment, looking at Rupia maritima in the Seagrass nursery, specifically taking Rupia from these sites and bringing it back to Harbor Branch for our Seagrass nursery, looking at the biology, seed harvesting, and hopefully using it for future outplanting projects. So getting into it, the water quality and, monitoring that we did at Beacon Point showed a high biomass of seagrass at the beginning of each year with a decline in around June or July in both sites. And this is consistent across all 3 years. You can see it's kind of a wrapped diagram with the second year in medium blue and the last year in light blue. And even though there was no seagrass towards the end of each year, at the beginning of the new year, there was again a seagrass count until again June and July. And this is 2 months directly after the culverts were closed and they were flooded. I can't really go into all of what a mosquito impoundment flooding does, but basically a truncated version of it is it decreases water quality. The turbidity goes up, the pH goes down, and ignore this minor typo, but essentially the water quality decreases and seagrass cover decreases along with that. And this diagram shows the culverts closing in red and the decline in all of the different parameters, except for, of course, turbidity, which shot up, again, decrease in water quality. And eventually a decline in seagrass cover. Moving into the mesocosm experiment, we saw a decline again in seagrass towards the June and July section of the year. This was a direct copy to what happened at Beacon Point Preserve. So originally we thought it was a water quality issue. Now we began to realize that maybe it was just how Rupia is. And based on that, we decided that maybe Rupia just grows out of phase with the other species of seagrass that we see normally in the IRL. And we're hoping that we could use that as a kind of pioneer species since it can survive the less good water quality environments, and it grows out of phase with other species of seagrass. Maybe we can plant it before the other seagrasses come in and kind of prepare the environment for the other more delicate species of seagrass. And lastly, maybe we just needed better water quality to grow healthily in the IRL. So I'd like to thank everybody on this project. I'd like to thank U.S. Fish and Wildlife Service and the Indian River Land Trust, who owns Beacon Point, for allowing me to work on their land, and of course the HBRI team and Dr. Nathaniel Sack for starting this project. Thank you.
Next, we have a student presentation, Harrison Hobbs, investigating the drivers of seagrass recovery in Mosquito Lagoon.
I strive to bring that Lori Morris energy to the stage, but I'm only human. Good afternoon, everyone. My name's Harrison Hobbs. I don't think this is the right presentation. Harrison Hobbs. There it is. That's me. Awesome, guys. In early 2023, we documented a significant seagrass recovery in Mosquito Lagoon following more than a decade of regional decline. What you're seeing here is the system bouncing back sharply within a very short window, from late February into mid-March 2023. That rapid shift tells us that the lagoon still has the capacity for meaningful positive change when conditions align. This map here provides some orientation. We focus on South Mosquito Lagoon and compared water quality conditions before and during the recovery to North Indian River Lagoon as a reference system. So the first question that we asked was simple: relatively how much growth occurred and when did it take off? Here are two quick lines of evidence. On the left is a presence-absence analysis from a Sentinel-2 imagery time series. Positive detections rose from just a few hits in January to nearly 40% occurrence in mid-March. Roughly 40% increase in occurrence in just 6 weeks. This pins the onset of the recovery to late February into mid-March 2023. On the right, we bring in the in situ transect data. The seasonal transition from winter to summer 2023 produced about a 35% increase in mean seagrass cover, exceeding every prior year in the study by over 11%. This means that Mosquito Lagoon did indeed experience an unprecedented growth event as far as the scope of this study covers. Taken together, these independent data sets show that recovery was both rapid and substantial, not a marginal uptick. Which leads to our obvious question: what changed in Mosquito Lagoon to allow for this recovery? To answer that, we examined a suite of water quality drivers across the system. When we compared these parameters and modeled their effect on seagrass, salinity emerged as the strongest predictor of mean seagrass cover in Mosquito Lagoon. Salinity also showed the clearest separation between Mosquito Lagoon and the North IRL, leading up to and during the recovery window. Chlorophyll A showed a nonlinear relationship consistent with light limitation, particularly surrounding the recovery time. Temperature and turbidity played smaller roles in the models. The implication's practical here: stabilizing freshwater inputs to avoid abrupt salinity shifts and continuing to limit nutrient inputs that fuel phytoplankton-driven light limitation is likely to support sustained recovery. The broader takeaway is hopeful. The speed and magnitude of this response suggests that the system retained an underlying resilience that could be rapidly expressed once conditions align, and that argues for a targeted sub-lagoon specific management approach as opposed to one-size-fits-all solutions. So thanks to the St. John's River Water Quality Management team and the Salty Dogs, you guys know who you are. I'm surprised I still have time. Thank you.
Next up, we have Isabel Bennett, novel methods for identifying Haloduli redii flowers and seeds in seagrass nurseries.
Good afternoon, I'm Isabel. I'm with the Brevard Zoo Restore Our Shores program, and today I'm going to be talking about the methods we use to monitor Haloduli redii flowers and seeds in our seagrass nursery. So, sexual reproduction for Haloduli redii is not super well studied, especially in nursery environments. And this is largely due to flowering within nursery environments for this species being rare. So when a flowering event was identified within the Hub Seagrass Nursery last year, we knew it was important to develop methods to properly document that. So what we did was we got a 50 by 50 centimeter quadrat, so about a quarter meter squared, and we used that to visually monitor the flowers that we found there. So we set it down, counted all the flowers in shoots that were within there, identified the sex of those, and recorded that data. So later that spring, some mature fruits were identified in grass that was harvested for an outplanting project.
So that confirmed the fact that seed production was occurring within our nursery. So we decided to adapt methods that were being used for seed collection throughout the state in the field to our nursery setting to be able to quantify that seed production. So we used a 10 centimeter deep hand core made out of a 75 millimeter PVC, and we collected 10 cores from each of our nursery tanks. Those 10 cores formed one composite sample per tank. We then processed those samples through a 2 millimeter and a 1 millimeter mesh sieve, and then all the material retained by those sieves was visually examined, and any seeds we found were removed and counted. So what we found through this was that we had 32 total flowers within those quadrats during the time of our sampling. So that was about a mean of 2 of those flowers per tank at the time of the monitoring. All of the flowers that we identified at that time were male. However, we did identify female flowers outside of our monitoring event, so we did know they were there. So as for seeds, we found a total of 3 seeds between 2 tanks, and while that may not sound like a lot by the area sampled, that means we could have had approximately up to 90 seeds per tank in those tanks that did have seeds, so that's pretty exciting. As for our next steps, we do want to do some germination and flowering experiments now that we have some seeds to use, and as you can see there, pretty exciting. One of our seeds that we found has actually germinated, so that's pretty cool. We also hope to be able to share these methods with other nurseries that might have flowering and seeds going on, so we can, compare observations and help each other out in the future. Thank you.
Up next, we have a student presentation, Namrita Ramakrishnan. Beneath the blades, how seagrass alters waves and sediment transport.
Hello, everyone. My name is Namrita Ramakrishnan, and I'm a civil engineering master's student at the University of Central Florida. And I'll be the first to admit it, I'm probably one of the very few people in this room who can't tell you the difference between 2 species of fish or 2 species of algae just by looking at them. I'm an engineer, so to me, the lagoon isn't just a habitat, it's a high-energy environment where physics is constantly at work. We all know the Indian River Lagoon is struggling. We see the loss of Haliduli as a loss of biodiversity and a blow to the food web. But when we look at the same data, we can see something else. The removal of the lagoon's primary hydraulic brakes. Without these meadows, there is nothing to absorb the energy from boat wakes and wind. That energy must go somewhere, so it hits the bed, kicks up sediment, and causes the erosion we're all trying to stop. My goal isn't to tell you how the grass grows. I'll leave the biology to the many experts in this room. I'm here to show you how much work the seagrass is doing to keep our shorelines from washing away. I spent the better part of my 2025 in the mud of Mosquito Lagoon to capture a more complete picture of seagrass dynamics. Rather than relying solely on sensors, I synchronized high-frequency wave and turbidity data with manual density checks throughout the entire growth season. This dual approach allowed me to pinpoint the moment a grass patch became dense enough to change the water's behavior. We now have data to show how these meadows evolved to shield our coasts from everything from summer ripples to major storm events. So the picture here on the left shows us doing our density measurements, and then on the right you can see our sensor setup in Canaveral National Seashore. If you've been near Parking 5 and seen like random metal poles, hello. So what did those 8 months of data show? It turns out this shoalgrass patch was quietly doing some heavy lifting. The sensors picked up an 11% drop in wave height and an 18% reduction in overall energy compared to the bare site. But the sediment was the most big result. We saw a 36% reduction in suspended solids, with levels dropping from 46 milligrams per liter down to 29, just by being inside the grass. But most importantly, we saw that the denser the meadow was, the more protection benefit it provided. We also saw that during storms and higher frequency events, that the seagrass was working harder to attenuate those waves. As a starting point for my thesis, it's a nice confirmation that Haliduli radii is helping stabilize the lagoon, but this is just a snapshot. We have the baseline now, which leaves me with the much bigger question of how far that protection stretches when the environment gets less predictable. I'm looking forward to seeing where the rest of the data takes us. Thank you.
Okay, our last presentation for this block is also a student presentation. Taryn Chaya, Seasonal Biochemical Dynamics of Managed Mosquito Impoundments in the Indian River.
What if the same coastal wetlands that protect us from mosquitoes could also protect our estuaries from pollution? Freshwater treatment wetlands are a well-established method for treating water. They typically have an inflow and outflow with ways to control the hydrodynamics to promote mechanisms like sediment settling and denitrification. So what if this concept could be applied to coastal estuaries to reduce nutrient pollution? Most of the wetlands in the IRL were diked and impounded for mosquito impoundment back in the mid-20th century. So they have infrastructure that's actually pretty similar to a constructed treatment wetland. Hi everyone, my name is Taryn Chaya, and I'm a PhD candidate in Dr. Todd Osborne's Estuarine Biogeochemistry lab at UF. And I study the nutrient and water quality patterns of mosquito impoundments, which are natural wetlands that were converted for mosquito control. And today these impoundments are managed mostly with rotational impoundment management, where during the summertime, the culverts are closed and managers are pumping lagoon water into the wetland to flood the substrate that mosquitoes use to lay their eggs. And then in the cooler months, these culverts are opened and there's a restored connection with the lagoon. So this seasonal flooding and draining technique can have really interesting implications for the chemistry and the ecology of these wetlands. So my main research question right now is how do mosquito impoundment managers and management affect the nutrient and water quality patterns? And ultimately, I'm interested in seeing if they can act as coastal treatment wetlands. So to approach my research question, I've monitored several impoundments across the IRL. One example of a site is Ulame Wildlife Sanctuary in Mare Island. And I deployed instruments at the pumping station inflow area, as well as 2 culvert sites where the water can exit. And these instruments are measuring continuous water quality parameters. Weekly water samples were also collected for nutrient analysis. So together, these data sets, covering a span of about 2 years, will help me see how water levels and quality are shaping nutrient transformations over time and space. And my results so far suggest that mosquito impoundments are not only mosquito control tools, they are also still valuable for coastal nutrient management. The summer flooding period promotes the conversion of inorganic nitrogen forms to their organic forms, essentially trapping those nutrients in the soils and the vegetation before it flows back out into the lagoon. And when the impoundments are drained, we see increased oxygen levels being correlated with increased inorganic nitrogen levels in the wintertime, so specifically nitrate and ammonium. And so this draining and flooding is a cycle of nutrient release and uptake, and perhaps if the impoundment is drained less often, then this could promote more nutrient uptake and storage compared to release. And by knowing when and how these systems store or release nutrients, we can refine their management to benefit both mosquito control and water quality. Thank you.
Thank you. Let's get a final round of applause for all our presenters. Before we go into our half-hour break, if you are one of our judges, please be sure to upload your scores. You have the QR codes on your sheets. Also, for everybody here, make sure to go upstairs and check out all the posters that everybody has worked really hard on, especially the judges. We'll meet back here at 3:20.
Okay, let's find our seats, everybody. It's about that time, living resource time. All right, we're going to go ahead and welcome our first speaker, Luciana Banquero from University of Central Florida. And just as a reminder to all of our constituents here, we're going to have these 3 signs, right? Green for 3, yellow for 1 minute, and red for you're out of time. And if you keep going, I'll get the net. And trust me, I know how to use it. All right. Go ahead, Luciana.
All right. Thank you. Hello, everyone. My name is Luciana. I am a master's student at the University of Central Florida, and today I'll be talking to you about my thesis work on the relationship between Clerpa prolifera and Haliduli radii in the Indian River Lagoon. So, Clerpa prolifera is a macroalga native to the U.S. Atlantic coast, which increased in abundance in the IRL following a decline in seagrasses, particularly in the northern Indian River and Banana River, as displayed on this map. So me and my collaborators at the Brevard Zoo and St. Johns River Water Management District wanted to investigate whether abundance of Clerpa prolifera affected growth of Haliduli radii, and we wanted to do this specifically with Haliduli because it is the most common form of seagrass in the IRL. It is also the most commonly used seagrass for restoration across Florida, so this would be a good species to do that with. And we wanted to investigate the hypothesis that Haliduli growth would be affected by Clerpa prolifera patch characteristics due to either competition between these species or possible facilitation where Clerpa could maybe help the growth of Haliduli. So we did 2 experiments. First, I'll talk to you about my controlled tank experiment where we did look at 3 different densities of Clerpa, 85, 25, and 2% cover, which from here on out I'll call high, medium, and low Clerpa. And we investigated this at the Hub SeaWorld Research Institute, where we used their outdoor tanks with replicate containers inside of these tanks with different Clerpa patch densities inside of each of them, as well as containers where there was no Clerpa in them and Haliduli was placed into them to grow on its own. We placed the same amount of Haliduli into the 3 different patch densities and allowed the 2 species to grow together for 7 weeks. We measured percent cover of both species, as well as frond heights of Clerpa, blade heights of Haliduli, and shoot and blade counts of Haliduli, and analyzed this data using multivariate analysis of variance to understand the effects of the different treatments on Haliduli. So what we found was that Clerpa density treatments had a significant effect on Haliduli growth after 7 weeks. We found that more Haliduli growth happened in the control treatment where Haliduli was growing by itself, and the least growth of Haliduli was observed when it was growing next to a high density patch of Clerpa. And we saw kind of a stepwise pattern where the medium density Clerpa patch kind of inhibited growth a little bit and made the Haliduli growth more similar to the Haliduli growing in the high density Clerpa patch, and Haliduli growing in low density Clerpa was more similar to the control treatment. So we saw this with our percent cover metric as well as our shoot count metric. We also saw this with blade counts, though we saw that Haliduli canopies were not affected by the different treatments of Clerpa. We also did a field experiment at 3 different sites in the northern Indian River and Banana River, where we had different Clerpa patch treatments, specifically Clerpa patches that were left unmanipulated, Clerpa patches where we planted Haliduli into Clerpa, Clerpa patches where all biomass of Clerpa was removed prior to the experiment, kind of leaving it bare, and then Clerpa patches where all biomass was removed and Haliduli was planted into it. So we monitored these different treatments for 8 months, collecting data on percent cover of both species, blade heights of Haliduli, frond heights of Clerpa, shoot density of Haliduli, as well as water depth and percent cover of drift algae. And we used multivariate analysis of variance as well as non-metric multidimensional scaling to understand the impact of these different variables on Haliduli growth. So we found that at all 3 sites, Haliduli grew, though at site 1, it reached its maximum coverage of Haliduli in June after being planted in April. At Site 2, it reached its maximum coverage in July, and at Site 3, it reached its maximum coverage in September. And for reference, our Site 1 was further north in the Indian River, Site 2 was a little bit south of it, and Site 3 was our One Banana River site. We saw a lot of variability in clerpa coverage at these 3 sites, where at Sites 1 and 3, they went into steep clerpa coverage went into steep decline immediately after the beginning of our experiment, whereas at Site 2, it increased significantly until July and then went into steep decline again, disappeared from that site for 2 months, and then came back at the end of our experiment. But overall, we found no significant effect of clerpa coverage on haliduli with the analyses that we used, though we did find a significant effect of the different plot treatments. We saw that in plots that were planted, there was higher haliduli coverage, though there was some natural recruitment of haliduli at Sites 2 and 3 specifically, though Site 3 had higher overall coverage of haliduli in all of the plots. We saw no significant effect of clerpa removal on haliduli, so it didn't hurt the haliduli, it also didn't help it. Factors that we did find were significant or had significant impacts on haliduli growth were water depth, drift algae, and time since planting. So haliduli coverage was generally higher when the water was lower. Then once the water level raised in the fall, haliduli growth began to decline. And drift algae coverage was generally higher when haliduli coverage was higher, and they both declined at the same time. So overall, we found that the tank experiment results supported our alternative hypothesis that there is a relationship between haliduli coverage and clerpa coverage, specifically that clerpa coverage had a negative impact on haliduli, potentially indicating competition between these species, while in the field experiment, results supported our null hypothesis that there was no relationship between these species. Potential reasons for that include feeding on clerpa by Lycia subornata, significantly decreasing the coverage of clerpa at all of our sites at some point, leaving us with not much clerpa to work with. But potentially this could have allowed the haliduli to grow more than it would have if abundance of clerpa was higher. So, and we found no effect of the clerpa removal treatment on planting, so we wouldn't recommend this as an idea for management to chew on. So thank you to everyone who helped out with this project. Thank you for the funding source at Mote Marine Lab and Florida DEP, and thank you all for listening.
Okay, we have plenty of time for questions. We got time to let these questions brew. Yes, right in the middle.
The water was pretty shallow, yes. You're saying the negative effects of clerpa would have been worse if there was less light? Possibly. We did 2 experiments, and one of them had, there was more light in one experiment than the other, and we found that haliduli generally did better in the experiment where there was more light penetration in the tanks. So, yeah, I would say that's possible.
Okay, got time for another question? Over there.
I'm not sure. Possibly planting rupia would be similar, but I have not studied rupia enough to be able to know that off the top of my head.
Okay, another quick one. Going once, going twice. Up, right here.
Do you think that the stuff that's eating the clerpa could help mitigate the negative effects that it has on seagrass?
I'm not sure. It definitely, the slug being there made the clerpa coverage more variable. but I'm not sure what impact that slug directly could have had on the haliduli itself, aside from the indirect effect of reducing nearby competitors, namely the caulerpa. So.
All right, let's thank our speaker. Okay, next up, Lorraine Simpson, the legend. Herbivore exclusion as a tool for seagrass restoration, evidence from research and practice in a subtropical estuary.
Thank you. That was so moody. Good afternoon, everyone. I'm Lorraine Simpson, and I just wanted to update you on a project that my collaborators and I have been doing, looking at the utilization of herbivory exclusion devices and seagrass restoration in the Indian River Lagoon. And so I'm not going to go into a lot of background. I think we all know that seagrass has declined significantly in the IRL due to degraded water quality. And because of that, a lot of practitioners have been actively working to plant seagrass in areas where it's not coming back naturally. And so while there's a lot of different methodologies that have been tested, one of the things that practitioners are actively working on is how to increase restoration success. How can we make this a long-term establishment of this habitat? And one of the ways that people are looking into that is that of herbivory exclusion. So essentially a way to protect the seagrass after it's been newly transplanted from large herbivores. And when I don't know, was it a year ago, we started thinking about this question a little bit, and we realized there's not a lot of guidance within the state of Florida as to what to do. And so we thought the best thing to do was to hop into the literature. And so we did a meta-analysis, and unfortunately we found that to be inconclusive. And that was just because there's not a lot of research that has been done on this topic yet, and so there was low power. And so while we couldn't find this in the body of literature, we thought, well, we know people are doing this in the state of Florida, so let's reach out to them. What are they doing? How are they doing? And how is it working? So we did a survey of practitioners, and we had 13 respondents that reached out and said, this is what I got going on. Of those 13 respondents, it was very interesting that 70% of them had either done their project in the last 3 years or it was currently happening, which really brings to light the fact that this is a very new methodology, and this is probably why we're not seeing the guidance that we would like in the literature. And so from this survey, there's a lot of information that came out of it, but we saw 4 major methodologies that popped out. And so we thought the best thing to do was to reach out, do a case study on said methodologies, and hopefully get some guidance that we can use moving forward. And so the 4 methodologies, we have really big cages, we have tiny cages under the water, we have circle cages, and we have square cages. And all of these, I'm going to go into depth a little bit more. So for the large-scale perimeter fencing, these are large. We're talking 100 feet, 200 feet, very labor-intensive, heavy-duty materials. They don't have a top on them. They're 5 feet tall. They're about $45 per meter squared, and that is just the raw material cost. There's no labor included in there. The project that was done here was in the Banana River. It was started in March of 2023, and it was dismantled in August. And in the there was bi-monthly monitoring and maintenance, and in the very beginning, there was nothing that we saw, no degradation of materials or indirect effects. Now, usually I would walk you through this graphic, but please, I don't have time, so just take my word for it. There was a significant difference in the caging treatment. So we saw significantly more percent cover, shoot count, and shoot height of haliduli when it was protected. But the main thing I want you to take away from this graph, though, is that this ended in July. We do not have post data when we took down the cages, so we don't know how quickly that seagrass potentially disappeared or if it is actually able to survive into the next growing season. So just really bringing to light, like, while we're seeing this as a success, is it actually a biological success if we're thinking about this habitat progressing on into future growing seasons? So more monitoring, the better. The next project is low profile and fully submerged cages. These are great. They're 15 centimeters tall, and these are $23 per meter squared. And once again, this is just the raw material cost. This project was done for a lot longer of a duration, and they did monthly monitoring and maintenance. What they found at this site, there was a lot of drift algae, and this drift algae got caught in that little cage often, which could be an indirect effect because it could lead to the degradation of the seagrass, right? Light attenuation, it could smother it. And so what they were doing is they would go out monthly and they would scrub on these cages. Well, after 6 months, these cages started to break down, and we're thinking it was a combination of the fact that we're scrubbing more because of the drift algae, but also that they were using steel wire mesh that was not PVC coated. And so really thinking about your materials is important for the longevity of your project. They too saw an increase in seagrass percent occurrence across all of their different sites, but we don't have time for that, so we're gonna move on. We also have a project that looked at meter square plot size exclusion. This was a huge project that had a lot of different facets of it, but the one that we peeled off of it was just looking at the difference between these two methodologies, the fencing and the caging. So the fences, these do not have tops on them, and as you'll see, this is $230 per unit. This is per unit because this is the subcontractor cost, and this actually includes maintenance. It's fabrication, deployment, and monthly maintenance. So you can see how quickly these cages increase in cost when you start to put labor in that number. They also were using cages which have a top on them, so you have this small mesh top. They have metal or little pegs that extend from the frame for stabilization, and these are $360 per unit. So the hope for this project was to talk about seagrass growth, right? Unfortunately, this project was done in 2024, and that was a really active hurricane season for us. We had 2 huge hurricanes that came over from the West Coast, and they really wreaked havoc on these cages. The fences broke open, and you can kind of see on the back side of this, one of the edges is open, and we're thinking that was the uncoated wire mesh. It couldn't withstand the wave energy. And then these cages, they just would flip over. So maybe the pegs weren't long enough for stabilization, as well as the fact that that top might have actually added drag. So as the storm surge moved through or waves moved through, it would topple them on top of one another. And so because of that, we didn't know how long the seagrass had been available to herbivores. We didn't know if the cages went back in the right spot. And so we felt uncomfortable about using that data. And I just want to say, when I keep saying we, this is the royal we, so I didn't do this project. But one thing that they did do is they wanted to look at the indirect effect of the cage, because these cages are not only there for seagrass, right? And so they put out light loggers, so hobo light loggers in each of their treatments. And so they had the controlled treatment, which is sand only, a planted treatment, grass with no cage or fence, and then a fence or a cage. And then what they found, there was 64% reduction in light in that cage with the top. Just really making one stop for a second and think, well, do I actually need a top at this site? Because if I do put a top, I'm going to see reduced light down to the seagrass, which could affect the growth of it. If you do need a top, maybe we need to do bigger mesh to allow more light to penetrate in there. The last case study that we have are diameter cylindrical cages. These are also a unit that is done by a subcontractor, and these are $370 per unit, which includes fabrication, transportation, and installation. So this doesn't include the monitoring or the maintenance. So once again, very expensive for these methodologies. This project that was done was over 15 months, and what they noted was there was heavy algal growth in these cages, and so there was a lot of maintenance that happened. And while they went out monthly, they really never felt like they were able to tamp down the algae as much as they would like. And so after 15 months, they noted that all of the seagrass had died. And so this is probably a combination of water quality in the area, but also might have to do with the indirect effects of that algae on that cage, slowing the water movement through the cage, maybe sediment dynamics, and light attenuation. And so when we take all of this together, the meta-analysis, our practitioner survey, and our case studies, the hope was to really walk away with some evidence-based guidance of how to move forward. And the first main thing that came to mind was these herbivore exclusion devices will be site-specific and adapted. This is not a one-size-fits-all. You really need to think through your site as well as the methodology as to what is going to make the biggest difference for you. And so also materials matter for durability and stability, right? If it's a very windy or there's a lot of fetch in the area, a lot of wave exposure, maybe you're going to need a lot more stability and anchoring than you would in another site. And protection comes with maintenance trade-offs. There are labor costs that you should factor in when you're thinking about using them. The next is monitoring design strongly influence perceived restoration success. Short-term monitoring can mislead success. The longer the monitor, the better. Use standardized non-destructive methods, as well as include controls when feasible, and please track those indirect effects, because while we're talking about seagrass, there's a lot of other things that might affect the seagrass that we might not think the cages are doing. And the last is transparent, standardized reporting is critical for a strong community of practice and future guidance. Please be consistent and use summary statistics when you're doing your final reports, and then we can pull from them and utilize that data for a meta-analysis. And be transparent. I know sometimes it's hard to say that something we did failed or something that we did was not the first and the best way to do it, but that's the only way that we can move forward as a community and to make us progress in our science, and hopefully help share that with other people through the literature. And with that, I don't think I have time for questions, but thank you.
Certainly find Lorraine during the break and ask her more about the heads. Okay, next presentation is Yander Diaz, and they'll be talking about 1 year and 200 species, the astonishing diversity of Microturbellarians in the Indian River Lagoon.
Good afternoon, everyone. My name is Yander, and I'm postdoctoral researcher in the Smithsonian Marine Station here in Fort Pierce, and I would like to present you the results of my first year of research here in the Indian River Lagoon. I study Microturbellarians, and Microturbellarians are a group of free-living flatworm, phylum Platelmintes, and they are characterized by the very small size of their bodies that is normally ranging between 0.5 millimeters and 3 millimeters long. They are an ecological assemblage, and it means that they are polyphyletic. They are not taxonomically a clade, a monophyletic clade. And that is easily to see here in this phylogeny of the whole flatworms. And in green color, we are going to see the clade that include all the parasitic flatworm species. In blue, you are going to see the flatworms that we call Microturbellarians, that are the big ones that normally size several centimeters, and you can see that they neither are a monophyletic group, and all the other ones, all the other groups you see in the chart, they are free-living Microturbellarians. There are more or less 3,300 species described worldwide. More or less the half of these species are marine species. The other half are freshwater species. From a morphological point of view, these very small animals are very complex, particularly those organs related to the genital system. We are talking of animals that they are hermaphrodites, then they present both male and female structures, and the variability of those structures, mainly in the male system, the sclerotized structures like the stylets, are the ones that are more important, more informative in the moment to describe and recognize species. But why is so important to study Microturbellarians, and why are they important? Microturbellarians are top predators in the ecosystem. Then they help to keep the healthy, for example, beaches and the other ecosystems where they inhabit. For example, this is an example of a Microturbellarian, a rhabdocoel Microturbellarian, and you can see in the parenchyma, the digestive parenchyma, because there is not here a digestive system, a nematode. But at the same time, they constitute a source of food for other invertebrates. This is, for example, one acyl worm that is feeding in some invertebrates, including a copepod, but you can see here mainly the eyes of several Microturbellarians. At the same time, they are good indicators of the quality of the environment because they are very small and at the same time very sensitive to the variations in the conditions of the environment, like salinity, oxygen concentration, on the amount of organic matter. They also develop very interesting relationship with other invertebrates and with microalgae. Some of them, like this example, and a species of Pocaina, also a rhabdocoel, they feed on diatoms, and they are able to keep alive and functional plastids inside of the body of these diatoms. And because of this reason, they have been used as models in evolution, regeneration, sexual selection, and many other topics. Before I moved here to the US to develop my project, only 165 species of marine Microturbellarians were recorded to the entire United States, including both the Atlantic and the Pacific coasts. And only 6 species were recorded here in Florida, the entire Florida. Then the big question of my project is what I'm going to find here in the Indian River Lagoon. Before my project, only 2 of these 6 species recorded to Florida were also recorded to the lagoon. Then my project is focused in general in the coast of Florida, but I'm just going to restrict my results to what I found here in the Indian River Lagoon. And I developed sampling from January to December of the last year, and from the intertidal to approximately 2 meters deep in a variety of sediments, and also collecting macroalgae and hydrozoan colonies. These samples are processed with one method that is called the magnesium chloride extraction method. Basically, magnesium chloride function lies an anesthetic solution, and then I can rinse this sample, and after a few minutes, I can filter those samples, and on those sieves, move the flatworms from the samples to Petri dishes with seawater, and later recover the worms. There are 2 main morphological approaches I use to identify and characterize the species I found. The first one is with the use of differential interference contrast, mainly to study the morphology of the hair structures of the copulatory organs. And the second one was implementation of confocal laser microscopy to study those species that they lack hair structure, and I have to study then the muscular arrangements of the genital, mainly the genital organs, but also the digestive ones. After this year, I have documented in the Indian River Lagoon, and this is just the number of species until December. Today is totally different, it's higher, of course. I documented 200 species, and they are distributed in most of the major groups of Microturbellarians. The most species richness group is rhabdocils, is the group where I have more taxonomical expertise, including 129 species, and the other one is Proceriata, a group I'm not an expert, but I can also differentiate species with 25 of them. Then in rhabdocil, the species distribute in all the major 5 groups included inside the rhabdocils, and something that is very astonishing is that approximately 70% of the species I found inside the lagoon, they are new to science. Then probably most of my work this year is gonna be about describing and naming these unknown species. This is a fair example of one new genus and one new species we have described from the lagoon. It's in an accepted paper in Marine Biodiversity, and also include molecular phylogeny, something integrative, and specimens from other places of the world, but there is the first species I described here from the Indian River Lagoon. A second example I bring to you to explain you what I do about morphological studies is about proceriates, a group that I told you before I'm not a specialist, particularly in those like the one in the left side, that they lack hair structures. Then you can see with confocal microscopy I'm able to study the muscular arrangement and, for example, distinguish the different pores of the both male and female system, and also the internal structures in the body. And in the second example, in the right side, I combined both the use of the confocal laser microscopy and the study with DIC of the armature of the cirrus, the male copulatory organ. And in this group, about 90% of the species are new to science. Altogether, since biogeographical point of view, the fauna of the Indian River Lagoon is mainly related with the fauna of the Caribbean. The Caribbean is a tropical area. We are in a subtropical area, but using the border in the limit with the Caribbean. Then it's not surprising that many of the species I find here are also occurring in the Caribbean. In conclusion, we consider that the diversity from a point of view of the species richness in the Indian River Lagoon is very high. That is not very surprising because there are other places in the world that are well documented and also present a high richness of species, like the island of Seal in the North Sea, where are recorded about 320 species. But the difference is that species from there have been recorded in more than 100 years of permanent studies in the area. Even I was working there. Approximately 125 years of research to document 320 species, and only in 1 year I documented here 200 species. Of course, the distribution of these species, what mainly say is the distribution of the researchers working in these animals. If you go to other places in the world, you are also going to find many species. But the people studied them have been mainly Europeans, and that's the reason we can see this pattern. And of course, not only the diversity is important, also from the biogeographical point of view, the most important thing is that about, in general, in all the groups, 70% of the species are new, and probably many of them are local endemics. Then they say, they are explaining that the diversity of the lagoon is unique. Finally, I want to say thank you to all my colleagues of the Marine Station, particularly to those of the benthic ecology lab that have been involved in the collecting of the samples. And of course, I also want to acknowledge the institution that have supported my work, the Smithsonian Marine Station, the U.S. Army Corps of Engineers, the Lynn Foundation, and the Ocean Census. Thank you.
Okay, thank you, Yander. Feel free to catch them during the break for questions. So our next presentation is by Jada Brown from FAU Harbor Branch. And Jada's presentation is entitled Shell Shocked, Community Responses Revealed by Empirical Dynamic Modeling.
Okay, good afternoon. Today I'm going to be talking about my work in modeling community dynamics with bivalves that will hopefully leave you shell-shocked through this new framework. So I first just want to start out by addressing that we all know the Indian River Lagoon is an extremely complex system to study, with experiencing decades of decline in water quality and sediment composition, which has impacted the overall ecosystem health. And so with this complexity in mind, my work is working on a new way of approaching monitored communities with methods that are designed specifically for systems that are at this clear state of non-equilibrium, such as the Indian River Lagoon. For my work, I'm partnering with the Smithsonian Marine Station's benthic and faunal monitoring program. So this program has been conducting quarterly sampling via petite ponar grabs at 15 sites across the Indian River Lagoon and St. Lucie Estuary since February of 2005. And so in the preliminary stages of building my model, I'm focusing only on the benthic bivalves in this data set, because they are widely present across the sites, but also we have IDs mostly down to genus, which is what I would like to work with. And so currently what we have in this data set right now is we know the bivalve composition across these sites, but what we're currently lacking information on is the interactions within these communities. And knowledge of these community dynamics would enhance our understanding of their responses to disturbances. And so instead of doing complex interaction experiments with all bivalves present in the Indian River Lagoon, we can model the community dynamics with abundance records over time. And so how we can infer these dynamics is with empirical dynamic modeling, also known as EDM. And so with EDM, you can take abundances over time and use them to reconstruct the dynamics of the system. And so I have a simulation to show you kind of how this works in a more simple example. So if you have 3 interacting variables, such as 3 bivalves in your system, as time moves forward, you can see how their abundances fluctuate together, and we're able to reconstruct their community dynamics, as you're seeing on the graph there, built in this state space that kind of follows this set state of patterns. And so this model is really unique because it accounts for constant change within the system. And so it's not assuming an equilibrium state, and it also is an equation-free approach to modeling, so we're using just the data to tell us what is happening in the system. And then also, this is the first application of EDM in the Indian River Lagoon, and potentially the first biological application across Florida, even though it was introduced in the 90s. And so this is really exciting. It's an extremely powerful approach for us to use for these complex systems. And so I'm gonna walk you through my framework of how I can apply this, and then also what it tells us. So firstly, we start with our abundances at one site, and so I'm focusing on one of our 15 monitored sites in the southern Indian River Lagoon. You can see it on the map in the bottom right corner there. This site, you can see the abundance records here since 2005, and so since 2005, we have records of 31 different genera at this site. And so using these abundances, I will feed them into the model, and this will be used to reconstruct the community dynamics. And so what this does, so EDM will use how the abundances have fluctuated over time to compute interaction strengths between all the genera present at each time period. And with these interaction strengths, we can create what is known as a community matrix. So for example, this is a matrix that I'll get at every single time period that we have sampled. It's a 31 by 31 matrix showing pairwise interactions between all bivalve genera at this site. And so from the model, we take the interaction strengths that are computed and we organize it into this community matrix. And what these values demonstrate is that how strongly interactions influence a genus's abundance. So for example, we have inhibition in red, facilitation in green, or no effect in gray. And so for example, where an intersection point between a column and a row reach, it tells us here, so for example, at this point, we're looking at the tagless's impact on the abundance of Leucinoma. And at this time period, it's suggesting that it's to be inhibiting it, which may be explained by their similar living modes as deep burrowers possibly competing for space. But these interaction strengths will vary over time as a result of the community's makeup, resources, space, availability, and disturbances. And so using these community matrix, we can compute what is known as a sensitivity value for this type of framework. And so using this equation here described in the paper on the bottom, we take the community matrix and pop it into the J values within that equation to compute what is known as a covariance matrix. This covariance matrix then tells us how do the taxa vary in response to perturbations, otherwise known as community changes or disturbances. And so genera with higher values then represent higher sensitivity to perturbations at this site. And so I'm going to show you some preliminary results of our site here so we can see what we can learn from this type of framework. Very preliminary, just pointing that out now. So for example, if we look at one of our bivalves, tagless, for the early stages of the model, we take 70% of the abundance records to train the model, and then we can compute the sensitivity for the last 30%. And so what you're seeing here now is the darker the purple is, the more sensitive that bivalve is. So I'm going to zoom into that part of the graph so we can talk about it. What my framework highlights is possible early warning signals of future changes to community makeup. And so examples of that would be in red here. These are time periods where we're seeing high abundance, but also moderate or high levels of sensitivity being reported. And so it's predicting an early warning signal of possible declines that are occurring right after these quarters. Specifically, these two summers here in 2017 and 2018, we're seeing those high abundances, moderate levels of sensitivity being reported. But what's interesting, and kind of to show you how this model works, is that in summer 2019, we're seeing the same level of abundance being reported, but now it's a slightly higher sensitivity level. So this is showing you how the model is able to pick up on historical changes that have occurred to better predict future community changes. As the model is picking up on those earlier summers when they had high abundance, we see that drop in abundance after, which is why it's seeing a higher sensitivity the second time, even though this is likely just reflecting seasonal changes, because tagless, we typically see peaks of abundance in juveniles in summer and then followed by lower abundances in the fall. But it just shows you how the model is picking up on these changes to inform for future ones. And then additionally, I want to point out that high sensitivity is not always bad for a population. So what we're seeing in the purple box here is high sensitivity in spring of 2021, followed by an increase in population for the following summer. And so what sensitivity means in my framework is that that bivalve is likely to have a higher response than other ones in the community. And that response could be either an increase or decrease in abundance. And so looking beyond just one bivalve genera, we can compare across multiple. And so looking at the top 10 sensitive bivalves at this site, you're seeing now on the y-axis is the sensitivity value computed and not the abundance anymore. This framework allows us to highlight these highly informative taxa across sites, and it does vary across sites, even though I only get to talk about one today. So you can see from this graph, there's kind of 4 top competitors here, specifically though, tagless in that purple. We're seeing a lot of high population fluctuations in that taxa, but we're also seeing them varying a lot in sensitivity. And so specifically for management purposes, this would be really useful because we can focus on specific type of taxa at different sites, knowing their sensitivity values. And so in conclusion, my framework allows for a more robust understanding of community dynamics by providing early warning signals of possible population declines, as well as allowing us to rank genera sensitivities to reveal these strong indicators of community statuses across sites. And for next steps, I'm going to be working on identifying past disturbances and those associated sensitivity values to see if we see any trends, as well as optimizing my model. It was really hard to build, and so I'm going to start now narrowing down genera to include in the model to avoid information overloading. As right now, I do include all 31 genera at this site, but some of those have only been recorded once or twice across the entire monitoring program, and so they're likely not informing our community dynamics and really confusing my model. So I'm going to start by dropping those ones out first. Thanks, Matt. And I just want to say thank you to my lab here at Harbor Branch, the Indian River Lagoon Graduate Research Fellowship, and then all the people I work with at the Smithsonian, as well as the Link Graduate Fellowship there for funding my research. Thank you.
Got time for a quick question. Quick question for Jada. Jada is also a student. This is a student presentation, judges.
Is everyone still awake?
I have a question. Have you explored the other sites, and how well does this work?
Yeah, so I have explored the other sites. What we're seeing is that there are different bivalves that are the most sensitive across sites, so you're seeing different indicators at the sites. But with this model, you need same time steps between all your sample periods, as well as it needs enough information to build it. And so really rare species that are only recorded once or twice throughout the model, or only a few abundances, doesn't inform it enough. And so you need at least 3, I think, is the minimum that we try to work with at a site that have some type of temporal fluctuations that can inform the model enough to get these results.
All right, let's thank Jada.
Okay.
Okay, up next, another student presentation. This is Jackson Evans. Jackson will be talking about habitat preference by Calonectes sapidus, blue crabs, in the Indian River Lagoon.
All right, hi everyone. My name is Jackson Evans. I'm with Bethune-Cookman University and the CCME program. And today I'm going to talk to y'all a little bit about benthic habitat preference by Calonectes sapidus, commonly known as the blue crab in the Indian River Lagoon, Florida. So to kind of start a little bit, why do blue crabs matter? So blue crabs are an ideal species for asking some of our very important ecological questions because they're both ecologically and economically important. They're widely distributed along the Atlantic and Gulf coasts of America, and they function as both a predator and prey species while also supporting a pretty large fishery, mostly up near Chesapeake Bay, but also down as far down as North Carolina and even some in Florida as well. And crucially, blue crabs do depend heavily on structured benthic habitat for refuge and foraging while they're in the juvenile stage. And seagrass beds have traditionally been seen as kind of the primary nursery habitat. However, as we've talked about a lot, with the changes that have happened in the Indian River Lagoon, that's something that's kind of been looked at in other estuaries, but kind of has been translated here into a subtropical estuarine system. So the goal of this study was to determine whether macroalgal beds can functionally replace seagrass beds as a nursery habitat for juvenile blue crabs in the Indian River Lagoon, Florida. So to do this, I had 3 complementary approaches. First, I did a spatial analysis of seagrass abundance versus blue crab presence data over the course of about 30 years, dating back to 1994. That led to some ex situ raceway experiments, kind of looking at how habitat shifts affect blue crab behavior, and also seeing how we could predict any sort of behavior from that. And then lastly, we are currently undergoing a gut composition analysis to see if we can link feeding preference to a preference of seagrass or macroalgae. However, for the purpose of today, because of time constraints, I will only be talking about the first 2 objectives. Okay, so this study integrates 2 long-term monitoring programs with some pretty different spatial designs. On the left, you can see the fishery, or the FWC FIM dataset, or the Fisheries Independent Monitoring Dataset for blue crabs in the Northern IRL. As you can see, it's pretty dense and spatially clustered due to the way in which FWC targets fish and invertebrate populations within some of the defined estuarine zones A through H. From this data set, I used blue crab presence and carapace width, as well as a host of different environmental parameters, including temperature, DO, pH, kind of the whole 9 yards. And this data spans from 1996 to 2023. And then on the right, you can see the St. John's River Water Management District benthic survey locations. While they're a bit sparser in comparison to the FWC data, they are lagoon-wide and do provide a very good image of what we see of benthic habitat cover, specifically looking at summer seagrass abundance. And this data set we used was from 1994 to 2024. So this kind of led us to the first bit, which is I did some GAMs of looking at blue crab carapace width versus a host of environmental parameters. We don't really have time to go into all of them today, but kind of the interesting ones are salinity and dissolved oxygen. As you can see, there are peaks in some relative intermediate levels. And then also you can see in wind speed and bottom vegetation cover, it's very oscillatory. That is because of the way in which the FWC or the FIM data set rounds its data. And so while the actual oscillations are not very important, the overall trend of the data can provide some information for us. So we also worked with some empirical orthogonal functions and principal component analysis. And so this is actually PC1 of benthic cover. So it's looking at the dominant seagrass changes over the span of the study. And overlaid with the ONI data set, which is the Oceanic Nino Index taken from NOAA. And as you can see, red is highlighted as a El Nino period, and blue is highlighted as La Nina. And from here, we could see that ensophase could actually really affect seagrass populations, as in both cases in which there were large seagrass die-offs, that being in the early 2000s and the early 2010s, they both did occur directly after a La Nina event, which could signal an increased level of rainfall and storms kind of leading to a lot of this runoff and increased turbidity. So from here, I was able to kind of combine the two data sets by delineating the St. John's data by the FIM zones. And so using that, I was able to compare average carapace width with summer seagrass abundance, while a separate study showed, or a separate graph really showed that the presence of blue crabs didn't really change over the course of the study. We did find that the average carapace width of blue crabs in the northern IRL did really dramatically fall off over the course of the kind of a gradual seagrass loss we've seen over the past 25 years. And this is backed up by the Spearman p-value, which shows that there's a moderate positive relationship as well as a significant or statistically significant p-value. So this kind of led us into the ex situ study, which was done at the Marine Discovery Center in one of their raceway systems. And so we had 15 total individuals that were acclimated for 1 week in this system. In the system you can see on the bottom right, it is made out of PVC and PVC-coated mesh to create 7 different replicates. And each replicate was divided in half by macroalgae and seagrass in a randomized manner. And each of the crabs was affixed with a rhinestone, both to make them look really cool and also kind of to help me observe them, as they can get pretty hard to find when they dig into some of the sediment. And so this experiment lasted 40 days and led to a total of 1,200 habitat locations, which you can kind of see mapped out in the bottom graph. And as you can see, kind of the important observation is that there was little to no preference that we found between the two environments. And so it was pretty scattershot throughout. There would be points in the study where I thought I would start to see some sort of preference, but this actually does kind of contribute or follow in what we've seen in the Chesapeake Bay, which has shown that species such as Gracilaria vermiculophylla can actually sometimes even outperform seagrass as a nursery habitat in a short-term manner. So kind of some synthesis and implications for this study. So taken together, the long-term analyses and experimental results point to a consistent conclusion that blue crabs rely on complex benthic habitat structure for refuge and foraging as juveniles. While macroalgae may not fully replace seagrass in terms of total ecosystem services, they can function as a short-term nursery habitat in systems where seagrass recovery is slow or uncertain. From a management perspective, this does help reframe macroalgae from something that's kind of seen as a net negative in an ecosystem to maybe something that might have some niche value, at least towards blue crabs and potentially other benthic invertebrates. And so lastly, I would like to thank Bethune-Cookman University and the NOAA CCME program for helping fund my research and providing me with plenty or more resources than I could ask for. I would also like to thank St. Johns River Water Management District and the Florida Fish and Wildlife Conservation Commission, both for providing me with their data sets as well as help throughout. Thank you, and I'll take any questions with any time.
Thank you, Jackson. Yep, we have 1 minute for questions. Questions for Jackson.
Yes, so we observe twice a day at 10 a.m. and 2 p.m. Because I live up in like Ormond Beach, so it's like about an hour drive for me, so.
I think there was one over here.
Your treatments of seagrass and macroalgae, were those already established, or did you establish them right before your experiment?
Yes, we established them. So we had they were established for about 2 weeks prior to. Both of them were taken from Scottsmore Landing area.
Okay, let's thank Jackson. Okay, our last 10-minute talk of this session is by Sarah Torrey from FAU Harbor Branch. Sarah's presentation is entitled Fish Don't Read Maps, but They Know Where the Habitat Is. Long-term habitat availability and sport fish responses. And this is another student presentation.
All right, thank you very much. Since I'm the last 10-minute talk of the day, I don't have to do any introduction because everybody else has already gone over that, including the last talk talking about FIM data. So I will skip right ahead to the end and say thank you, everybody, for being here. But for real, so this is some preliminary data from my second chapter. Looking in the St. Lucie River, which is a part of the southern portion of the Indian River Lagoon, and also the southern portion of the Indian River Lagoon, looking at the differences in catch per unit effort of sport fish in this area based on the Fisheries Independent Monitoring data by FWC. So in that nice box there, I think you guys are all familiar with it. If not, you should check it out. It's a pretty cool place. So as we know, historically, flow from Lake Okeechobee used to move south. There's restoration work in place to keep that, to put that back into place. But then since then, it has been diverted to the east and west, causing a different array of issues, including freshwater discharges that typically have happened before weather events to kind of lower the lake levels. And this has caused issues within both sides of the estuaries today, obviously only focusing on the Indian River Lagoon. And we know that changes in freshwater flow can attribute to changes in turbidity, salinity, temperatures, and nutrient levels, and that could affect species richness, habitat availability, and primary production, as well as food availability, and going from a good ecological condition with nice biodiversity to a poor ecological condition with some very bloated puffers down here. So those of us that have lived or worked in this area for a while have seen some of these effects, and we know that there's the possibility of loss of essential fish habitat, which can result in the collapse of fisheries that can even affect things as far as offshore, and then thus impacting the humans and animal communities that depend on these fisheries.
The decreased salinity and increased nutrients and turbidity are responsible for mass die-offs of seagrass and oysters, which other folks have discussed today as well. So the knowledge gaps that I'm looking at are the large-bodied sportfish habitat use in this degraded estuary. This is, again, my second chapter, so I'm assessing the fish habitat preference and changes in catch per unit effort over time using the fisheries independent monitoring. Right now I'm looking at the timeline from 97 to 2019, although there's more data available that I'll be digging into soon, and identifying how habitat and hotspots for select sportfish species have changed over time. So again, the purpose is to identify how natural and anthropogenic disturbances affect the availability of natural habitat and sportfish catch rates over time. So the 3 species we're going to be looking at, I'm really sorry, Derek, I don't have a better picture of a juvenile Goliath. That's not out of the water, but our juvenile Goliath grouper specifically, sheep's head and spotted sea trout. So the juvenile Goliath grouper, recently it's been open for harvest, but previously was a protected fishery. Sheep's head is pretty abundant in this area, as we'll see with some of this preliminary data. And spotted sea trout, that's highly correlated with seagrass. So people tend to think no seagrass, no spotted sea trout. I've tagged about 30 of them. I've caught a bunch more. That's not necessarily true, but we'll see what the data says. So some of our methods include the monthly seine hauls with the 600-foot seine net in 2 different zones in the lower IRL and the St. Lucie River, and the FWC Fisheries Independent Monitoring catch data, again, from 97 to 2019. This is randomly stratified sampling, so you're not always going to hit the same spot every time, and this is also a very large net in a highly urbanized area, so there's not always space to set the net in between the docks where the point says you should go, so then you have to adjust, and they have a whole process for that. And then looking at various analytical tools, actually Jackson touched on a few of these too, so thank you for introducing those, to look at all of these different elements together. And these methods will reveal shifts in habitat use and catch per unit effort in relation to major natural and anthropogenic related ecological events such as cold snaps, HABs, hurricanes, and freshwater discharge events. So here's an example of the net as it's being kind of closed and pulled in. So again, very large. It's actually a lot of fun. I enjoy it. It's a good workout, but it is a lot of fun. And the monitoring efforts have been going on since the 90s, and this data set is so vast, it's contributed to a number of papers. These are just some more recent ones. Talk to that back row if you want to look at any FIM data. This is a non-exhaustive list of some of the events that we've had occur here in the Southern IRL in St. Lucie, and some of the things that might cause an effect on the fish abundances over time. So over that time, we have captured only 37 juvenile Goliath grouper. There is kind of a reason for that. And then over 5,000 sheep's head, and only about 283 spotted sea trout. And these zones that I was talking about earlier, there's zone T, so this is going to be represented in blue later on some of the graphs, and then zone J, which is the southern IRL portion, that'll be in some of the red outlined graphs. And so catch per unit effort over time is kind of interesting. Again, only 37 Goliath grouper, so, you know, what do you expect? But these nets aren't set. This sampling method isn't designed to capture these fish where they are actually occurring in the estuary, which is around bridges and dock pilings. We know this through the acoustic telemetry studies. That was part of my first chapter, not today. The sheep's head had kind of a steady decline for a while, and then you see in zone T, the St. Lucie, there was a huge peak in 2015. What happened? And then another sharp decline right after that. And then the spotted sea trout, kind of the same thing, not too many being captured in the St. Lucie after 2014, and then a lot of staggering in the southern IRL. So this is looking at some of those different events. You see they're all titled up here, kind of in chronological order, and these green boxes represent the pre-event catches. The orange boxes are going to be the event period itself, and then the post-event. And these are kind of in like a couple year buffers, which isn't really ideal for this data set because it's monthly sampling. So this is something I'm working on refining later. And then it's separated again by zones J and T. And you'll see there's not really much data here for the Goliath grouper, only 37 fish, and so on. And then you'll see down here, there's just no Goliath grouper being caught at all. So it's pretty interesting data. So then we're gonna look at some principal component analysis to identify what the dominant environmental drivers, structuring variation, and which variables are moving together. It's a little hard to see here, but the sheep's head, there is a lot of bottom vegetation and shore type drivers that are significantly impacting their catch per unit effort. And even though it's a small sample size, the Goliath grouper have a significant effect of bottom vegetation. So then we also did an IVLEB's electivity index. I have some graphs that I have at the end of this that we could show you later to look at their preferences or avoidance of these habitats and where you're typically going to find them with the FIM data. So including like mud bottom type, mixed seagrass, and no surprise with the sheep's head, they like oyster bottom and man-made structure. I also ran some GAMs looking at the environmental variables taken during the FIM sampling. And so you can see a decline for the sheep's head in the St. Lucie with dissolved oxygen and salinity, and then kind of more variable responses in the St. Lucie, or in the southern IRL. The spotted sea trout, not as robust of a data set, but there's some increasing, some positive correlations in the St. Lucie, and then again, some mixed effects of, at least of salinity in the IRL. And Goliath grouper had significant effects of salinity and temperature affecting the catch per unit effort, but again, only 37 fish. Looking at the hotspot analysis, we see that the sheep's head hotspots with over 5,000 fish caught over the years in the North and South Fork. And then the spotted sea trout in this area up here in the Indian River Lagoon, that's kind of associated with some mangrove shoreline and some patchy seagrass. And I'm not going to talk about the Goliath grouper. So my next steps are looking at some habitat data. This is an excerpt from a report done for the South Florida Water Management District looking at how oyster density has changed over the years, and I want to relate that to the catches, as well as looking at all the seagrass changes. Again, some data sets through the South Florida Water Management District and FWC, and concluding that the long-term catch per unit effort trends are non-linear and species-specific. The water quality thresholds matter, and that natural habitat availability still remains important. And also noting that sportfish in the St. Lucie River and southern Indian River Lagoon respond not just to habitat presence, but when, where, and under what conditions that habitat is available to them. I would like to thank a number of people, a lot in that back row. Here's some references, and if you have any questions, I don't think I have any time for ones.
Yeah, catch Sarah during the break. Thank you, Sarah. Okay, and now we're going to switch to the 3 minutes, maybe possibly 3 slides.
All right, thank you. So this is our last 3 minutes, 3-slide session on living resources. And up first, we have Jamila Roth talking about sulfide oxidizing bacteria.
Cool, my name is Jamila Roth, and I'm a postdoc at the University of Florida. So seagrass sediments can have high sulfide concentrations, and sulfide is a phytotoxin. So high sulfide concentrations, especially when combined with other stressors, can lead to seagrass die-offs. And therefore, seagrasses have evolved mechanisms to detoxify sulfide, with one of these mechanisms being associations with sulfide oxidizing bacteria. Specifically, I'm interested in the bacteria Candidatus thiodisotropha, which oxidizes sulfide and fixes nitrogen, both of which are expected to reduce seagrass stress. So I wanted to compare seagrass rhizosphere microbial communities through time and space. And first, I analyzed rhizosphere microbial samples collected by Julie Meyer in Cedar Key, Florida, over the course of 3 years for multiple seagrass species. And we found that the sulfide oxidizing bacteria, Candidatus thiodisotropha, was really dominant in most of these samples. So you can see thiodisotropha in this pink color, with each bar representing a different sample. We have Haliduli, H. rhi, Syringodium S. phil, Thalassia T. tess, and we have rhizome and root samples. And the relative abundance is on the y-axis, and it often reached
30% or higher relative abundance for this bacteria. However, all of these samples were collected from the same site in Cedar Key, Florida, so I wanted to see how the relative abundance of this bacteria varied spatially. So we collected Haliduli rhizosphere microbial samples from 3 sites along the Gulf Coast, which were Cry, Home, and Wee, and 3 sites in Banana River, which were called IRL A, B, and C. And again, we found that this sulfide oxidizing bacteria, Thiodisotropha, was present at all sites and in pretty high relative abundance. So while there is some variability in the relative abundance, I just wanted to show you that it's consistently associated with Haliduli rhizosphere spatially. And then we also measured gene expression for this bacteria, and we found that Thiodisotropha was actively expressing genes related to nitrogen fixation and sulfide oxidation at all of these sites. So not only is it present, it's also actively oxidizing sulfide. And so in conclusion, we found that sulfide oxidizing Thiodisotropha bacteria is consistently associated with seagrass rhizospheres, both through time and space, and it is potentially reducing seagrass stress. And so this is really important because mechanisms that impact seagrass stress response can potentially be applied to restoration. And so next, I'm planning to explore relationships between environmental data that I collected at these sites and the microbial community. Thank you.
All right, up next we have Michaela Sternenson talking about Project Plankton.
All right, good afternoon, everybody. How we doing out there? End of day, yeah. So like she said, my name is Michaela Sternenson. I'm an education specialist at the Marine Discovery Center located up in New Smyrna Beach. And I want to tell you about a community science initiative that we started back in 2023 called Project Plankton. So as some of our presentations today have mentioned, and some of you may know already, plankton are drifting marine organisms that serve as vital components to marine ecosystems. They comprise the base of the food web in the marine world, and they also produce almost 50% of oxygen in the world. Here in the IRL, however, of course, they have a different sort of infamy. They're known for creating harmful algal blooms, which we are all familiar with here, as those are driving factors to the loss in seagrass, especially in the last few decades. Project Plankton is a community science initiative aimed at monitoring plankton communities in the northern IRL throughout time while educating the community about the complex role of plankton in the ecosystem. Community scientists, like this one on the left, are trained in collecting plankton and environmental data using a variety of tools and technology, including our 13-centimeter diameter plankton net that has 150 micrometer mesh, also a LabQuest, refractometer, Secchi disc, many tools that a lot of you probably have used before. But one of our unique tools is actually an AmScope T720 microscope that has a built-in camera, which you can see in the third picture there. And the second picture there is actually one of the images we were able to capture with our microscope. This allows us to capture brilliant photos of our specimens observed that we're able to share with the public via our original plankton catalog on Flickr, and a QR code to this will be available on the next slide. Since its inception, Project Plankton has trained 46 unique individuals through bi-monthly trainings who have invested over 580 hours into our project. We've also educated over 3,500 students in the Volusia County area about plankton through our field trip education programming, including 12 Volusia County Title I schools. Our vision is to have regular year-round plankton sampling at our study site and to empower people outside of the scientific community to pay attention to their local waterways and to act accordingly. Our catalog will be available on our website before the end of the school year, along with some plankton lessons that teachers can use in their classrooms to engage their students in water quality. And in the future, we also hope to have our data available online as well. So just a couple things that we've observed so far. We have a fairly small data set, but we actually have found 36 unique genus of phytoplankton that we've identified, 2 phyla of zooplankton, and we've also identified a correlation in our study area over this small amount of time with a decrease in temperature, seeing an increase in abundance of phytoplankton. So kind of an interesting pattern that we're noticing, at least up in our site in this amount of time. So that's just one piece of data that we've found so far, and I want to thank you for your time today.
All right, thank you, Michaela. Next up, we have Stephanie Schreiber. This is a student presentation talking about real-time temporal monitoring of phytoplankton in the Indian River Lagoon.
Sorry to sound like a broken record here, but eutrophication in the lagoon is a problem that leads to algal blooms, as shown in this photo here. These algal blooms can then lead to seagrass die-offs, fish kills, and a lot of other problems for the ecosystems, like toxin production. To gain a better understanding of these blooms and their dynamics, we've been monitoring phytoplankton at these 5 sites in the central and southern portions of the lagoon for a little over 7 years now. And our methods include flow cam and manual cell counts through microscopy. These are to look at the microphytoplankton, and then we also use flow cytometry to look at the pico and nanoplankton. Those methods are traditionally labor-intensive, time-consuming, and very temporally limited, but we recently acquired an IFCB, which is the Imaging Flow Cytobot. And this is designed to have long-term deployments that last up to many months. It has really high temporal resolution. It can sample up to 3 5 mil samples per hour, all day, every day, for a month. With this, we've already been able to detect some phytoplankton that we have not seen through the other methods. And we've also seen some oxospore formations of diatoms. And this is really rare to find, so there's not a lot known about it. To put that in perspective, I've been doing the cell counts for over 7 years, over 900 of them, and this is the first time that I've seen oxospores. We can also monitor for HABs. We have these pyridinium cells here. They produce saxotoxin. They're primarily up in the Banana River. And we can just look at bloom dynamics in general at a much finer scale than typical discrete sampling. Ultimately, our goal is to deploy the IFCB in the lagoon near an Erlon site and set up a dashboard like the one that's shown here. This will be available to the public, and you can look at previously collected data as well as see data that's being collected in real time. That's it.
All right, thank you, Stephanie. Next up is Natalie Spahn, who'll be talking about assessing the role of burrowing in fauna in Indian River Lagoon sediment, reoxygenation, and restoration. And this is a student presentation as well.
Hi, I'm Natalie. I'm an undergrad at Florida Tech, and I was looking at the role of bioturbating in fauna on reoxygenating sediment and restoring seagrass in the Indian River Lagoon. I looked at the polychaete species Pectinaria goldii, or the ice cream cone worms. That's a picture of them from the Smithsonian. And species like those, when they burrow into the sediments, they help to bioturbate them, which extends the oxic layer of the sediments, which extends the amount of space where aerobic and anaerobic reactions can be coupled and allows for better removal of harmful anaerobic products like ammonia and sulfide to be removed. And things like ammonia and sulfide can be toxic to seagrasses, so having something like this extend the oxic layer could be really beneficial to seagrass restoration. So I looked at 4 different groups, experimental groups in cores, the first being a control, so bare sediments, then sediments with seagrasses, sediments with the polychaete worms, and then sediments with polychaete worms and seagrasses. And I measured the oxidation reduction potential and the average oxic layer depth in centimeters of both of those across a 5-week period. The ORPs from the polychaete treatments were significantly higher than the ORPs without. As you can see, there's negative values for the ORPs for the non-polychaete treatments and positive values without, which means the ones with the polychaetes had aerobic environments in the sediments, while the ones without had anaerobic ones. And there were significant differences in the oxic layer average depths, with higher oxic layer average depths for the sediments with polychaetes. The duration of the experiment was too short to really see any difference in seagrass growth, but I think that if the same methods were to be applied over a longer period of time, there would be differences because of that removal of anything toxic that could build up in the sediments to the seagrasses. If you can see on the screen, there's the little burrows in the sides of the cores, and that's what the worms do, and that's what enables them to extend that oxic layer. And so, yeah, I want to continue the studies by looking more into how it can help seagrass growth and look at long-term monitoring data of infauna to identify the best areas for seagrass restoration habitats. Thank you.
All right, thank you, Natalie. Next up is Catherine Harris talking about multi-stressor decline of oyster density in Mosquito Lagoon, heat, brown tide, and mangrove refuge, and this is another student presentation as well.
So this past summer in Mosquito Lagoon, we had an unprecedented loss of oyster density, up to 85% loss of this density. Now, typically when we have mangroves recruiting onto our intertidal oyster reefs, this is often associated with negative impacts to our oysters. But with this summer, we noticed that oysters that were near the mangroves, but not totally in the mangrove-dominated area, had increased survival with only 49% loss of our oyster density. So this led us to ask two research questions. First of all, what were the main drivers of this overall loss of oyster density we saw? And secondly, are mangroves able to act as a type of refuge during stressful conditions that oysters are experiencing? So we looked at many different abiotic factors, and three came up as the most important towards our loss of oyster density. Here we're looking at sea surface temperature during August of each year within Mosquito Lagoon, and we found that August of 2025 was the hottest that we've had in the last 10 years, and this was the main driver of the oyster loss. This overlapped with a low water level. So here you're looking at continuous water level in Mosquito Lagoon over time. The dotted black line is the mean water level during summer months. And we saw that in summer 2025, we had significantly lower water level than we'd had for the past 7 years. So our oyster reefs were exposed to that heat for longer periods of time during the day. Here we're looking at brown tide for summer months of each year in Mosquito Lagoon, and we also saw that in summer 2025, we had a significant brown tide event where we saw this contributing to the lack of new oyster recruitment to our reefs. So then to determine whether or not mangroves were potentially able to provide refuge for these oysters during these stressful conditions, we placed transects out on the reef going from the open reef area into the interior of the mangroves. And we were able to compare this to data we had collected in summer 2024. Here we see that data, which is typical of what we expect for natural oyster reefs in Mosquito Lagoon, with about 250 oysters per meter squared, indicated by that black dotted line. We see that in summer 2025, that significant drop in oyster density across the reef, but we're able to document that areas, that oysters in the canopy cover and transition zone did have higher survival, indicating that oysters in this kind of shaded area, but not fully directly impacted by the mangroves, were able to survive better, and the mangroves were providing some refuge for our oysters. We went back out in January 2026 and were able to show that once these stressful conditions had abated, oysters were able to recover. However, going forward, what I want to look into is potentially predicting how frequent these multi-stressor events are going to become so we can understand how this will impact long-term ecosystem resilience, including things like the cold snap we just had a couple weeks ago, wanting to know how that's going to affect both our oysters and our mangroves and potentially give us some interesting insights into these multi-stressor events as they become more common. Thank you.
All right, thank you very much. Next up is Jeff Ebel talking about environmental DNA as a tool for tracking lagoon biodiversity.
All right, so I have 5 slides, so hopefully we can do this real quick. Really quick introduction to eDNA methodologies. Thank you earlier, Jess, for introducing eDNA just as a general description. We have field collections, a variety of substrates to capture our sample, which contains eDNA, environmental DNA. Then we're in the lab, we're isolating the DNA from those samples and purifying it. Because these are environmental samples, there are lots of contaminants that come in that cause problems for us. We have a variety of approaches for DNA analysis, which, depending on the approaches you take, you can estimate the abundance and detect single species using eDNA, which is one approach, or you can look at whole communities, which is what we're often hearing about nowadays. But don't discount the single species approach, because you have an opportunity to get to a little bit more quantitatively get to abundance estimates. Really quick, so I mentioned substrates. Water sampling is typically the source for eDNA samples. Sediment is the next popular source, but then you can pull eDNA from plankton nets and a variety of other substrates. Depending on what substrate you use, you're going to be sampling a different community, basically different. You're more likely to get DNA from different species depending on the substrate, and you can see that in this data that we published in 2020. It's a lot to digest here. I don't expect you to do it, but please go look up the publication. Some really quick, interesting data from the lagoon itself. This is fish eDNA sampling from mostly Banana River, 216 water samples. We were specifically targeting looking at fish DNA in these water samples. We detected previously documented regional diversity trends with these water samples, with declining diversity as you get away from the inlets, as you can see there on that top graph. We also established a fixed taxonomic baseline that allows us to actually track these changes in diversity at these sites over time. And that's a big advance, I think, to allowing the integration and use of eDNA. We have also separately, for a more recent study, we have 108 sediment samples, specifically to attempt to look at differences between seagrass habitats and bear habitats and the benthic diversity there. So we were focusing on sediment samples. But I probed those sediment samples with our primer set used to look at fish, and so we've got a mixed distribution, a mixed community of species of fishes that we detected in those sediment samples, demersal and planktonic species. Again, we're seeing significant regional differences based on these eDNA signals. We weren't seeing any differences over small scales between seagrass and bear habitat for this particular data set, which is fishes, which are mobile. Even a small blenny can move several feet between a seagrass habitat and a patch, a bear patch. That same data sets, that's those same sets of samples, we were actually looking at, okay, so this is metazoan data. We have not run the biodiversity analyses on this, but you can see remarkably more species here, 313 protists, 449 species of metazoans. Really interested in seeing what we pull out of this data set when we start analyzing it. So that's an example of the power that we can get from eDNA. Thank you.
Thank you, Jeff. Next up is Emily Farrell. This is a student presentation. She'll be talking about coast to coast, charting Florida's nearshore marine biogeography with environmental DNA.
All right, so hi, I'm Emily Farrell. I'm finishing up my PhD in the Gaither Lab at the University of Central Florida, and today I'm going to tell you a little bit about our work evaluating biogeographic patterns using environmental DNA in Florida's nearshore fish communities, and why this is going to matter for systems like the Indian River Lagoon. So we all know that Florida's nearshore fish communities are biologically diverse and economically important. Understanding how these, Understanding how species are distributed within these systems is really important for effective management and conservation, but there's no agreement on how Florida's coastline should be divided into biologically meaningful regions. Most commonly, an east-southwest 3-region model and an east-west 2-region model have been used, with the 3-region model actually being codified into our state law. But neither of these models includes the well-documented transition zone between the subtropical and temperate regions that is noted on Florida's east coast. FWC's monthly sampling provides a lot of the data that we have within these systems, but these are limited by gear and access and effort. eDNA metabarcoding offers a complementary approach, which allows us to capture a broader snapshot of the community. So we set out to test if this increased detection of richness would allow us to compare models of Florida's coastal biogeography. To do this, we sampled 11 sites along Florida's coastline over 2 weeks, filtering water from multiple sampling locations within each of these sites. After extraction and amplification, we sequenced these samples with 2 fish-specific primers. and retained sequences identified at the species level for our analysis, which yielded a final data set of over 200 species. We evaluated 9 different region schemes in total, including that 2 and 3 region scheme that I told you about a little earlier, and some additional schemes that subdivide our coastlines more finely. For each scheme, we modeled richness as a function of distance between sites, as well as regions, and controlling for salinity and site level variation. And then we compared our model performance using 2 different measures, which allowed us to directly evaluate how each regional model explained patterns in nearshore fish richness. And we found that by both of those measures, a model dividing the state into 5 regions, a north and south region on each of our coast, as well as a separate region for the Keys in the south, was the best fit. This model performed significantly better than our other subdivided models, but also that 2 and 3 region model that have been commonly used in the state. We then performed an NMDS for the best performing model, which showed that most of the sites within each of these regions is clustering pretty closely together, with some moderate overlap between our regions. We also ran an indicator species analysis and identified species within these regions, and we think that this might be a better model for managing our fish populations within the state.
Thank you, Emily. Next up, we have Eric Ryer, who will also be talking about environmental DNA and how it can reveal fine-scale fish community differences across natural and armored shorelines in the Banana River Lagoon.
All right. Hello, everybody. So we've in the upper Banana River, we've had some extensive shoreline erosion over the years due to storms. That holds true at NASA's Cars Park in the no-motor zone of the Banana River. We've lost, say, 50 feet of shoreline in some spots, extensive mangrove damage, and the waves are actually undermining the road, and so NASA needed to repair this road so people could get to their facilities. And so they got a permit to actually harden about 1,000 meters of shoreline with coquina boulder. They also constructed an offshore wave break to further protect the site. This was an infrastructure protection project, but the hope was it would also have some ecological benefit in terms of reduced turbidity, better vegetation recruitment, and then the fish might actually find some habitat value, especially in this offshore wave break. As contractors, our job was to survey this site. We did mostly visual surveys the first couple years. We found the data set sort of uninspiring because it was very murky. My daughter would call it a sort of mid data set. So we've been eDNA curious for a long time now, and so we got money to actually run a round of eDNA sampling. We used metabarcoding, and we found a commercial option for this. We didn't have a ton of money, so this is our first pilot study at KSC. So we had 16 samples. We took 5 from a natural eroded shoreline, 5 from right in front of this wave break, 5 from immediately offshore this wave break, plus 1 in a freshwater pond that I won't talk about too much. But basically, we sent off the samples. They came back. We ended up with 51 species, including 9 sport fish like sea trout, snook, etc. 2 non-native species, both tilapia. We saw more species near the wave break than offshore, which makes sense. There's more structural complexity along the wave break. This was all sort of expected. What I thought was interesting and maybe worth sharing is that even though all these samples are fairly close together, we saw some differences in the 3 habitat groupings. The natural shoreline and the repaired shoreline, the species assemblage was clearly different. And even more surprisingly was the samples from the wave break, and just offshore the wave break, 75 meters, those sample sets were actually different. You can see that in this non-metric multidimensional scaling plot. There's not much overlap, and we followed that up with an Anderson test. And yes, even with this really low sample size, we saw clear, statistically significant separation between these groups. And so really the take-home message here is, one, the taxonomy, it performed well. There's clearly, we saw some, I'm a taxonomist, there's some glitches in the reference database, but for the most part, it represented our IRL community well. We're not an Indo-Pacific reef. There's commercial options available. That's the gold standard right there, but for contractors, if it's a wham-bam study, there are commercial options. And that we see that eDNA might be valuable for living shoreline assessments because it might capture some of that patchiness in habitat and fish and organisms better than we thought it would. So thank you.
Thank you, Eric. Next up, we have Shannon Whaley, who will be talking about habitat use by juvenile sea trout in the Indian River Lagoon before and after major seagrass losses.
It doesn't seem to be working. Sorry. Use the keyboard. Okay, the right arrow. It wasn't. See. Oh, okay. Oh, sorry. I did it twice. All right. Thank you. Sorry about that. As we talked about, and okay, thank you. We know about all the seagrass loss that has occurred here in the Indian River Lagoon, and for one of our sport fish that are very common here, the spotted sea trout, that's an important juvenile habitat. So we wanted to look at the habitat use patterns before and after this big seagrass loss to see if the juveniles are adapting where they're going, because we do still have quite a few sea trout in the lagoon here. So in order to do that, we also used fishery independent monitoring data that we had heard about earlier. Now I'm really looking at the earliest juveniles right now, which are between 15 and 50 millimeters standard length, so really the small ones. And we separated the data into a pre-bloom and a post-bloom period to look at that, and the orange dots are the data sets, or the data. Oops, sorry. So one of the things that we did to incorporate the sort of like a seascape analysis, because the fish can move, you collect them in one place, but they very well can move around. And so we wanted to just kind of quantify the habitat around that site. And so we did that looking at the area of different habitats: seagrass, salt marsh, mangroves, edge density, and then the distance from the nearest inlet. That's a very important feature as far as, a lot of different processes in lagoons and estuaries. So we did negative binomial regression models, and these are our variables that we have right now. This is a preliminary results that I'm talking about today. So we did look at the time period. That was one variable. Subbasin was another variable, because as so many people mentioned today, there was a lot of different things happening in the different subbasins. So we thought that was important to separate out. Also, distance to the nearest inlet, the habitat context metrics, as I mentioned, and then we also used random effects to look at the spatial and temporal autocorrelation. Oops. And here are our preliminary results. I'm not going to go through all of this, but we did find some interesting things that were kind of counterintuitive. But before the big loss in seagrass, we found that there was really no relationship between the seagrass and the sea trout. But then the post bloom, as the sea trout got more rare, there was quite a strong relationship. So we also have some data and results in a poster that you can see later on today. So thank you.
Thank you, Shannon. Up next, we have Skylar Mayer talking about testing methodologies for monitoring a pilot-scale inshore artificial reef structure in the Indian River Lagoon.
Hello. So in an offshore setting, artificial reef structures have been proven to increase fish abundance and biodiversity. However, little work has been done with these kind of structures in an inshore environment. This particular pilot-scale project consists of 51 concrete X-shaped structures that were placed into 3 different designs that offer a variety of spacing for the Necton community. The main goal of this project is to establish a set methodology that can be implemented in any future efforts going forward. In an attempt to do this, a variety of different monitoring techniques were tested over the course of 1 year. Some of these techniques were brought in from proven offshore methods, such as the chevron trap, which is the second photo right there. And we scaled it down to appropriately sample the expected fish size classes that you would expect to see in the lagoon. Other applicable trap designs, such as rectangle traps, mesh traps, and seine nets, were also implemented to identify what the best methodology would be for sampling these kind of structures. Additionally, BRUV video sampling was conducted in an attempt to bring fish closer to a camera to potentially sample fish in very murky or turbid environments, as we often see in the lagoon. And the last thing that we also conducted were timed swim transects, which we will talk about here shortly as well. Here are just a few photos of some of the fish that we saw on some of these different monitoring techniques. And here is a graph showing some of our preliminary results. On the left, you have species richness. On the right is the total fish abundance that we saw throughout the course of 7 months. And we only have 5 sampling techniques up on here because the rest of them were only sampled for a shorter period of time, and we are not ready to present on that. But out of these 5 monitoring techniques, you can see that the swim transect resulted in the highest fish abundance, but the species richness scores were much lower compared to some of the other monitoring techniques, such as the BRUV, which is baited remote underwater video, or the mesh nets. Additionally, some species were only seen in certain monitoring techniques, such as pipefish only were seen in the mesh traps, and juvenile sheepshead were only seen on the timed swim transects. Therefore, it is likely that a multifaceted approach involving multiple of these monitoring techniques would result in the best way to monitor these kind of structures. And in fact, based on some of our preliminary data, a combination of the swim transect, baited remote underwater video, and the mesh traps would result in the highest diversity and species richness scores that we're seeing. Obviously, as I have said, this is preliminary, and we're still conducting ongoing trials on testing different methodologies, and we'll see how that evolves. If you're interested in any of this, though, please contact me and let me know your thoughts, and I'd love to talk to you about it. Thank you.
Thank you. And last up in our 3-minute session, we have Andrew Woolley, who's going to tell us about big sawfish in the southern Indian River Lagoon. What are they doing?
Kind of. So this story really begins with the U.S. Sawfish Recovery Hotline, because generally speaking, sawfish are kind of difficult to find. But the hotline allows us to collect information from boaters, anglers, and researchers whenever they're out on the water and they might happen to come across, see, or catch a sawfish. And generally speaking, we get about 500 plus reports per year statewide, but in recent years, the IRL has really been starting to kind of wake up. And so since 2020, we've received an average of about 50 reports per year, and most of those reports from the Southern IRL are what we consider big sawfish. Big is kind of relative, but when we're talking about sawfish, we're referring to sawfish over about 2.2 meters or about 7 feet long. That would be considered big for a variety of kind of life history reasons. And these reports have led to a number of collaborations with researchers over here, as my lab is actually based on the West Coast in Port Charlotte. But due to those collaborations, the first big sawfish that we have a record of here being tagged was tagged in 2016 by our colleagues at Harbor Branch. And you can see we caught a couple sawfish here and there, just opportunistically in other people's sampling in the early years. But in 2022, we made a concerted effort to start coming over here ourselves and targeting large sawfish. And most of that sampling, funding is tight, so we can't necessarily sample all year, but we used that sawfish hotline to really target April and August, because that's when people were telling us, hey, you gotta come over here and catch these sawfish. And we've been really successful. We've caught 56 big sawfish, 47 of which were actually adults, well over 4 meters, but the average length was about 4 meters long, which is a total of over 2.5 football fields of sawfish in just 4 years. So the biggest of which was a 16-foot female that we caught just last year on rod and reel in the St. Lucie. And we found that we typically see more females than males. There seems to be some seasonality going on to when we actually see them. So we typically find adult males in the spring in April, and then adult females in the summer in August. And there's not much mixing, it doesn't seem so far. But we'd love to continue to study this further, and that's where you guys come in. So, like I said, we're not based over here. Most of you guys are. So if you're out there and you see a sawfish, please let us know. Call us, email us, just please tell us. Because sometimes we can actually respond to those things in real time. We might have a crew on the water or collaborators in the area that can actually go catch that sawfish, tag it, and we can learn more about the species so that next time I come and present here, I can actually tell you what they're doing. So, thanks.
All right, so that concludes all of our oral presentations for today. Can we all give a round of applause to all of our speakers again? So, thank you to all of them for sharing your thoughtful, innovative, and inspiring work in the Indian River Lagoon. Today we've explored new technologies, creative applications of applied methods, and forward-looking approaches to monitoring and managing the Indian River Lagoon. So now we have the opportunity to continue those conversations in a more informal setting over some nachos and beers. Yes. So I invite all of you to join us in the poster session and reception. There's a really wonderful chance to ask the question of the presenter that you didn't get to earlier, spark up collaborations, and support all of our students and early career scientists. Before we get to that, we do have a couple of announcements. So most of them have to deal with our digital posters. They're new this year. One thing I want to say, if you've already judged one, thank you for your enthusiasm, but they haven't actually presented yet. So if you have already judged them, do it again and they'll use the later timestamp on it because they didn't get the opportunity to actually talk to you yet. Second announcement on the digital posters, Robert Cheatham had to withdraw his poster. His wife decided to have a baby today, and apparently that's more important. No, it is. So we're all very happy for him, but he will not be there to present his poster. So please help yourselves to food and refreshments, and then we'll all gather again here at 7:30 for the student awards. We're very excited. Nope, I'm wrong. Judges need to submit by 7, and we will gather here at 7:30 for student awards. But please submit all of your judging by 7. Thank you all for being part of such an engaged and collaborative community, and let's keep all of our conversations going. Thank you.